Yes, so let us go with the introduction chapter of the alcohols, phenols and ethers. Let me see what do we have in this prescribed syllabus for grade 12 with the NCERT books. So in alcohols, phenols and ethers, you are going to study about classification. You're going to study about classification, that is types of alcohols, monohydric, dihydric, trihydric, and if it is coming back to from the classification, we are primary, secondary, tertiary. Okay, fine. Then we will be doing something called nomenclature. We'll also be studying about a topic like once we are done with all the nomenclatures, I've planned for a class for the whole of nomenclature at a stretch, from starting from haloalkanes till amines. I'll be doing one particular class, a session of 40 minutes for the nomenclature, including all the compounds. So I'm not picking up along with the chapter. Yes, after classification and nomenclature, we'll be doing physical properties. We'll be learning about preparations of alcohols, phenols and ethers. After the preparations, I'll gradually drop in. So if I speak about alcohols preparation, let us see what do we have. We have under alcohols for your prescribed syllabus, we are going to prepare alcohols from alkenes. We are also going to prepare alcohols from alkenes by a name reaction called Hydroboration Oxidation reaction. Yes. Then I'll be preparing alcohols from carbonyl compounds. So what are carbonyl compounds? So when I speak about carbonyl compounds, I'll be basically picking up aldehydes. I'll be picking up ketones. I'll be picking up acetyl chlorides. I'll be picking up esters, all these. I'll be categorizing and showing you all the things. And after carbonyl compounds, I'll also be like further if you go just into the depth alkene, because both are alkenes. Here also carbonyl compound. Then I'll go to a class of compounds called Grignards or organyl metallic compounds, that is from Grignard's reagent. So this is where I'm going to prepare alcohols. When I go to phenol preparations, yes, so in phenol, I'm going to prepare phenol from haloarenes. So haloarenes, how do we write? Benzene ring with an X. X can be chlorine, bromine, fluorine also very less amount, which will be studied already. Fluorine, chlorine, bromine and iodine. I'm going to prepare phenols from BDC. We have done already BDC. BDC is nothing but benzene ring with N2Cl. I'm also going to prepare phenol from benzene sulfonic acid. Benzene sulfonic acid. So what is benzene sulfonic acid? A benzene ring with SO3H. So benzene sulfonic acid, yes. After that, I'm going to prepare phenol, the most famous reaction, from cumene. This was asked last year. From cumene. Yes, from cumene. So these are the preparations of alcohols. And if I speak about ethers. When we pick up ethers, I'm going to prepare ethers by a process called dehydration. And I'm also going to synthesize ethers by a process called Williamson ether synthesis. So these are the list of preparations of alcohols, phenols and ethers, which we'll be doing. We'll also be doing different reasoning questions on all these topics. Yes, please note it. I'll come back to the next subtopic. Yes, so let us come back to one more question. We have done almost 2 questions based on the structure of function groups. We have picked up reasoning question like inductive effect plus I effect, minus I effect plus R effect, and we also told double bonds shorter than single bond. Let us come back to one more question. Here, the bond angle in alcohols is slightly less than 109 degree 28 minutes. That is the tetrahedral angle in alcohols. Why? Basically, when I see the structure of alcohols, it is like this, right? So when we see the structure, it's basically, or it resembles tetrahedral structure. Now they are asking us, why is this less? It should be 109. Why is this less? Simple reason, nothing. Now when I speak about this highly electronegative oxygen atom, what are you finding here? You have, these are your bond pairs, bond pairs, bond pairs, bond pairs. They are lone pairs. So they are lone pairs on both the sides. Now because of the lone pairs, so what reason will I write? Because of lone pairs on oxygen. So lone pairs on oxygen, you are finding lone pairs on oxygen both the sides because of this lone pair repulsion. So this and this will start repelling, yeah. So LP repulsions. So what happens to LP repulsions? It will try to drag the bond towards this, like, you know, it's trying to drag. This is first of all electronegative in nature, and because of the repulsions further, it will, instead of this bond expanding out, it will try to pull the bond closer, right? LP repulsions, bond angle decreases from 109 degree 28 minutes to 108.9 degree. We very well know LP repulsions are stronger than BP repulsions stronger than BP repulsions, right? This is your main reason. If you just mention this and show them the concept, the answer is complete. Let us read one more. Why is the bond angle in ether slightly greater than tetrahedral? Here they said it is lesser. Here they are saying it is greater. Here 109 degree, less than that, but it is 111.7. Now what are you finding? What difference are you finding? Here you have lone pair. Here also you have lone pair. Here you have a smaller hydrogen atom with 3 hydrogen atoms, 1 carbon. But here what's happening? Only difference in ethers is, apart from the lone pairs, you have 2 electron donating groups. Alkyl groups are always electron donating. So here there are 2 electron donating groups. They keep on donating electrons towards this. When they are donating electrons towards it, there is a lot of electron cloud created, yeah. So now I'll write, here I spoke in terms of oxygen. Here I'm going to speak in terms for ethers. You're going to sponsor, this is your ether. So in ethers you're going to speak due to repulsions between 2 bulkier, due to repulsions between 2 alkyl groups. Repulsion between 2 alkyl groups, your bond angle increases from 109 degree to 11.7 degree. So 109.28, okay, specific, yes, 28. So here it was due to difference in electronegativity and your lone pairs. Here this is basically due to your alkyl group. Please note it. Now I'll be starting with the preparations of alcohols. I already given the index for the preparations of alcohols. Let us once again write what are the subtopics for preparations of alcohols. So when I speak about alcohols, I can prepare alcohols from alkenes. I can prepare alcohols from alkenes. There is one mechanism here, very important mechanism. I'll tell you how to remember that. And this particular mechanism is called acid catalyzed hydration. Okay, acid catalyzed hydration is a conversion of alkanes to alcohols in the presence of an acid. Okay, next would be your hydroboration. I'll write this preparations. Okay. Hydroboration Oxidation Reaction. Hydroboration Oxidation Reactions. The next type of reaction is preparation from carbonyl compounds. Carbonyl compounds, I'll be picking up aldehydes. I'll be preparing this one from aldehydes. I'll be preparing from ketones. I'll be preparing from acetyl chlorides. I'll be preparing from esters. Yes. After this, I'll be also preparing alkenes from alcohols from Grignard's reagent. From Grignard's reagent. Let us see this reaction. First, I'm going to pick up this. So, write the heading: preparations in block acid catalyzed hydration of alkenes. Right. So this is your heading. They'll ask you the mechanism also. Let us see. Basically, we have already studied whenever I have an alkene with me, alkene has a double bond. Because of this, it undergoes addition reactions. And one more thing which I have studied is alkenes undergo Markovnikov addition. In that addition only, Markovnikov addition as well as anti-Markovnikov addition in the presence of peroxide. So let me use that and write. Suppose if I have an example, a smaller alkene, pick up anything, ethene, right? Now, fine. Why did I pick up this? This is a symmetrical alkene, because when I take this and see, when I hold my hand, on either side I have equal number of carbon atoms. Suppose if I add HOH to this, fine, simple, H and OH minus. H goes and adds here and OH comes and adds here. So I get C, this double bond is broken, single bond C, H, OH, 1, 2, 3, 4, 1, 2, 3, 4, simple. Suppose if I pick up one unsymmetrical alkene. Now this is a symmetrical alkene. Now pick up one unsymmetrical alkene. Now this is unsymmetrical. Why? If I hold this here, on the either side of the double bond, here you have 2 carbons, here you have 1 carbon. So it is unsymmetrical alkene. Now to this unsymmetrical alkene, if I add H plus, no H minus. Yes, we very well know, according in unsymmetrical alkene, if you have an unsymmetrical alkene, it's going to follow Markovnikov addition, Mark addition. Yes, unsymmetrical alkene, in the absence of, there is no peroxide here. So the negative, so I'll write this H3, H, H. Now, according to Markovnikov addition, the negative part of the addendum adds to the carbon having lesser number of hydrogens. Correct? The negative adds to the carbon having lesser number, means this is 3, this is 1, this is 2. I have to add OH here and H here. So for that you have to break this bond. So how is this looking? C, H3, single bond, C. Now there is already one H, right? Write that H on the top. This OH minus, so dash. So CH2. So this H has added here, so this becomes CH3. Let me count. 3 plus 1, 4. This carbon has 1, 2, 3, 4 bonds, and this has 4 bonds. Right, done. So it's going to form which type of this one? This is, if an alcohol, if OH forms here, it is called primary. If it forms here, because this carbon has only 1 hydrogen, it forms secondary alcohol. Correct? Secondary alcohol. That is what is the example given. So any symmetrical, you can pick up any symmetrical, any unsymmetrical. So now this particular your board wants you to learn this particular reaction using an acid, right? You have to show, they'll ask you acid catalyzed hydration of alcohol. Here I directly studied Markovnikov addition, not a problem, but here I have to show using an acid catalyzed reaction and finally prepare alcohol. Fine, let us see that, note it and come back with the mechanism. Yes, so let us do the mechanism. Acid catalyzed hydration. Hydration means addition of water. Don't write addition of hydrogen. Hydration of alkenes. Which alkenes? We're going to pick up symmetrical alkenes. Now I'm going to pick up symmetrical alkanes. Let us make this fine. So as I have written already the reaction, C double bond C, this is my symmetrical alkene. I am going to add HOH, but this should occur, this is a reversible reaction in the presence of an acid. So instead of H2SO4, I'll be writing H plus, not a problem, right? H2SO4, instead of writing this, just write acidic medium. So both are same, this or this. So this, the product which you get is, this is going to break here, OH comes and adds here. I get C, single bond, C and H and OH. I have to show this in the form of mechanism. Now, let us see the steps. First important step 1. First, important thing is, always remember, when I write H plus, right? Now, H plus can't exist like that in water, right? Fine, it's electron deficient H plus. So it will not exist as this form in water. So what it does, it immediately combines with water molecule. Right, when this H plus ion from the acid, when it is broken into H plus and the other nucleophile, it will immediately combine with water forming H3O plus ion. Now, this electrophile, now this is an electrophile, correct? Yes, plus charge. Now this electrophile will go and attack your alkene. So the first step, what should I write? Step 1, protonation of alkene. What am I doing? I am going to add proton to this, proton to alkene. Protonation of alkene is addition of proton. So you can also write like this, addition of proton, H plus. Fine. So take this alkene, C, I write a bit above, C double bond C. Right. Now you are H3O plus, right? Protonation, you pick up this, right? H3O plus. So how am I writing H3O plus? H O, H and O. Isn't it? H3O plus. Now 1, 2, 3, 4, 5, 6, 7, 8. Correct? Now, when there is a cleavage of the bond. When this is cleaving, what happens? This particular bond is broken and it is shared by H. And immediately this bond, whatever is there, it shifts to this. Now what do we get? We get, now this bond is broken, form a bond with hydrogen, C, these two are here, now this H comes in, attaches, second, now because this has lost a part of the bond, this becomes deficient and becomes carbocation. Right, and what else do we have? We have water molecule again coming. So that is the reason, what did I do? I added H plus here. That's why it is protonation of alkene, addition of proton. I am adding protonation of alkene, addition of proton. This is called your carbocation. Done. So second step. In your second step, you have to remember, yes. To this, now this has become electron deficient. There should be something to donate electrons. That means something should have a lone pair of electrons to donate to this carbocation. So now, which has lone pair? We will write nucleophilic attack of water on carbocation. Basically, we have this carbocation. Take this carbocation with H, yeah, and after that you're going to pick this carbocation, you're going to add water to this H, O, H, right? Water 1, 2, 3, 4, 5, 6, 7, 8. Fine. Now this has lone pair of electrons here, so this is going to donate electrons. This will come and attach to this carbon. How does this look now? C, this is your H. And your C, fine, this whole thing. Now I'm going to attach this whole group to this. So let me write this here and start from your electronegative atom, oxygen, hydrogen here, 1, 2, right? This is 1, 2, 3, 4. You have your OH, fine. So this is donated because you have a carbocation, fine. Now after donating, what happened? This has shared a pair of electrons to this. So this becomes plus. Just remember that. Yeah, because earlier this was plus carbocation to satisfy this, a lone pair of electron from oxygen has shared. Now oxygen, because it has shared its lone pair of electron, you get this forms of carbocation now. Now I'm going to pick this up and I'm going to write step 3. Now in step 3 what happens? I am gradually preparing alcohol, isn't it? Now what are we going to write? We will just write, now protonation I did, nucleophilic attack we did. Now I have to take out that OH. I just need this. So what do I write? Here I did protonation. Now you will write deprotonation of alcohol. So now you will deprotonate, means you will take out. So how will I take out that deprotonation? Pick this whole thing here, carbon, you have your hydrogen here and you have your carbon. Along with that you have an electrophile, that is O plus. Add one more water molecule to this, H2O. So now what happens? A bond or part of this H2O comes out with this H and this bond because shifts. Now when this bond shifts here, how does this look? Yes, carbon with H, done. Now this is single bond. Now this is C, right? You have no both the sides be iron, right? So CH2OH. Fine. What type? Let me count 1, 2, 3, 4. So indirectly, how does this look now? CH2, CH3, CH2OH. Isn't it this one? Same thing if I write this one. What do I get? CH2, CH3, 1, 2, 3, right? HH, CH2OH. Same thing, this is H and this is H. The same thing I have got. What did I get now? I have got primary alcohol. So please note the mechanism. Remember, protonation, nucleophilic attack, deprotonation. So before you go for your exam, just write 3 steps like this. Remember, protonation, nucleophilic attack, deprotonation, your answer will be complete. Very important mechanism, note it. Yes, so we've already seen reactions of alcohols. Basically we said when we go with alcohols topic, alcohols are going to show reactions with the cleavage of OH bond. We have done this. Alcohols show cleavage of the carbon oxygen bond. We have done that also. Now we are going to start with reactions. Let us write the heading, reactions based on lone pair of electrons of oxygen. Lone pair of electrons on oxygen atom. Okay, what do I mean by this? I mean, suppose when I take ROH like this, we very well know 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has a lone pair of electrons, one above and one below. So this is going to show a different type of reactions like hydrogenation or dehydration reaction, hydrogenation reactions, oxidation reactions. So let us list out what do you have. So reactions due to this, you have hydrogenation reactions, that is hydrogenation reactions where you are going to add hydrogen. Yes, this particular oxygen, or you will remove this oxygen and add hydrogen. And you have dehydration reactions, that is removal of water molecule. You will remove water molecule from this dehydration water molecule. You will first add water and then you will first add hydrogen, then remove water from that. You will also be watching oxidation type of reactions where alcohols are oxidized to aldehydes. Aldehydes are further oxidized to acids. In that way, I'll be showing different reactions. So let us start with the first reaction. You have one mechanism. In my earlier video, I've shown you acid catalyzed dehydration of alkenes to form alcohols. Right now, I'll be showing dehydrogenation reaction or dehydration reaction of alcohols. So first, let us write the heading. So what am I trying to explain? I'm trying to explain today a mechanism called, so write down mechanism, very important it is. It was asked last year, mechanism of dehydration of alcohol. So mechanism of dehydration of alcohol, just observe carefully what am I trying to do. So when I say dehydration, basically the meaning of this word is removal of water. For dehydration of alcohol, you're going to follow 3 important steps. Step 1, I'll write a bit, yes. Step 1 is protonation of alcohol. So basic, I'm going to pick up an alcohol and add protonation. What is protonation? Protonation is addition of H plus ions. Okay, protonation. Second step would be, I'll be eliminating water molecule. Elimination of water molecule. Elimination of water molecule. This is done? Yes. Now after this, in the third step, I'm going to again eliminate. There are two times. Once you'll eliminate water, and again second time you will eliminate or elimination of H plus and rearrangement. These are the steps. If you are writing these steps, at least you'll be getting half mark, but don't stop till that. You have to do the whole mechanism. So first is protonation, second is elimination, third is elimination of H plus and rearrangement. Let us start. Now I'm going to take one alcohol, basic alcohol. So let me take now CH3, CH2OH. This is our alcohol, ethanol. Now what am I going to do? I'm going to protonate it, right? I have to protonate it, but this whole protonation will happen in the presence of dehydrating agent, remember. So I have to protonate it. So this protonation is, or this proton is supplied by your dehydrating agent, that is sulfuric acid. So let me write one sentence here. You should have, whenever you are writing dehydration, you require agents called dehydrating agents. So in chemistry, what are the different dehydrating agents you have studied? You have studied in your grade 9 or 10, where you studied about silica. Remember, even you use silica for dehydrating, absorbing moisture. Yes, gradually when you came to grade 11, you have studied about calcium oxides. Yes, now in grade 12, when you're coming, dehydrating agents include concentrated sulfuric acid. Dehydrating agents include H3PO4, phosphoric acid. So whenever you see these, that means they are going to take out water from the molecule. So phosphoric acid can be one more dehydrating agent. You can also write silica is one more dehydrating agent which will absorb moisture. So in the presence of these dehydrating agents, yes, these are going to take out, or even calcium hydroxide, calcium oxide also you can use. So this is going to supply this H plus ion. So what's going to happen? So basically, this is like this, isn't it? 1, 2, 3, 4, 5, 6, 7, 8. Correct? Now, this H plus will come and attack this oxygen. So, how does this look now? CH3, your CH2 and your oxygen. There's one H and there is one H here. Okay, fine. So, because of this, now what happened? Oxygen has shared a pair of electron with this H plus. So, this is going to become, this has a pair of electron and this becomes plus. Correct? Now, I'm going to pick that CH3, same. I'm going to take that CH3, CH2, O, dot, your plus and H and H. This is what formed. Now, elimination of water molecule. What did I say? Elimination. There is a cleavage of bond here and the water molecule just comes out. So, what do I get? I get a which carbocation? Primary carbocation, right? Carbon with 2 hydrogens and water has come out. Done. Now, to this carbocation, observe carefully, you are going to eliminate hydrogen H plus and you're going to rearrange. So, what should I do? I'm going to take CH3, I'm going to take CH2 plus. Now, observe carefully, this is your H2, right? Hey, instead of H3, I'm going to write H. Observe carefully, this is already electron deficient and this H from here has to shift in this direction. So observe this H or this particular bond, yeah, from here will shift and this hydrogen comes out. So what do I get now? I get CH2, yes, double bond, CH2 and your H plus is again, that is what I written, elimination of H plus and rearrangement. That means whenever you are taking an alcohol, observe carefully, OH from one carbon, H from the other carbon is eliminated. That is a logical. Again, whenever you have two carbons, OH from one, yes, H from 1 is eliminated. Finally, water molecule is released out, and we call dehydration of alcohol. Right? Please note this. We'll start with some examples now. Yes, so now when I take this example, now I'm erasing it, remember. So let us take some examples and do the dehydration. But remember, you should always prepare an alkene. You have to prepare an alkene, you have to take out hydrogen from one carbon and OH from the other carbon. Let us start. So examples for dehydration, observe carefully, do dehydration. Right. Don't be in a hurry while doing, but please write the dehydrating agent. Suppose if I'm given ethanol, right? If I am given propanol, if I am given butanol, so how should I hydrate? Okay, it is all, not al. Al means aldehyde. So ethanol when I take, now observe CH3, CH2OH. Okay, this is in the presence of a dehydrating agent. H plus means sulfuric acid. I took that H plus. Now what did I say? OH from one carbon, H from one carbon will get released out, because that is what I've shown you in the mechanism. OH from one, H from one, what do I get? CH2, double bond CH2 and water. Ethene I get. Correct? Now let us try with propanol. Okay, 1, 2, 3, and this is your prop. Correct? One propanol. Now this is your CH3, this is CH2, this is CH2. Now I have to dehydrate it. Okay, yes. Now let me add one more. There is one more dehydrating agent specifically for alcohols, that is your aluminium oxide or alumina. You can add alumina also. Alumina is basically used for dehydrating alcohols. Or aluminium oxide or alumina, it's the same. Yes, now this alumina or dehydrating agent, so what it does, I told you, OH from 1. Don't do a mistake of taking H from here, OH, that's blunder. We've seen the mechanism. OH from 1, H from 1 is eliminated. So what do I get? I get a double bond here. So what do I get? CH3, CH, double bond, CH. Now 1, 3 plus 1, 4. 1, 2, 3, 4. This is 2. Remember, OH from here, H from here. Don't eliminate from this. So I get water molecule. Simple as that. Now let us start with butanol. What's going to happen to butanol? Let us see. Now when I am eliminating from butanol, two conditions. 1, 2, 3, 4. This is your butanol. Correct? Now CH3, you're going to take 2 and 2. Now what should I do? I have to take out OH from here and I have to take out H from here. Correct? Yes. Now this is alpha, beta. Now there are two possibilities. If I take out, now this is your H plus and dehydrating agent Al2O3. This is your H plus and dehydrating agent or Al2O3. Okay, fine. Now observe carefully. If you take out OH hydroxyl from here and if you take out H from here, what product do I get? This bond is going to shift here and I get CH3. This is CH2. Yes, this is single bond CH2 and this is your double bond. Yeah, that is what happened. Yes, so basically you picked up from here and you did this. Correct? That is, we should not do that, but let us see. So what is this now? This is 1 butene. Correct. Now one more option. OH from here, H from here and the bond, okay, OH from here and H from here and the bond drops in the second position. So what do I get? I get CH3, CH2, double bond, CH and CH3. So 2, 3, no, this is what? 1, 2, 3, 4, 5. Okay, now this is your double bond. Correct. Yes. Now what happened? 1, 2, 3, 4. 1, 2, 3, 4. Yes. Now what happened? What did I do? I picked up OH from here. Correct. Then I picked up H from here and the double bond shifted to the second carbon. So what is this now? But-to-ene. Correct. Now observe carefully. Sedzef rule. Yes. The highly substituted carbon is the major product. The highly substituted carbon atom is a preferred product. That is according to Sedzef rule. So this is your minor product because this is not substituted. Here we have two carbons. Here you have only one hydrogen along with carbon. So this is minor, this is major. So once again, according to Sedzef rule, 2 butene is more preferred than 1 butene because this is more substituted. Yes, go with that. Remember, butene 1-butene, 2-butene. If the question is asked which is more preferred, 1-butene is or 2-butene is preferred, you should clearly say most preferred product 2-butene is preferred confidently. So this is how you are going to show the dehydration mechanism. Let them give you any example, but remember adjacent carbons, not on the same carbon. Yes, please note it. Yes, so let us come back and do one more reaction which involves the lone pair of electrons on oxygen. So earlier reaction was dehydration of alcohols. Now something a bit different. Now I'm going to do dehydrogenation. So what is the difference? When I say dehydration, most of the students get confused here. Dehydration and dehydrogenation. Please note it properly. Simple. D means subtraction, right? Hydration means subtraction of water. Dehydrogenation means subtraction of hydrogen. Simple as that, right? Fine. So basic thing. So let me erase and let us start now. So whenever I say dehydrogenation reaction, you have to be very, very careful. Hydrogenation reaction. This will occur in the presence of, okay, I'm going to remove hydrogen in the presence of dehydrating agents. What are the dehydrating agents? Just like copper, correct? Sulfur, selenium, all these are dehydrating agents, right? Some metal oxides also, all these are dehydrating agents. Remember, if you find them in the paper, that means the examiner wants you to take out hydrogen. From where should you take out hydrogen? That is important. Suppose if I have, now observe carefully, now I'm going to take primary alcohol, I'm going to take secondary alcohol, and I'm going to take tertiary alcohol. Okay, yes, let me show all the three examples so that we are not left with anything. So I'll write here, I'll put this a bit far. Copper, sulfur, selenium, all these are dehydrogenating agents. I'll just make it, I want some place. Yes, yeah. Now observe, primary alcohol, when I take carbon, oxygen, right, one hydrogen, one more hydrogen. Okay, so I'll write like this, hydrogen R. This is primary alcohol. Yes. Now instead of this R, can I write this as CH3? Not a problem, no? Fine. Yes. Dehydrating agent, I am taking copper at 300 degrees centigrade. As I said, it can be anything. I have to remove hydrogen. Now observe this carefully. Here, this carbon has OH, this carbon has H. Yes. Now, this H. Now what is dehydrogenation? I have to take out hydrogen. There is one hydrogen atom here. There is adjacent hydrogen atom here. Okay. Observe carefully. Take out this and take out this. Fine. I am taking this out. Now what do I get? What is left? CH3CHO. What did I prepare? Aldehyde. Primary alcohols on dehydrogenation give me aldehydes. First logic, remember, primary alcohols on dehydrogenation gives me aldehydes. Please note it. Note it separately in your book. Correct. Second, now I have to go back and make one secondary alcohol. So secondary alcohol, can I take this as CH3OH. Why is this secondary alcohol? Because secondary alcohol is something which has two alkyl groups and one hydrogen. So this is secondary alcohol. Now I have to add or take copper 300. So I have to take out hydrogen. Where should I take out? Observe carefully. H from here, H from here. Please, not here and here, wrong. H from here and H from here. So what do I get? Hydrogen. Now I should take out hydrogen, right? Hydrogen. Observe carefully. When I take out this and this, what do I get? CH3CO, CH3. What is this now? This is your aldehyde. This is your ketone. Now observe carefully. Secondary alcohols on dehydrogenation gives me ketones. Remember this, please. Important. Yeah. Now let us come to tertiary alcohol. In tertiary alcohol, now this is your carbon, this is your OH. there is one alkyl group here. There is, okay, I'll write this OH on this side so that it's easy for me. OH. So tertiary alcohols have 3 alkyl groups, correct? Now copper 300 degrees centigrade. Now observe, primary alcohols will give me aldehydes, secondary alcohols will give me ketones, but tertiary alcohols they prefer elimination reactions. Remember, they will not release out, means they will not, hydrogen is not easily released like this, but they undergo E2 mechanism where, observe, this is 3, right? This is H. Observe carefully. This H and this H, adjacent H, are released out. Now what happens? This bond is going to shift to this direction. What do I get now? I get CH3, C, double bond, CH2, and your single bond. I get an alkene. Remember, tertiary. So tertiary alcohols always give me alkenes. Don't write a mistake. They give me alkenes only because of elimination mechanism. Yes, this is your alkene. I took out from here and here. You can pick from here also, not a problem. You could because this is adjacent to OH, I just took out from there and I eliminated. So this and this, finally I got alkene. So please note it, dehydrogenation reactions of alcohols, primary, secondary and tertiary. When I do my questions, I'll be picking up examples related to this question also and we'll solve it. Thank you. So welcome students back to one more session of your organic reaction mechanism series. Now what mechanisms did we learn? We have learned aldol condensation, done. We have learned the reaction mechanism of carbylamine reaction. We have learned the reaction mechanism of Gabriel phthalimide synthesis. Now let's come back and learn one more reaction, that is dehydration of alcohols. So the reaction which I have chosen today is dehydration of alcohols. Done. Right. So in dehydration of alcohols, basically, as we know, dehydration is nothing but removal of water. Right. I'm going to take out water using what? Sulfuric acid. That's the reason we are going to name this reaction as acidic dehydration. Acidic dehydration means I'm going to remove water using, or in the presence of acid medium, that is nothing but sulfuric acid. Right. So here basically I'm going to take alcohol, as the name suggests. What are alcohols? Basically they are hydroxy derivatives of alkenes, isn't it? How do we represent alcohols? When I have to represent alcohols, I'm going to represent with this formula ROH. Now what is R? R is nothing but, R means the general formula of this R is CnH2n plus 1. As I said, they are derivatives of alkenes. Yes, right. So that's the reason we have written this general formula. So what do we do here? I'm going to take, first I'm going to take alcohol. Okay, we're going to take alcohols rather. Which alcohol I'm going to take? Here I'm going to take primary alcohol, remember. So I'm going to take primary alcohol. What am I going to do? I'm going to treat or heat it with concentrated sulfuric acid. So I'm going to take concentrated H2SO4. So in this step, what happens during this when you're heating with concentrated sulfuric acid? There is a removal of water, isn't it? Yes, there is elimination of water molecule. When water molecule is eliminated from alcohol, in this presence of this acid hydrogen, so acid means acidic hydrogen, that is with from the sulfuric acid, what is formed? There's a formation of an alkene. Remember, alcohol to alkene. So this conversion of alcohol to alkene in the presence of acidic hydrogen or acid medium is called acidic dehydration. This whole process of conversion of alcohols to alkenes in the presence of acid or concentrated sulfuric acid is called acidic dehydration of alcohols. So one important thing, this is also an example of beta elimination reaction. What is beta elimination reaction? That also we'll see. Example of beta elimination reaction. Done. let's see the step, let's see the reaction, and let's see the mechanism also for this. Right. So in the first step of acidic dehydration, what am I going to do? My requirement is I have to take an primary alcohol for this, isn't it? Right. So that is what we said, primary alcohol getting converted to alkene in the presence of an acid medium. That is that's the reason we are calling this acidic dehydration. We're taking out water in the presence of an acid, because sulfuric acid is a dehydrating agent. Yes. So I'm going to take primary alcohol. What is primary alcohol? First let us write the functional group. Alcohol is OH. Okay. So primary alcohol, I'm going to take 2 carbons. Primary alcohols are those which have, okay, H, right? Yes. So what is primary alcohol? Primary alcohols are those which have 3 hydrogens. 1, yes, just see here, 1 OH group on one side and the remaining all are hydrogens. Yes. If it is secondary, there are 2 alkyl groups here. Means basically this is only 1 alkyl group and 1 OH and 2 hydrogens, primary. If it is secondary, there will be 2 alkyl groups here. If it is tertiary, there will be 3 alkyl groups here. Right. So I'm going to take a primary alcohol or ethanol, basically primary alcohol or ethanol. Right. Now, so the same primary alcohol, I'll write it in this way. Just see, same thing for easy mechanism. So I'm going to write alkyl group here. Then I'm going to write OH here. Simple. H and H. Primary alcohol. Yes. Now I'm going to treat it with concentrated sulfuric acid, H2SO4. It's a dehydrating agent and you're going to heat it. In this first step, water is eliminated from this, because you're heating with concentrated sulfuric acid, water is eliminated, right? So this is alpha hydrogen, this is alpha the carbon, this is beta, and from wherever there is OH, we are going to take hydrogen from beta and OH from alpha, and this bond shifts in this direction and you're going to get alkene, CH2 plus water molecule. So this is ethene. Done. Now, what is the ease of dehydration of alcohols? Let us write that. Always remember the ease of dehydration. What is the order or how it goes about? Let's see. The ease of dehydration is, always remember, tertiary alcohol. Tertiary alcohol ease with secondary alcohol. It's an ease with, greater ease with primary alcohol. Okay, of dehydration takes place in this order. Example, if I take tertiary, all 3 alkyl groups OH, greater, secondary 1 OH and OH, tertiary, okay, this is tertiary, this is secondary. Now I have to write primary alkyl groups. So this is the order, remember. Right, so all this is how it goes about in the dehydration process. Now when I have to write the mechanism part of this, hope students this is clear for you all. Now let me write the mechanism. So in step 1, mechanism of dehydration of alcohols, let us write the heading. So mechanism of dehydration of alcohols. Mechanism of dehydration of alcohols. Right. First thing, you're going to take primary alcohol, isn't it? You're going to take primary alcohol. Fine. This step 1, what is going to happen? Sulfuric acid, whatever you're going to take, that is your concentrated part of this dissociates into HSO4 minus and H plus. This is done. Any doubts, students? Hope this is clear. There's nothing big logic in this. So simple. I have taken the dehydrating agent. It dissociates into HSO4 minus and H plus. That's done. Now let us take the primary alcohol. So carbon, as I said, primary alcohol has 1 alkyl group, that is here CH3, and 1 OH and H. Now I'm going to take this H plus here. 1, 2, 3, 4, 5, 6, 7, 8. Right. In the first step, water molecule is eliminated to form ethyl carbocation. So whatever is there, this one, this is elimination of water molecule, right? So first, this attack of this H plus to this OH minus. What do you get? H, 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 first carbon, second hydrogen, hydrogen, O, one H and one H. Hope this is clear, right students? Yes. Now 1 2 3 4 5 6 7 8, and there is formation of protonated alcohol, right? So here what happens, there is a cleavage of the bond, and this bond shifts to this oxygen. So what is this? This is nothing but protonated alcohol. Okay, then from here, from this step, as water is eliminated, I have to write this water, isn't it, here? H2O, C, H, hydrogen, hydrogen, C, hydrogen, hydrogen plus. What is this called? This is nothing but the formation of ethyl carbocation. This is ethyl carbocation. Okay, students. Now I am going to take a new molecule of alcohol again, right? Take a new molecule of alcohol minus H plus. So there is a shift of bond, again a new molecule is taken, this is lost, finally there is shift of H, and I am going to get carbon, carbon, double bond, carbon, carbon. What is the name of this compound? This is nothing but ethene, right? Yes students. So what a molecule here, important thing is hydrogen from beta position, this is alpha, this is beta. Hydrogen from beta position is eliminated. Always remember, hydrogen from beta position is being eliminated, that's why it is beta elimination, right students? Right. Now let us take one more example. So if I take CH3, CH2, CH2, this is also primary only, isn't it? Because this alkyl group. Now I am going to take concentrated sulfuric acid, as I said, on heated. From where it is removed, which is this? This is alpha, this is beta. This is alpha, this is beta. From where is the hydrogen eliminated? It is always eliminated from the beta carbon. Yes students. So what do we get when double bond? OH from here, H from here. Yes students, right? So OH from here, H from here. Finally what product do we get? CH3, CH, double bond, C, CH3. So what is the name of this compound? It is butene. Okay, instead of butene, here in this case it is butene. This is according to Zaitsev, because according to Zaitsev rule, more stable alkene is formed, isn't it? Where chances of two alkene combinations, the two alkene combinations are formed, but here the most stable product is butene. Yes students, let's see the reaction mechanism for this. Yes, so how did I get this? Let me draw one line and see. First step, as I said, sulfuric acid is dissociated into H plus and HSO4 minus. This is done. Okay, let me put this as 1. In the second step, I am going to take the same alcohol, CH3, CH2, 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 OH. 1, 2, 3, 4, 5, 6, 7, 8. Now I am going to take this H plus from sulfuric acid. Correct. There is attack of this hydrogen here. Yes. What do we get? CH3, CH2, CH2, one more CH2, then O, H and H. So 1, 2, positive charge. This is called protonated alcohol. What is this called? Protonated alcohol. Done. Next step. What is the next step? I hope this is clear, students. This protonated protonated alcohol, whatever is there, right? We are going to remove water molecule from that. Let me write that protonated alcohol, CH3, CH2, CH2, OH and H, right? There is a cleavage of the bond here. So remove water molecule. What? Plus. What does it look? Your CH3, 1, 2, 1, 2, 3. So CH3, CH2, C, H. CH3 is here written, CH2 is here written. This CH done. One more CH and plus, isn't it, students? The cleavage of bond plus. What is this called? This is called primary carbocation. This is primary carbocation is formed, isn't it? Right? So primary carbocation is formed. Done. Now rearrangement happens at this stage. Let's write that. The next step. This is your fourth step. Here rearrangement takes place. So during rearrangement, what will happen? There is a hydride shift. So during this process, what happens? There is a hydride shift. During this process, what happens? Due to this hydride shift, there is a secondary carbocation which is formed. Primary is over. Now secondary is going to form. Let's see this. CH3, CH2, C, we have written earlier also, H, this positive charge here, the primary carbocation. Now this hydride from here is going to shift to this carbon. What is this called? 1, 2 hydride shift. Hydride shift. Remember this. So how does this look now? It's going to look like CH3 is here. Now CH2, C, because the hydrogen has shifted to this carbon, this it gets up a positive charge, and this is CH3. Done, students. What is this called? This is called secondary carbocation, because there's a hydride shift, 1, 2 hydride shift. Now let me take the same secondary carbocation. Now unstable carbocation, isn't it? This is unstable. Secondary carbocation is unstable. So what will happen? This unstable carbocation, it loses a proton. From which position? From beta position. That's why it is beta elimination. Right. Let me take that. So CH3, CH2, CH. Now the secondary carbocation is here. Correct. Now let us write this. This is unstable. Unstable. So what does it do? Here it's going to lose. It loses proton from which? From beta position. It loses proton from beta position. Done, students? Yes. So when it loses proton, I am going to take out proton from beta. This is alpha which we have taken. This is beta. Right, so it's going to the earlier shift, same thing. We are going to take out a proton from here, that is from the beta position, and finally form an alkene. Now let's see how does it happen. So let me write this H as one hydrogen here. Let me write this H. This is done, students. Yes, there is removal of hydrogen, beta position. There is shift of this bond just into this carbon. What do I get? CH3, CH, double bond, CH, then CH3. So this is nothing but your but2ene. Right, students? So this is your complete reaction of dehydration as I explained step by step. Let me take out from the first page. I have written 3 different pages for dehydration. First I said, in acidic dehydration, primary alcohols are getting converted to alkenes by dehydration process. Right. Then I have said, I have taken the primary alcohol which I have taken here is nothing but ethyl alcohol. Done. So I said this is also called beta elimination, and I have also
just showed you how it goes about. But here this dehydration, for simple thing, no problem, we just directly got, we eliminated water and we got ethene. But what is the order? Tertiary, secondary and primary. This is the ease. Suppose if I have to write the mechanism, I've shown you the mechanism how it forms. Finally I get an ethene. But in the case of, suppose if you have an alcohol like this, it's going to follow Saytzeff rule, where the product which we get is butadiene. So I have shown step by step how it goes about, how I get, how there is rearrangement or the hydride shift, how primary carbocation gets converted to secondary carbocation. Now finally, to form a stable product, there is elimination of H plus, right, beta elimination, and finally there is formation of double bond between two carbons, where butadiene is a major product. So this is your acidic dehydration, students. So thank you for watching. Hope this is clear, students. Any doubt anywhere, please let me know in the comment section. I'll show you again from the first. Please note it carefully, all the 3 pages which I have written, so that you have a clear notes of everything. So in the dehydration process step, this is the first reaction step, students. You can pause it and note it, right? After this, the next step is this. I have shown you this reaction. This is the complete reaction process. Then after this, I have taken the mechanism step for the whole thing. Yes, after that I have taken one more example of this. What is this alcohol? 1, 2, 3, 4. Propanol. I have again shown the Saytzeff elimination and Saytzeff rule. And finally, this is the final mechanism of reaction. Thank you for watching. Stay connected. I'll meet you again with one more name reaction.
Yes, so students, we have seen the first acid catalyzed hydration of alkenes to prepare primary alcohols. Now let us come back to one more name reaction, that is hydroboration oxidation reaction. Please write the heading. Hydroboration oxidation oxidation reaction. Yes. So when I speak about hydroboration oxidation reaction, basically, so there are two probabilities. Either they'll ask you directly with the name, like write the hydroboration oxidation reaction of alkenes. That is one way. If they're not asking that, they may give you the reagents and they'll ask you to write the products. How? For example, they'll give you this and they'll give you the reagents like borane with tetrahydrofuran in the presence of peroxide and OH minus, and they'll ask you, give you a question. That means they want you to do the hydroboration oxidation reaction. Let us see. Now in hydroboration oxidation reaction, basically what are we going to prepare? I'm going to take an unsymmetrical alkene here. I'm going to pick up an unsymmetrical alkene in the presence of very important two reagents. Yes, first would be BH3. What is BH3? BH3 is basically, suppose if I come back, BH3 borane, this is called borane. Borane I have got from diborane, right? But what is the dimer of this? If I make double of this, B1 becomes B2. H3 becomes H6. This is diborane, right? So I'll write this clearly. B2H6 is diborane. So the monomer of diborane is borane, right? I'm going to take borane now. Along with this, I'm going to pick up in the presence of THF. So I have written this here. So borane, THF. I'm writing about THF. THF, what is the full form? It is called tetrahydrofuran. Right? If I write the structure of tetrahydrofuran, like if I just pick up this furan for your information, it is like this: oxygen 1, 2, 3, 4. This is your furan ring. Fine, heterocyclic compound. And then after that, I also require hydrogen peroxide in the presence of base OH minus. Very important, I'll teach you what it is. So once I take all these things, if you find these in the reaction, if you find these in the paper, remember they want you to convert unsymmetrical alkene to your primary alcohol. You will be preparing primary alcohol from this is your procedure. The primary alcohol, very important. Let us do the reaction now. So just remember hydroboration. So if you have to write it in words, how will you write? Hydroboration oxidation reaction is a reaction where an unsymmetrical alkene by the mechanism of anti-Markovnikov's addition gets converted into primary alcohol. Primary alcohol basically the carbon which has only one alkyl group and all two other are hydrogens in the presence of BH3, THF, hydrogen peroxide and base to form. Okay, I've already written. This is how you're going to write the explanation. Please note it. I'll show you what is the mechanism for hydroboration oxidation reaction. Yes. So now when I am writing this hydroboration oxidation reactions, first important thing I have to remember in the reaction is I require an unsymmetrical alkene, correct? Yes. So in an unsymmetrical alkene, let us see the stepwise mechanism. So first I am going to pick up an unsymmetrical alkene. So I have picked up now as a 3-carbon chain propene. So take this propene 1, 2, 3, H, 1, 2, H propene. Now to this propene I am going to add, or this reaction is going to occur in the presence of, as I said, it occurs in the presence of BH3 borane. What is borane, or if I speak about diborane, they are highly flammable and toxic gases, right? Highly flammable because once so this diborane or borane we are not going to leave it because we want that, or we want the reaction to be continued forward. I'm going to take this borane. Along with that, I'm going to add THF. What is the role of THF? Let me see. Yeah, now if I take diborane, I said it is highly toxic and flammable. Let me see. Diborane, B2H6 is diborane, correct? Now how am I writing? BH6, right? 1, 2, H3, H, B, hydrogen. So 3, right? B2H6. Now this B2H6, what am I going to do? When I am adding this furan to this, tetrahydrofuran to this, what it does is this diborane, I already said, if this breaks up into this bond, particularly like this, BH3, this is what we have written, BH3. Now to this THF or tetrahydrofuran, this BH3 has said it is very toxic and flammable. It's going to come and form a bond with THF. It will just come here and it will just form a bond with THF. This becomes BH3. Yes. So now the action of BH3 is suppressed, so that reaction proceeds forward. Fine. So I'm going to take this BH3 and I'm going to start the reaction. Now second important thing, I require hydrogen peroxide. I'll show you what is the role of hydrogen peroxide, and in the presence of a base OH minus. Fine. So now when I take this particular reaction, just observe carefully. Here in this particular case, this diborane acts as an electrophile, right? Electron deficient. Here you have a double bond, highly rich in nucleus or rich in electrons. This acts as a nucleophile, right? Fine. Now basically this diborane, how am I breaking this diborane? Just observe. BH3, can I write it as BH2 and H? Both are same, right? BH3 I can write as BH2 and H. Now see, I said they're going to follow anti-Markovnikov addition. So what product do I get? CH3, single bond, C, H, this H will go and attach here, single bond, C, now your BH2. Simple, correct? Nothing. I just broke this here. Plus and minus, and I added that. It followed anti-Markovnikov addition. Now in step 2, now let me take this as step 1, right? I'm going to take this as step 2. Now in step 2, observe carefully. Now this whole thing is an alkyl group, correct? Now instead of this whole thing, this whole is alkyl and this is BH2, I'm writing that as R. Okay, this whole thing is alkyl R. I'm going to write this as BH2. Same thing. Every time it keeps adding. We are going to take one more propene. This is first time, this is second time. 1 CH3, this is CH, double bond CH2. One more molecule of propene. Now what happens? Again the same Markovnikov rule. Now this BH2, can I write it as H in H? Same thing. There is a cleavage here. H adds to this carbon. This whole group adds to this carbon. What do I get now? CH3. Single bond CH. Now there is one H. I said this H also will come and attack. Now you have single bond, you have CH2. Now what is left now? This CH2. After that I am left with BHR. So it is BHR. Right? Now observe carefully. Now how many I have? I have this as one alkyl group, this as one alkyl group. Let us take. In step 3, again this BHR, this whole compound. Now what did I do in earlier case? I took this whole thing as R and I took BH2. Here I am going to again take this whole thing as R, this as BH and this R. Now how many I have? I have R2BH. Every time one alkyl group is increasing, one hydrogen is decreasing. Now take one more propene, CH3, CH double bond, CH2. Same story again. There is a cleavage in the double bond. Here also there is a cleavage. This becomes plus and minus. So what happens? What product do we get? Now I get CH3, CH, one more H, single bond, and your CH2, and your whole this alkyl group comes and attacks here. Now observe, how many alkyl groups do we have? This whole thing is one alkyl group. This is 1 and this is 2. So let me write this Br2 as like this so that you will clearly understand. B, R and R. How many alkyl groups we have got? We have got 3 alkyl groups. 1 alkyl group, 2 alkyl group, 3. It has become bulkier. Now this has become a bulkier group. It has become a bulkier group, so it can't hold all the alkyl groups. Now this is the last step of the reaction. Now at this particular stage, fine, pick up that. How many are there? This is 1, this is 2, this is 3. So can I write it as R3B? Because all the H's have added. Here it is 2 hydrogens, 1 alkyl group, 1 hydrogen, 2 alkyl group, no hydrogens, all alkyl group. So this is your bulkier group. So to this bulkier group, now what are we going to do? So I'll write this bulkier group like this. Just see, R for easy for making it easy for you all. R and B. Same thing. Yes. Now your role of hydrogen peroxide starts here. Now your hydrogen peroxide starts hydrolyzing your the structure. Basically your hydrogen peroxide. What do? Now hydrogen peroxide acts, it will try to hydrolyze, means it adds your OH minus. So how many am I taking? Hydrogen peroxide, I'm going to take 3 moles here. Observe, because I have 3 RHs, right? So 3 H2O2, how does it look? H, hydrogen peroxide, I'm expanding it and writing HOOH, 1, HOOH2, HOOH3. Done. Now I'm almost done. This whole thing should occur in the presence of a base, correct? Yes. Now let us see. I have to prepare primary alcohol. Now see, 3 R's are here. Fine. So 3 R. I have 3 OHs here. 3 OH. So primary alcohol done. Now what is left now? Just see carefully. H3BO3. The leftover is H3BO3. That is your boric acid. H3BO3, your boric acid. Yes, simple. You have prepared which alcohol now? Primary alcohol. So the conversion of an alkene unsymmetrical using anti-Markovnikov of addition forming or finally converting into a primary alcohol is called hydroboration oxidation reaction. Please note the mechanism. Any doubts? Please let us know. Yes. Now we've already done preparations of alcohols from alkenes. One was using acid catalyzed hydration of alkene. Then I did hydroboration oxidation reaction. I also solved 2 questions based on hydroboration oxidation. Now let us come back to one more, that is a third preparation of alcohols. Now I'm going to prepare okay, I'll write a bit down. I'm going to prepare alcohols, preparation of alcohols from carbonyl compounds, yes, carbonyl compounds. Right, now let me give you certain clues so that it's easy for us to do. Now when I speak about, just remember 2 things in your mind, right? So whenever a carbonyl compound like, okay, aldehyde, suppose aldehyde, whenever a carbonyl compound like ester, whenever a carbonyl compound like acetyl chloride, right, whenever an acid is given to us, right, and if these are treated with reducing, or if these are treated with some certain catalysts like nickel or platinum or palladium or lithium aluminum hydride or sodium borohydride, all these are reducing agents. They act as a catalyst by adding hydrogen, right? All these will get converted, or they will turn into primary alcohols only, right? Acid, not directly, it will get converted to ester, then it will become primary alcohol. But aldehyde will convert to primary alcohol. Ester also will give, you will get a mixture of primary alcohols. Acetyl chloride also you will get primary alcohols. Remember this, very important. Next one, when you are treating ketones, you are treating ketones with any of these, like sodium borohydride. Suppose if you are picking up sodium borohydride, if you are picking up this catalyst, ketones will always give you secondary alcohols. Remember this. If you remember this, let the examiner give you any sort of example, it is easy for you to solve. So using these clues, let us start preparing alcohols from carbonyl compounds. Yes. So I'm going to pick up the basic carbonyl compound. Let us formaldehyde. Observe carefully. Formaldehyde. Right? Okay. I'll give you a question. Then I'll come back to formaldehyde because this may confuse you. I'll go with basic aldehyde. Then I'll come back to this. Fine. Okay. Carbonyl compound, if I pick up aldehyde, I said, what did I say? Aldehyde on in the presence of reducing agents like sodium borohydride, they have to give me primary alcohols. Now let us see. In aldehydes, if I speak, now CH3CHO is an aldehyde, correct? Now I am going to add hydrogen to this. What is the preparation in this one? Basically, preparation of alcohol carbonyl compounds is nothing but reduction reactions. All these are reduction reactions. What is reduction reaction? Addition of hydrogen or removal of oxygen, correct? Yes, addition of hydrogen is reduction, or removal of oxygen is hydrogen. I am going to add hydrogen to aldehyde. Now observe carefully. When you are adding hydrogen, yes, H and H, I require some certain catalyst for this. Fine. So suppose if I pick up sodium borohydride, I said you can use nickel, platinum, palladium, lithium aluminum hydride, sodium borohydride. Now when I am using this, observe carefully, this H goes, and now this is your site. Fine. This H goes and adds here and OH here. So what am I trying to say? We are performing reduction reaction, that is addition of hydrogen in the presence of reducing agents. So now how does this look? CH3 CH2OH. See, I have prepared primary alcohol. This is what 2 carbon, right? Ethanol Now I have also got 2 carbon, ethanol. There's a lot of difference. Aldehyde to alcohol. Fine. Now I picked up this. Now I'll take up one more. Aldehyde. Other than aldehyde, I said you can also take your acids, right? Now let me take an acid. CH3COOH. I'm picked up an acid. Which acid is this? Ethanoic acid. Ethanoic acid. Now acid also gives primary alcohols, but not immediately. It will go 2-step process and then go. There is, if they can give you a conversion, convert propanoic acid to propanol, use this process please. So ethanoic acid, I'm going to use add H. Now observe carefully, this whole thing, addition of H, whenever you have ethanoic acid, there should be something called alcohol also, esterification reaction, right? So hydrogen will not add here. First I said 2-step process, acid plus alcohol, CH3OH. Acid plus alcohol in the presence of an acid gives me ester plus water. You remember grade 10th question? Acid plus alcohol in the presence of acid, it gives me ester. How? This is CH3COO and O. What do I get? CH3, COO, CH3 and water comes out. Acid plus water gives me ester. Acid plus alcohol gives me ester plus water. So this is ester. Now further, now to this ester, when I take this ester and I am going to introduce any reducing agent, right? Now either I can use nickel, platinum, palladium. Suppose I am using platinum here. Observe carefully, here you are going to add hydrogen. That is what is our aim, addition of hydrogen reduction process. You have to add hydrogen to this. So exactly break this bond here. Now CH3, I should have mixture of alcohols. So take your pen and exactly break. Fine. So what do you get now? CH3 OH is 1. Now observe carefully. Now I should get an alcohol here also. Most of the students, what do? They write hydrogen here well, but they get confused with this hydrogen, this alkyl group. Observe carefully, when you're taking hydrogen, while taking only with ester, try to pick up how many hydrogens. Now suppose I need 1 hydrogen here, I need 3 more here. So try to pick up 4 hydrogens. That would be easy for you. So what happened now? 1 hydrogen is added here. I am left with 3 more. 1. So this hydrogen, 1 will add, 2 hydrogens will add here, 1 hydrogen will add here. What do I get now? CH3, CH2OH. Both are primary alcohols. Observe carefully, esters. You'll get mixture of alcohols, right? So both are primary alcohols, both. But remember here, try to take 4 hydrogens because you get both. One here with 1 alcohol, the second one H2 here and OH, primary alcohols. Please remember, esters will give me primary alcohols, but acid to ester, ester to alcohols. Fine. Now I said I'm going to pick up acetyl chloride. What is acetyl chloride? CH3COCl. This is acetyl chloride. Yes, I'm again going to try to do reduction reaction. So acetyl chloride, when you're picking up, try to pick up 2 means indirectly what am I taking? I'm taking 4 hydrogens here, nothing. Use a reducing agent, pick up nickel, platinum, palladium, anything. Here let me pick up nickel. Now observe carefully, there are how many hydrogens I said? There are 4 hydrogens, right? So 4 hydrogens, how am I writing? H, means I am trying to add these. Observe carefully. Your H comes out with HCl. Correct? Done. These 3 are there, right? Now this is your site. Wherever there is oxygen, highly electronegative atom, these hydrogens will go and add. This hydrogen and this hydrogen, these 2 will combine and they will go and add. Because I have to prepare primary alcohols, this will add here and this will add here. So what do I get now? CH3, first one, CH2, second, and OH. Look here, I have again prepared a primary alcohol. So the conclusion is, whether it is aldehyde, whether it is acid, whether it is acid chloride, whether it is ester, I will be getting only primary alcohol in the presence of reducing agents. Right? Please note this. I will meet again with ketones. Yes, we've already prepared alcohols from aldehydes, ketones, acetyl chlorides and acids. Now let us prepare from ketones. What did I say? Ketones on reduction in the presence of nickel or platinum palladium or sodium borohydride. This is going to give me secondary alcohols. I have to remember this before I go for the exam. So ketones, if I speak about ketones, RCOR is ketone, correct? Then I'm going to use sodium borohydride with this. We are going to add hydrogen to this. Now observe carefully your side. Whenever some carbonyl compound is given to you, your concentration should go here. Oxygen. Fine. So how many should I take? H2 will add here. H will add here. Right? Okay. I have to prepare an alcohol, isn't it? So what should I do? Should I use H2H? Because if I add H2H, I'll get a primary alcohol. So this should not be the condition. Then what should I do? I should just add. Now basically I have to get an answer like this. RCHOH and R. This is what I have to get. Now what is extra compared to this? This is your secondary alcohol. What is extra compared to this? RN same. Carbon same. What is extra? Hydrogen. Here one hydrogen. So how many hydrogen should I take? 2 hydrogen. So I get secondary alcohol. Let me take an example. Right? CH3 CO C2 H5. This is your ketone. Right? Now how many carbons? 2, 3, 4. Butanone. So I am going to add sodium borohydride to this. Okay, then I have to add. Now I've added a catalyst. This should form an alcohol. So I'm going to add this reaction. My concentration should go here. These two are going to add here. So what do I get? CH3 C, yeah, OH and H and C2H5. What is the name of the compound? Now here we've got 2, 3, 4. 4 carbons is butanone. So here what did I get now? It is 1, 2, 3, 4 carbons. But this is also butanone. But this is but to all. Correct? Yes, secondary alcohol. This is secondary alcohol. This is how we are going to do conversion of ketones to secondary alcohols. Yes, so now we'll be preparing alcohols using Grignard's reagent, that is an organometallic compound. So let us see the reaction. Preparation of alcohols from Grignard's reagent. Grignard's reagent, right? Now let us see. Now we very well know Grignard's reagent is an organometallic compound. What is organometallic compound? If a metal is attached to a carbon atom directly and with a halogen, then it is called organometallic compound. Here RMGX. You can take R group. I'll be doing it here. Now when this is added to an aldehyde, I'll be showing with formaldehyde, acetaldehyde and ketone also. Fine. So when I am adding this to an aldehyde, so I've picked up this R, so I'll write this as RCHO. Fine. So when I'm adding this, initially just see Grignard agent. Now this is your Grignard's reagent. Grignard's reagent acts as a nucleophile. Right, remember that it acts as a nucleophile. So first there's a cleavage of bond. Here if I write the CHO, I am writing this as C double bond O CH. Here there's a shift of double bond or break cleavage. Magnesium attains a partial positive charge and alkyl group attains a partial negative charge. Now because of this cleavage, oxygen will get a minus charge and this becomes plus. Now observe carefully. This is minus. So the positive will go and attack oxygen. The negative alkyl group will come and attack this. So what do I get? I get R, C, H, R, O, MgX. Correct? Now, on further hydrolysis of this, I'm going to add water to this because I have to prepare alcohols. On further hydrolysis, there's a cleavage of bond like this. There's a cleavage of bond. So what happens? This is plus and this is minus. Your hydrogen, now this is minus, this is plus. This O goes and attacks here and this comes and attacks here. So what do I get? R, C, now this is here. I said this OH will go and attack that carbon, H and OH. Fine, this is what we are going to get. And now let us see how to do along with the example. Yes. Now let us take one example and see what can we do. The first I am going to take formaldehyde. Let us see what happens with formaldehyde if I take formaldehyde in Grignard's reagent. What is formaldehyde? The basic CHO. Correct? Yes. When I take formaldehyde, I am going to add now RMgX. So what do I get? I said already, magnesium, this goes and adds to oxygen, R goes and adds to this carbon. Again, MgX goes and adds to oxygen, R goes and adds to this carbon. You get R, CH, R, O, MgX. Correct? So again, this on further hydrolysis, you get MgOHX, MgOHX. Right, so MgOHX is done. Now what do I get? I get this directly as an alcohol. So I get RCH2OH. If I rearrange this, I get RCH2OH. So RCH2OH. Right, I got primary alcohol. Addition reaction. So with Grignard's reagent, whatever you see, all are addition reactions. Addition reactions. Now let me take one more example. Apart from formaldehyde, now I'm going to take acetaldehyde. Now CH3C, double bond O and H. Correct. Now this is formaldehyde as I've written. Now this is your acetaldehyde. Acetaldehyde. To this acetaldehyde, now instead of RMgX, let me write C2H5. R can be any alkyl group. So I write C2H5MgX. X can be fluorine, chlorine, bromine, iodine. Now I forgot. I have to write this in presence of dry ether, inert solvent, dry ether. So now observe carefully. This goes here. What did I say? Always MgX goes and adds to electronegative atom oxygen. We have already seen charge separation. This breaks up, this gets partial negative charge, this gets partial positive. So what product do I get? CH3C. Now this whole group comes here. OMgX. My product is still not done. I have to hydrolyze it to get alcohol further. So after hydrolyzing, again there is a cleavage of bond here between H and OH. Again there is a cleavage of bond here and I get CH3 still here existing. Now this carbon, this you have to get alcohol. C2H5, I'm getting it above CH2OH. This whole thing. And now what else is left now? The whole thing. MgOHX. Set. This should be HOH, right? No, I did a mistake. So CH3, C2H5, CH3, C2H5. Let me write this H down. CH3 here, C2H5 down. This CH, this OH will come and add here, and H will add here. Fine. So this is what we have got. Now, let me do with ketone now. Let me see what is going to happen with ketone addition reactions. So third, I'm going to take ketones. Right, ketone RCOR plus RMgX. What do I get now? Let us do with the reaction and then come back and write. CH3CO CH3 ketone. Now I'm going to write RMgX, addition product. You have to cleave the bond here. This becomes partial positive, this becomes partial negative. Fine. Now this is your site where the magnesium comes and attacks. So you get CH3COMgX plus this is here, and your alkyl group is also there. Now this on further hydrolysis, H and OH. H goes here and OH comes and attacks this carbon. So what do I get? CH3 carbon. Your alkyl group is still there. Your OH is still here. Your CH3 is there. And MgOHX. Now what did I get? I got which alcohol? 3 alkyl groups. I got tertiary alcohol. You got tertiary alcohol. So please note it. Now I have to write this also. You get R, C, one more R group. Here also one more R group. Alcohol plus MgOHX. So ketones on addition with Grignard's reagent, we get tertiary alcohol. Please note it. Yes. So students, we've already done preparations of haloalkanes using alkenes, hydroboration, oxidation reactions. Then we have done from Grignard's reagent, from carbonyl compounds. So let me do the last preparation of alcohols from haloalkanes. Right. So preparation of alcohols from haloalkanes. Right. Basically, there was a question asked from this. Let me write the question so that's easy for you to answer in the exam. Yeah. Why does aqueous KOH form alcohols when compared to alcoholic KOH, which forms alkenes? Right. So just basic question. Let us see. Whenever you see in the paper alcoholic KOH and aqueous KOH, only one thing should strike your mind. That is, aqueous KOH will always give alcohols. Alcoholic KOH will always give alkenes. Remember this. Very important. Alkenes. Let us see why. Now, I want to explain this using an equation. Just see. Now, I'm going to prepare alcohols from haloalkanes. That is, let me take C2H5Cl. Right? Haloalkanes. I'm going to add KOH, that is aqueous. Fine. So immediately aqueous, as you see, you take out this KCl, add KCl, and the leftover is what? It is C2H5OH. Simple. Okay. Now let me write one more, C2H5I. I'm going to add aqueous AgOH. Okay, silver hydroxide. Then immediately your AgI comes out, and AgI comes out, and what do you get? C2H5OH. C2H5OH. Okay. Now question. I have to come back to the question. Just see. Now I already converted haloalkanes to alcohols. Now aqueous KOH nature. What is aqueous KOH actually? Aqueous KOH is basically an alkaline substance, right? It is alkaline in nature. So it is alkaline in nature. When something is alkaline in nature, what happens? What does it release when it is dissolved in water? It's going to release OH minus ions. OH minus ions. So what are OH minus ions? OH minus is a strong nucleophile. It is a very strong nucleophile. So what happens whenever you have aqueous KOH in solution, because of the nature of OH minus, immediately this OH replaces this nucleophile which is weaker than that, and you get the required alcohol. So you will write aqueous KOH is a strong nucleophile and it is alkaline in nature, and it immediately replaces Cl minus, forming an alcohol. Now compared to aqueous KOH, I can pick up here your AgOH, aqueous AgOH will give you more yield. Why? It is mild in nature, right? It is mild, but compared to KOH it is mild, but the result on the products are good. Aqueous KOH yields are high. So this is how you're going to answer. Let us come back and do the next nucleophilic addition reaction, that is with your Grignard's reagent. Yes, so Grignard's reagent already we have done in alcohols chapter, but once again let us do it so that we'll have a clear idea on that addition of Grignard's reagent around the carbonyl compound. So when we speak about Grignard's reagent, what is Grignard's reagent? It is an organometallic compound. That means you have a metal atom attached to the carbon atom, isn't it? RMgX is your Grignard's reagent, right? Now this dissociates into R minus and MgX plus. Yeah, let me see how does this go and add. Suppose if I'm going to take, let me write the general reaction first. So now I'm going to take a carbonyl compound, let it be aldehyde ketone anything. Now I'm going to add this R MgX. How does it this dissociate? This becomes minus, this becomes plus, this is your minus, this is your plus, I said. Now your negative, this is like this, isn't that correct? So now what do you get? You get a carbonyl compound with your alkyl group, and your oxygen is still, oh, okay, we'll directly add here only oxygen, OMgX. Yes, now this is unstable. Further, this undergoes hydrolysis. You have to always hydrolyze it to get the required alcohol. So H plus. Now when you are hydrolyzing it, observe carefully, this H goes and adds here. Correct? Now what do you have in this water? You have H and OH, isn't it? Now observe this H or this H, whatever is here, let me take from here. Okay, this H goes and adds to the magnesium, and the remaining OH goes and adds to this particular point. What do you get? I get group R, your OH, and what else is left? I say MgOHX. Am I not getting an alcohol? I am getting an alcohol, isn't it? So please see, this is your mechanism. I am going to show it for all the three, easy. But finally, you have to prepare an alcohol only. Right. Now, let us start with this first one. Let me erase this whole thing so that I require the whole board for showing it. Now, I am going to add Grignard's reagent to this. R. Yeah. Now, try to add it step by step. It is easy for you. When you are adding, this is plus, this is minus, isn't it? R comes in, attacks this. What do you get? Carbon, hydrogen, hydrogen. The carbon has this alkyl group and O minus is still existing. Now you can introduce the Grignard's reagent MgX plus. This is going to add to this oxygen. What do you get? You get one hydrogen, hydrogen, O, MgX and R. Because the compound is unstable and we require the alcohol, we are going to hydrolyze it. Right? When you're hydrolyzing it, I said H goes and adds to this. What do you get? MgOH and X, and your OH will come and attack this carbon because this bond is broken, isn't it? When the bond is broken, this becomes plus and this becomes minus. What do you get? I get H, H, OH and R. Right? So what is this alcohol? If I write this particular thing, it is basically like this, isn't it? CH2. Okay, now this is your alkyl group, alkyl head. The alcohol or the functional group of the OH is attached to a carbon having two hydrogens. When it is two hydrogens, which type of alcohol is it? Primary alcohol. So what am I going to get? I am going to get a primary alcohol. So formaldehyde with Grignard's reagent is going to give me primary alcohol. Let us write this. formaldehyde with Grignard's reagent RMgX will give me primary alcohols. Remember this, please. So if you remember this, if they give you primary aldehyde, you can easily form your primary alcohol, or the formaldehyde you can easily form alcohol, primary alcohol. Let me add. Now what is this? This is your acetaldehyde, isn't it? Now acetaldehyde. When I pick up an acetaldehyde, when I'm adding Grignard's reagent, step 1, now this is negative, this is your positive. What do I get? This negative is going to add to this carbon. As I said, carbon, try to put 4 bonds like this. Methyl and H. So CH3 on one side, H on one side. Now you have your R group here and your O minus here. Simple, it's the same thing. Now to this particular one, I'm going to add the leftover or the remaining cation of the Grignard's reagent. This MgX will go and attack this oxygen. You get again tetravalent carbon with CH3 on one side, H here, your O, MgX, and your R is still existing. This further undergoes hydrolysis. Yeah, what do I get? Your hydrogen goes and adds here, and see your CH3, your H, your O. So I should not take this, isn't it? Yeah, I have to take this because your OH is coming up, OH and your R. What else do I have? MgOHX. This is the compound. Now what is this compound? A carbon with 1 hydrogen and 2 alkyl groups. It is a secondary alcohol. Secondary alcohol. So what did we learn now? Acetaldehyde with Grignard's reagent. Let us write here. Acetaldehyde with Grignard's reagent gives me secondary alcohol. Remember this, please. Very, very important when they give it in the exam. If you remember such clues, it's easy for you to solve it. Let us come back and do a ketone. What is this? This is acetone or propanone. The same story again. R minus, this shifts here. What do I get? 1, 2, 3, 4. 2 alkyl groups on either side. 2 alkyl groups on either side. You get O is minus and R has already attacked. Now what should I do? Same like this. You have to add the Grignard's reagent, the leftover cation, which will go and attack this oxygen. So what do you get then? Carbon with 2 alkyl groups on either side, right? Now this becomes OMgX and R is still existing. Now what do? I have to hydrolyze this. As I said earlier, your H goes and attacks. When this becomes a carbocation, this OH minus goes and attacks this. What do I get? 1, 2, 3, 4. First I said take out that MgX. Write as MgOHX. Now fill everything now. CH3, CH3, your OH, this is your OH and your R. Now carbon with 3 alkyl groups. Which type of alcohol is this? Tertiary alcohol. So what should you write now? Very important. Ketones. Let me write here. Ketones with Grignard's reagent gives me tertiary alcohols. This is important. Very, very important. Please try to note. I've given you all the 3 examples so that it is easy for you to analyze. Yes, so we've already done the preparations of alcohols. Let us come back and see the chemical reactions of phenols. So when we go to the chemical reactions of phenols, basically your phenol ring shows 2 types of chemical reactions. First would be the reaction based on the cleavage of the OH bond. So you'll be finding reactions based on the cleavage bond. As I mentioned here, we have taken almost 1, 2, 3, 4, 5, 6 reactions which involve basically ionization of H plus ions. This particular bond is broken and easily H plus is replaced by the incoming nucleophile. And the second type, so let me write reactions involving cleavage of O and H bond. And the second category would be reactions involving the benzene ring. That means basically your benzene ring will show, means you'll be getting products of the ortho and para positions, both ortho and para. I'll also be showing what percentage of ortho and what percentage of para will be formed. So reactions involving only benzene ring. Only benzene ring. So like nitration, sulfonation, Friedel-Crafts alkylation, acylation, all these reactions will be dealt later stages. So let us come back and go on start with the reactions involving cleavage of OH bond. So basically when I did alcohols, right, I almost used the same type of reagents so that it is easy for you to do a comparative study. So what do we discuss in alcohols? Alcohols they are acidic in nature but less acidic compared to phenol. Remember, we are going to start with a concept called phenols are they're stronger acids than alcohols. Let me see the reason for the stronger acidity of phenols against alcohols. So when I go with the first reaction, now I've taken sodium metal here, fine. So we very well know the other day when I said alcohol, right, acid plus metal gives me salt plus water, salt plus hydrogen gas. There you are. Once again, when a metal piece or a stronger highly reactive metal is dropped into an acid, immediately it forms a salt along with evolution of hydrogen gas. Here also it's the same story. In the exam, if you find any metal like sodium, the stronger metal given to you, try to prepare a salt and then show the evolution of hydrogen gas. Let us come back. Now this is your phenol. As I said, these are the reactions of OH. Now this is where your cleavage occurs. Now just see, your sodium metal comes and attacks here. So how does this reaction look? Your phenol ring, your the cleavage of OH bond, and you have your sodium metal which is reacting. And what do I get? As I said, this is minus, this is plus, and this is plus. This comes in attacks and forming sodium phenoxide. Just see, ONA plus your hydrogen. How many hydrogen? We just have half, so half H2. Hydrogen gas is evolved. So because of this evolution of hydrogen gas, we call phenol as highly acidic nature. And one more thing I can just say, because phenol is easily able to release H plus ion, now the element or the substance which releases H plus ions is called an acid, isn't it? So one more factor with which I can call phenol acidic in nature is it can easily ionize this H plus ion. Point number one. It is releasing hydrogen gas when metal is dissolved. So with these two factors, I can conclude that phenol is acidic than alcohol. Yes. So this, what is the name of this? This is called sodium phenoxide. And that is your hydrogen gas. That's done. Now let us come back to one more reaction and see where you are just finding cleavage of this. Ma'am, how should I know whether I have to cleave the bond here when such reagents are given? Simple. Remember, you have, look here, here you have a nucleophile, correct? Here also, this one is acting in H2. Here also a nucleophile. Here also nucleophile. Here also nucleophile. That means when you find a nucleophile, basic substitution of the H positive with the negative, right? You'll replace this one with this and finally end it. So we also see some electrophilic substitution reactions. Now I'll just show in a few minutes. Now just see, I have this reaction. Now whenever you see ZnCl2 in the reaction, what is the role of ZnCl2? Remember, basically your ZnCl2 is deliquescent in nature. What am I trying to say? ZnCl2 is deliquescent. Try to understand what is deliquescence. Deliquescent means, deliquescent is something, suppose as you have seen in your lab, when you leave your zinc chloride salt in the watch glass, after a few minutes you find that moisture content in the salt, isn't it? So students who will get zinc chloride in the exam are the luckiest ones in the salt analysis, because after 10 or 15 or 10 minutes rather, it's going to absorb the moisture which is there in the room and finally become wet. Right? So deliquescency is the ability to absorb moisture, right? Absorb water content in the sin. So deliquescent, I said ZnCl2 is deliquescent. So whenever you see ZnCl2, that means this is going to take out water. It's going to remove water. How does it remove water in this reaction? Just observe. First, this is going to cleave this bond. Fine? Yeah. Now NH3. Now can I write NH3 as NH2 and H? Correct. Yes. Now what is this? What is the role of this ZnCl2? I said it is deliquescent. That means it's going to absorb moisture. It has to take out water. Now see this H and your OH, right? So just pick up this H and your OH is just going to come out, and what is attached, this whole NH2 is going to go and attach. So what do I get? This, because of the deliquescent nature of ZnCl2, phenols are converted into anilines. This is one conversion. Remember, what is, if an examiner is asking you to convert phenol to aniline, this is the easiest way. Pick up ZnCl2 and add to phenol. Immediately that moisture content is out, and you're left with, in NH3 you're left with NH2. So that is the speciality of ZnCl2. Let us come back to CH3COCl. Now what is the CH3COCl? It's called acetyl chloride. Why acetyl chloride? Look here, this is acetic acid, isn't it? CH3COOH is acetic acid, right? So I've taken out OH and replaced with Cl. So it is acetyl chloride. Fine. Now just observe, you have to cleave the bond here. Now this is your bond. This is your minus, this is your plus. Fine. This is your minus, this is your plus. So observe carefully. I'm going to take phenol. Yeah, and this phenol, already a bond has cleaved here. The positive end will go and attack the negative end. Yeah, negative end is still there. O, you should not take out that O. And you have your COCH3, so just make carbon COCH3. And what has come out? HCl has come out. Now what is this now? This whole reaction where acetyl group or addition of acetyl group occurs in the presence of pyridine to phenol is called acetylation. What is the name of this reaction? I call it as acetylation. I'm just adding acetyl group to this. Now there's one speciality about this reaction. Observe here what happened without pyridine. Always remember, acetylation, basically you require pyridine as a base. Now what is the role of pyridine here? Now what is the structure of pyridine? Pyridine structure is your ring. Yes, this is your NH, correct, fine, and you have your alternate double bonds. Yes. Now in this pyridine structure, basically this pyridine is acting, or it's going to act as a catalyst. First of all, let us remember, it's going to activate the ring faster to undergo acetylation. Now this pyridine, whenever you're adding this pyridine to this is going to go and attack this HCl. What does it do? This pyridine, as I said, it will boost up the reaction, it will go forward and you get this product. After getting the product, you also have HCl in the reaction. This HCl, what does it do? To prevent it to go back or backward reaction, when I add pyridine goes and combines with this HCl. Okay, this is plus and this is minus. Now this is called pyridinium chloride. Okay, what is this compound called? Pyridinium chloride. Now observe carefully. So this pyridinium chloride, what is its specialty? Now I took phenol, I did acetylation, then I got this compound, then I added pyridine, which came out as pyridinium chloride. Basically pyridinium chloride is a water soluble salt. It can easily dissolve in water. So what happens when you do such reactions? When this is completely soluble in water, I can take out that particular thing, it dissolves, and the leftover content is this. Now what is this leftover content called? Just name phenyl. Why phenyl? Because from phenol we have taken out H and added this. Now how many carbons are there? 2 carbons. Eth, correct? Now this is your ring, this is oxygen, so ethanoate, phenyl ethanoate. You have to call it as phenyl ethanoate. Let us come back and redo the reaction. First of all, let us define what is acetylation. Acetylation is a reaction where when phenol is treated with acetyl group, correct, in the presence of pyridine, which is acting as a catalyst, yes, we get phenyl ethanoate. How did I get phenyl ethanoate? HCl has come out, yes. Now what is the role of this pyridine? Pyridine basically is water soluble in nature. It is water soluble in nature. So once it is dissolved in water completely, it's already neutralized HCl, no? So not a problem. So once it is dissolved, the final product which I get a pure phenyl ethanoate, that is called acetylation. I've given you many questions in between. Please note it carefully. Yes, that's done. Now let me erase because I need the upper part of the board. Yes. So let us take out all these and let us come back and do these reactions. Now what do I have? I'm left with these reactions. Let us see. Now acetic anhydride. Now I have phenol. I have to cleave the bond here, and I have along with me same as alcohol, acetic anhydride. What is this compound? I wrote already. Watch that video. Acetic anhydride without water. Acetic acid without water. 2 moles. Now just cleave this bond here above. You cleave this bond here, you cleave this bond here. This H plus comes along with this. What do I get? I get acetic acid, CH3COOH. Yes, done. What else is left? You have your benzene ring, you have your phenyl ring with oxygen. So take that phenyl ring, take that oxygen. So what else is left? Now this is going to come and attack. Same thing as earlier. Again, name this compound. This is phenyl, 2 carbons, ethane, oxygen, OH, ethanoate. This is phenyl ethanoate. Yes, simple. You're just cleaving the bond above oxygen. Just cleave it above oxygen. This H plus and your COO minus. Let us write the signs. This is plus, this is minus, this is minus, this is plus. Okay, so the cation and the anion, will just come out and you get this product. Yes, let us come back. Now this is also done. Let's come and do one more. Now I'm going to see the reaction of phenol cleaving at which the bond oxygen and hydrogen. I have to cleave the bond here. Remember always, please. And I'm going to pick up a compound called, let me write in this way, ClCO. This is your compound. Okay, fine. So I'm erasing this also because I need it again. Yeah. Now simple. This is minus, this is your plus, this is minus, this is where it cleaves, and this is plus. Okay. As we know, your anion and cation comes out as HCl. Okay. Now what are you doing? What are you adding? You have 2 benzene rings here. Correct? Now I'm going to write this benzene ring here, and I'm going to write that benzene ring here. Okay. Yes. Now this oxygen is here. This CO is here. Yeah, done. Let us name this compound. Very important. First, let us name the reactants. So here this is phenol. Simple as that. Now, what is this compound? Earlier it is CH3COCl. So earlier it was CH3COCl. I called it as acetyl chloride. Correct. Now, what am I calling this? Instead of acetyl CH3 group, I have benzene ring. So I can call it as benzoyl chloride. Simple. Acetyl chloride is this, benzoyl chloride is this. Now I have 2 rings here, 2 benzene rings. Correct? Now how to name this? Simple. Name it as phenyl. Yeah. How many carbons do we have? You have 1 carbon, right? But from where have you got the particular ring from? That COC, benzoyl chloride, right? So phenyl benzoate. Yes, what did I do now? I took phenyl ring. I got this particular thing from benzoyl chloride. I should not write ethanoate because there is no 2 carbon chain. I have benzene ring, benzoate, phenyl benzoate. This is your ring. Now remember one thing, the reaction, I am defining something now. The reaction when a phenol ring reacts with benzyl chloride to form phenyl benzoate is called benzoylation reaction. Okay, this is called benzoylation reaction. Okay, there is one speciality about this reaction. This benzoylation reaction also is called Shortman-Baumann reaction Yes, this is also called Shortman-Moorman reaction, where you are following this basic reaction. Why did they call this reaction like this? Because this is the reaction mechanism where we convert aniline also to this product. That is the reason. So we use the same mechanism. So this particular reaction mechanism, whenever you're using, I require this, or the medium which I use is base. A base is quite important. If the examiner is asking you what is a speciality of this base, you have to just tell them base tries to, or it will allow the reaction to proceed forward. So I'm writing it here. Your sodium hydroxide or the base helps in forward direction, helps the reaction to go in the forward direction, to go or to proceed in forward direction. Yes, so this is your role, or this is your benzylation, this is your, this one, please note it. Yes, so now we have done acetylation, we have done benzylation. So just let's correct this. This is Shorten-Bowman reaction. It's basically benzylation reaction. So let us come back and do the final reaction of involving your oxygen and hydrogen cleavage, that is reaction with PCl5. We have done already this phosphorus pentachloride. So what is this? This is phosphorus pentachloride. Now let us see the reaction. So I picked up this phenol, again the same story. You're going to cleave that bond at O and H, correct? Now you're going to take PCl5. So PCl5, I have 5 chlorines, 1, 2, 3, 4 and 5. Correct? Yes. Now in this PCl5, where should I cleave the bond? I have to cleave the bond here. So basic thing, first HCl comes out. Okay. HCl comes out. Done. After that, you have POCl3 coming out. PO, phosphoxychloride. We have done this in alcohols also. So first this bond is broken, HCl has come out. Left is POCl3, that also is done. What is left? There is only one chlorine left with benzene ring or phenyl ring. You get chlorobenzene. Or what is the other name? We have haloarene, we have done haloalkanes and haloarenes, right? So this is again haloarene. Simple. So let us come back and discuss once again. Phenol shows different types of reactions. One is involving OH bond cleavage and other is benzene ring. So when it is cleavage of OH bond, it shows basically your acetylation reactions, benzylation reaction, as I said, Shorten-Bowman reaction, right? Please correct that. So acetylation reaction is done, benzylation is done, where you're getting 2 benzene rings attached. You've also used zinc chloride, where it is acting as a deliquescent. It's going to remove moisture when ammonia is added. Gradually, you also studied the reaction with phosphorus halides. So please practice the reactions carefully. Let us do one more question on boiling point. We've already done based on branching. We've already also done a question based on number of carbon atoms. And now let us do one more question similar to that. Fine. Suppose such type of questions are compulsory in your board paper. Comparison of acidic strength, comparison of boiling point, which is basicity in nature, which is soluble in water. There's compulsory question given in the board, so please don't neglect such sort of questions. Let us discuss. It's very easy, right? Among the following, which is the correct order in the increasing means you have to show in the increasing boiling point, which is the correct order. They've given me this order, this order, this order, and this order. Fine, so many things to do. But remember one thing, only simple logic. I already said boiling point is directly proportional to number of carbon atoms and inversely related to branching. If you remember this, all questions are easy. Right, I'm going to use this now. Now, propan 1-ol, prop 3 carbon atom, bute 4 carbon atom, bute 4 carbon atom, pent 5 carbon atom. What did they ask me? I have to arrange in increasing order. Most of the students, what did I've observed is, when they ask increasing order, they will write least here and maximum here. Mistake. Increasing order means the maximum should be at the end, minimum should be here. Right? Remember that. Fine. Here, prop 3 carbon, bute 4 carbon, bute 4 carbon, pent 5 carbon. Here, 5. Bute 4, this is also 4, this is 3, here 5, this is 4, this is 4, this is 3. Right, first of all, when I said it should be increasing boiling point. So when I see the first thing, so the maximum is at the end. Good. Here also maximum is at the end, but minimum is here, minimum is here. So I'll rule out this and this. Wrong. Not, because I have to arrange in the increasing order. Now I have to compare first one and second one. Let us see. Here 3, 3 correct. Fine. But here, here it is butan 2-ol. Here it is butan 1-ol. Here it is butan 1-ol. What is the difference now? Remember, if I take butan 2-ol, right? Butan 2-ol and I take butan 1-ol, what is the difference? Butan 2-ol, 1, 2, 3, 4. All is in the second carbon. Butan 1-ol, 1, 2, 3, 4. All is in the first carbon. Which is branching compared to both? Yes, butan 2-ol is branching. We very well know branching. Boiling point is inversely related to branching. This has branching, this doesn't have branching. It will have more boiling point, no? Because the surface area of contact is very less here. Dispersion forces are acting, weak intermolecular forces are acting. So this is branching. So butan 2-ol is branched. Branching. This is straight chain. Correct? This is branching, this is straight chain. So if it is branching, boiling point will obviously be less. We here, look here, what did they do? They have taken branching as more boiling point. This is wrong. So wrong. So the first order is correct. Remember, based on the carbon chain, smaller. Based on the branching, lesser. Increase because of the increase in carbon chain, and finally the carbon chain. The first order is a correct order. You will put a tick and leave so that the answer is correct. So you will write and finish off your answer. That's it. Yes, so let us see one more question based on the acidic nature, acidity of alcohols. So let us write the question. Compare acidic strengths of primary, secondary and tertiary alcohols. Suppose if this question is asked, right? How should I answer this question? Now, if they're not asking you like this, in this way, like primary, secondary and tertiary, if they're giving you an example, like if they're giving you some compound which acts as in tertiary alcohol, if they're giving you some other compound which is basically, suppose ethanol, right, primary alcohol, then also the answer would be the same. So let us write. So they've asked us primary, secondary and tertiary alcohols. First let me write primary here, let me write secondary here, let me write tertiary here. Fine, let us see all the three. Primary alcohol, when I say OH group on one side, yes, carbon and it has one alkyl group and two hydrogens, correct? In your secondary alcohol, when I speak, your OH group on one side, your one alkyl group, second alkyl group and one hydrogen. When we come to tertiary alcohols, carbon with a functional group OH and all the three are alkyl groups, isn't it? Your tertiary doesn't have any alkyl hydrogen group, all the three are alkyl groups. Now, Now, what do they say? When some question is raised on acidic strength, that means this particular compound has to release H plus ion, which is adjacent to oxygen atom. So release of H plus ion makes it more acidic. Let us see the first case. Here you have only one electron releasing group. Electron releasing group, that means plus I effect. So plus I effect, plus I inductive effect is only, there's only one alkyl group which is releasing. In this case, you have alkyl group only one. Here how many alkyl groups do you have? You have 2 alkyl groups. Here how many do you have? You have 3 alkyl groups. So what happens is, here also this is donating, this is also donating. But when it comes to tertiary alcohol, you have 3 alkyl groups which are continuously donating electrons or releasing electrons towards carbon. When something is releasing electrons around carbon, so what happens to carbon? This whole electron density is further pushed on to oxygen. This oxygen has a certain amount of electron cloud formed around oxygen. When lot of electrons are accumulated around oxygen, is there any requirement for oxygen to drag this electron from hydrogen? Not possible, not required, because already there are a lot of electrons or electron cloud which is accumulated. So what happens here? Due to 3 alkyl groups and plus I effect, electron cloud density, where is electron cloud density increasing? Here, around oxygen increases. Now, when electron density increases, what is decreasing? Polarity decreases. It will not break up into minus charge and plus charge. So, polarity decreases. When polarity decreases, acidity increases or decreases? Obviously, it is understood. Acidity decreases. It will not donate H plus ion. So, what should I write in the final order? Remember, you have to write primary is easier, it easily donates, right? So it is less. Fine means it can easily donate electrons. Secondary, then difficult, tertiary. That means here I can easily pick up, easily participates. It's difficult to break. It's very difficult for me to break here. So easily it can cleave, difficult to break. So this is the order. So this is primary alcohol, for me very easy. Tertiary alcohol, very difficult to break and pull out this H plus ions. Let us do this question. So we already saw that alcohols, when a metal is added to alcohol, just like an acid, it also behaves as an acid and releases hydrogen gas. So if a question is asked based on that particular reaction, let us see how to answer that question. So concept is the same, it's going to release hydrogen gas, but if a question is asked, how should I answer that in the exam? Now what do they ask us? Compare acidic strength of alcohols with water, right? Now let us start. First write water structure. Now water, this is your H, correct? Here also same, here electronegative, positive and positive, same story. Now this is your water. Now when I am writing alcohols, R, O and H, this is your negative, this is your positive, no positive. Okay, this is going to release electrons, right? Yeah, this is going to release, correct. Now see, what is the difference? When I speak about water, basically, now when do we call something as acidic in nature? When it releases H plus ions, right? When dissolved in water, when it releases H plus, I can call something, that particular compound as acidic in nature. Now in this particular case, in water, oxygen is attached to hydrogen. Oxygen is attached to hydrogen, correct? Attached to hydrogen, correct? Yes. Now in alcohols, what is oxygen attached to? Oxygen is attached to very important, R. Alkyl groups are electron releasing groups. We already discussed. Alkyl groups are electron releasing, ethyl, butyl, all alkyl groups are electron releasing. More number of alkyl groups, yes, more of electron releasing nature. Cloud density is more. Okay, I'll discuss that. So alkyl group attached to electron releasing groups. So what is ERG? Electron releasing groups. Yes. So when you have electron releasing groups here, what's happening? Here hydrogen is not electron releasing, it's just, you know, positive charge, and oxygen is going to drag that electron density towards itself. Now what happened? Here when it is electron releasing, what happened to the electron cloud? Yes, it keeps on donating electrons to oxygen, correct? Now hence your electron cloud density, here, electron cloud density has become maximum, right? Because this is donating, this also has electrons, so electron density increases around oxygen. So when it increases around oxygen, tell me, does oxygen require electrons from anywhere? Not required. Here though, what happened? Here oxygen, as an electronegative atom, it started dragging electrons from hydrogen, but here it doesn't require any electrons because already alkyl group has given it so many electrons, right? So oxygen now, it doesn't require any electrons, it will not try to pull the electrons, so increases around oxygen, and thus it does not drag electrons from hydrogen. Correct? Yes. Now if it is not dragging electrons from hydrogen, do we get two poles? Do we get two charges? Do we get positive and negative charge? Does it release hydrogen? No, because already this is so many electrons here. There is no difference in electronegativity, or there is no difference in or requirement of electrons. So because of this dense electron cloud here, release of hydrogen atom, this hydrogen atom release is not possible. It means it's very difficult. Very less, very rarely try to release H plus ions unless until you add a stronger metal. Fine. So release of H plus becomes difficult. When release of H plus becomes difficult, now alcohol is less acidic than water, correct? So hence alcohols are less acidic. So what am I comparing in the acidic strength? Remember, alcohols are less acidic than water. Remember, the weak acids, alcohols are weak acids compared to water. This is what is the answer. So I'm done with the preparations of alcohols. Now let us go to the physical properties of alcohols. Right. Basically, when we speak about physical properties, we study under the variations of melting point, boiling point, solubility, density, what is the odor and everything, as we have done in the first chapter. So let us see questions. Now I'll be discussing based on the questions. I'll be giving you the question. Let us answer those questions. Right. So there's one question given in physical properties. The melting point and boiling point of alcohols are much higher than those of corresponding hydrocarbons, corresponding haloalkanes, corresponding ethers. Right? Why? So they've given us why is the boiling point higher. The alkanes are 111, so this is higher. This is the maximum boiling point. Why? So simple reason. Whenever they're asking you about a question about boiling point, remember, this is an important clue. You have to speak in terms of three terms, right? Or speak use these three terms because those are the keywords which are there in the board marking scheme. First, whenever boiling point question is given to you, either speak in terms of branching if the question is related to branching. If you otherwise, if you don't have, speak in terms of hydrogen bonding. Hydrogen bonding, higher, the boiling point will be higher. Or you can also speak in terms of number of carbon atoms. Number of carbon atoms. Right. Simple. Boiling point and branching. Remember, I'm writing something here. Boiling point is inversely proportional to branching. First point. Boiling point is directly proportional to hydrogen bonding. Remember, boiling point is directly proportional to number of carbon atoms. Remember this. A very important question. topic, right? Let us come back and see this question. Now they've given me this question, I have to answer. I'm going to remember these criteria. So which criteria will work in this question? Hydrogen bonding criteria will work in this question. So take this alcohol. So instead of C2H5, I let R, O and H. Fine, not a problem. So this O forms a hydrogen bonding, correct? Now this becomes a partial negative charge, this becomes a partial positive charge. Now because of this hydrogen bonding, alcohols, or because of strong hydrogen bonding, alcohols possess higher BP and MP compared to others. Remember this please, because if you remember these keywords, it's very easy for you to write any sort of answer given to you based on boiling point. Please note it. So let us do one more question on boiling point. But remember, whenever you're doing boiling point questions, you have to remember three important things. One, boiling point is directly proportional to hydrogen bonding. Boiling point is directly proportional to number of carbon atoms. Boiling point is inversely proportional to branching. Let us read this question. They've given me, compared to 2-methyl, 2-propanol and 1-butanol, which possess higher boiling point. Why? There is no data given to me. They have not given me any Kelvin, any temperature. So let me write the structure and see. So I have 1-butanol. 1, 2, 3, 4 OH. CH3, CH2, CH2, CH2. I have to write 2-methyl, 2-propanol now, right? Prop 1, 2, 3. Okay, prop, right? So this is your first carbon, second carbon. In the second carbon, I have my methyl group. In the second carbon, I have OH. So 3 and this is 3. So this is 1-butanol. And this is your 2-methyl, 2-propanol. Okay, now they are asking you among these two which will have which possess higher boiling point. I will say this possesses higher boiling point. Why? What is the reason? Okay, let us write the reason. I already said, what did I say? Boiling point is inversely proportional to branching. Correct? Why? What is happening in this molecule? This is not branched, this is branched. What is happening in this molecule? First important thing, what type of forces are acting on this molecule? Weak dispersion forces, right? So first important thing, forces acting are dispersion forces, right? Weak dispersion forces. Okay, if I speak in like simple language, the intermolecular forces of attraction is very, very low. Here this is linked to this, 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 but here all are branched. You know, this is not linked to this. Like carbon atom, fine, but the distance between this and this is more, this and this is more, this and this is more. So I should write weak intermolecular forces of attraction. Weak intermolecular forces of attraction. Done. When the forces of attraction are very weak, should I use more boiling point or should I use less boiling point? I have to use with less BP. We can break the bond. Bonds can be broken. That is simple. You'll just write the compound, write this reason, write the dispersion forces, so weak forces. So automatically when this is weak, I can easily break, and with less temperature, I can break. So this is your answer. So we have learned the mechanism for Reimer-Tiemann reaction. So we have done two named reactions. One is Lieberman's test, that is a confirmatory test for phenol. Next is a Reimer-Tiemann reaction where I prepared salicylaldehyde from phenol. Please learn the mechanism, because if you learn the mechanism, even if you're forgetting the final product, but deriving the mechanism, you can at least finally reach to the required product which the examiner expects from you. So let us come back and do one more named reaction, that is Kolb's reaction. Kolb's reaction, yes. Basically, Kolb's reaction, as I said earlier, it is a conversion or the conversion of phenol in the presence of a base, sodium hydroxide and carbon dioxide, to form, look here, I will give two names for this. This is called salicylic acid, which is the starting raw material for preparation of aspirin tablets, or it is also called orthohydroxybenzoic acid. Orthohydroxybenzoic acid. Okay, let us start the mechanism. Basically, when I speak about Kolb's reaction, first important requirement is you are going to take phenol, yes, and thus phenol, as we know, the stable form, phenoxide ion, yes, why? Because it shows more number of resonating structures. To this phenoxide, now let me write this also, phenoxide ion, right? To this phenoxide ion, this, and one more thing you have to remember, it occurs at 135 degree atmospheres, 4 to 7 atmospheric pressure, right? Yes. Why did I give this? Because in the exam, if they're not giving you Kolb's reaction directly, suppose if they're giving you these temperature and pressure conditions and they're giving you one of the reagent, you should be able to write the reactant and able to write the product. So remember these reaction conditions, very important for Kolb's reaction. So phenoxide. Now to this phenoxide, why did I take phenoxide? More number of resonating structures and more stable. To this, your sodium hydroxide is going to come in attack. So what do I get? Yes, I get sodium phenoxide. Yes, sodium phenoxide. So this, yeah, this is your. Let me write this name also. This is sodium phenoxide ion. Now, this your carbon dioxide. Now the role of carbon dioxide starts from here. Your carbon dioxide, a C double bond O and C double bond O, correct? Right. This is highly electronegative and this is also highly electronegative. This is going to drag the electron density. When it's dragging the electron density, this gets a negative charge and this gets a positive charge. Now what happens when I take this particular sodium phenoxide? There is a bond here, isn't it? Yes. So this carbon dioxide, just see, I'll write the same thing here. O double bond O, C plus and your O minus. This is dragged by this. Now, this bond is, because this is deficient now, this bond is shared with this carbon. When this particular bond is shared by this carbon, how does that phenoxide look like? It is like this, your sodium phenoxide, done. This pi bond is still existing, this pi bond is still existing. Now, I said there is existence of this is C6, carbon everywhere and hydrogen also. So, the hydrogen of that is position here and this is already shared with this carbon dioxide. Now carbon, so COO minus, done. Now let us come back and see. Now there's a problem. This hydrogen should be shared with COO minus or with this phenoxide. That is the main thing you should remember. What factor should I remember here? Observe, when I compare your carboxylic acid and when I compare your phenol, carboxylic acids are stronger acids compared to phenol. So this is a weak acid. Yes, point number one. If I take the ionic form of carboxylic acid, if this is a strong acid, this is a weak base. Yes. If I take the ionic form of this phenoxide ion, if this is a weak acid, this is a strong base. Simple. Yeah. Now observe, Now, when there's a competition between a carboxylate ion and a phenoxide ion, the H plus or the hydrogen is going to shift towards the strong base. This is what we have learned. So the H plus goes and joins towards the strong base. Fine. Yeah. So let us see that. What do I get? If you want this you want to show this shift like this, you can directly cleave it here and show that shift. So if you don't want sodium also, not a problem, you can just always make O minus and show that, and this is your COO minus. Correct. Now how did I get this bond here? This H has shifted to this direction and this has dropped in, COO minus. Now to this particular thing, this H plus will go and attack. And what do I get? I get the final salicylic acid. COOH, this is our salicylic acid. Salicylic acid. As I said, it is a raw material for preparation of aspirin. Let us come back and see. In Kolb's reaction, how do I write the definition? Kolb's reaction is basically the conversion of phenol to orthohydroxybenzoic acid or salicylic acid. So these are the reaction conditions. So first important thing, formation of your phenoxide ion. Not a problem if you're not picking this also. From here you can use this and finally convert this into salicylic acid. Once phenoxide ion is formed, you're going to pick up the carbon dioxide and show the position or attack at the ortho. Here there is a competition of H plus, either should it be donated to COO minus or should it be donated to phenoxide. So we very well know phenoxide is a strong base conjugate. So automatically that H plus goes to phenoxide, and further on acidification, this particular, or I'll write here acidification. And further acidification, COO minus gets converted to carboxylic ion. So carboxylic acid. So final product is this. So this is your Kolb's reaction. Please note the mechanism. Yes, so let us do the chemical reactions of alcohols chapter. So let us go with the first reaction, that is reaction where you're going to see the rupture of RO and H bond. ROH we've already taken. I already said you have reactions between R and O and H, reactions between C and O. So let us start with the first reaction. So I've listed out certain reactions which will only involve replacement of this H plus ion. So let's see. The first reaction, when I go with this, so instead of R, let me take one alcohol. Any alcohol will do, right? Then I picked up this metal. Okay, this is a reaction where you have done in your grade 10th class. That is, you have taken a piece of sodium metal, you have dropped in sodium metal in an acid. Then immediately you have seen the liberation of hydrogen gas. So this is also the same type of reaction. Let's see what's going to happen. So here, let me take 2 moles of the metal, right? To this particular alcohol, also I'm going to take 2 moles. Let me tell you why have I taken this. Now, I said there is a rupture at this particular point, O and H. So your Na will go and replace this. So what do I get now? C2H5ONA. So it is 2 because I've taken 2 moles here also 2 done. So now what else is left out? Now hydrogen, 2 hydrogens, that is H2 gas is liberated. So observe carefully what happened. Whenever I have taken an alcohol, whenever I have dropped in a metal, I have got, what is this called? This is called sodium ethoxide. Sodium ethoxide and hydrogen gas. Now observe carefully. When you, just now I have mentioned, you have studied in your grade 10, acid plus metal gives us salt plus hydrogen gas. So this particular reaction of alcohol with metals, basically because of the release of hydrogen gas, we call alcohol as acidic in nature. So in the exam they ask you to write a reaction which explains the acidic nature of alcohol. You can use this reaction because we very well know acid. So here alcohol is acting as an acid. I've dropped in metal into this. Once I've dropped in metal, hydrogen gas was released, right? So because of this, I can show, or this can be used as a reference for proving alcohol as an acidic acidic in nature, right? So this is one reaction. So let us go to one more reaction and see. Now I picked up the second reaction. Just see. Now I've taken C2H5OH alcohol. This is our alcohol. I've picked up an acid, acetic acid. Let us take CH3COOH. I'm just written the reverse. Nothing. Simple. Now a reaction between an alcohol and an acid. Yeah, okay, fine. Now such reactions are always reversible in nature. Why? Let me complete this and I'll come back to you. Come back to this particular reaction. So this particular reaction is reversible, I said. Okay. Now I'm going to add something called concentrated sulfuric acid. Very important. Concentrated sulfuric acid's role here is to dehydrate the reaction, right? Yes, concentrated sulfuric acid is basically a dehydrating agent. Dehydrating means removal of water. So whenever you find concentrated sulfuric acid in the reaction, that means you have to take out water, H from the other side and OH from the other molecule. So now where is the alcohol where is the rupture here, right? So take this, draw and pick out this water. Fine. So what do I get? I am going to get water here. So what else is left? C2H5O, C2H5O and the leftover OCCH3. Yes. So what am I getting now? I am getting an ester plus water. So now see this reaction. The reaction where an acid, when an alcohol or when an acid is added to an alcohol in the presence of a dehydrating agent like sulfuric acid concentrated, we get ester plus water. Such reactions are called esterification reactions. Remember, this reaction is called esterification reaction. Esterification reaction. Now, so if they can directly ask esterification, fine, not a problem. You can just take an acid, take an alcohol, add that concentrated sulfuric acid. So as I said, this is acting as dehydrating agent, removing water. You get an ester plus water. Now, what else? What sort of question is asked other than this? They may ask you, what is the role of concentrated sulfuric acid? So, what is the role? Or why should it be added? Yeah, I'll tell you. Concentrated sulfuric acid, I said it is dehydrating. Now what happens is, if this reaction or if I don't add concentrated sulfuric acid here, as I said, these reactions are reversible in nature. Once this product is formed, it tends to form the back products also. See, ester will again get converted to acid and alcohol. To prevent that, basically we want formation of esters. To form esters in the forward direction, we'll add concentrated sulfuric acid. If I don't add sulfuric acid concentrated, again I'll get back the reactants. So what is the role means? Basically to prevent reversible reaction, to acid and alcohol. This is what you're going to write. Yes, to prevent the backward reaction, you're going to add sulfuric acid. That's it. So this is esterification reaction. This is reaction with metal. So note this. I'll come back to next two reactions. Yes. So I'm done with the first two reactions. I've learned esterification. I've learned reaction with metals. Now I have to learn something else called reaction with CH3Cl. What is that? Let me see. I'm going, this is done. This is done. I'm going with this reaction. CH3CH2OH. Okay. Right. Ethanol. Now I'm going to add, this is called acetyl chloride. How am I writing? I'm writing Cl here. I'm writing COCH3. What is this name? Acetyl chloride. Why? Because I've got it from acetic acid. CH3COOH, right? OH nucleophile was replaced by Cl nucleophile. Acetyl chloride. Now what do? A cleavage occurs here at this particular point and HCl is liberated. So what do I get? I get HCl. Correct, right? CH3CO, CH3, CH2OO, that is COOCH3. Correct. Again an ester, right? How do I name this? Ethyl ethanoate, because two carbons, ethyl ethanoate. Ethanoate. Such reactions where an alcohol, when it combines with acetyl group, if you get an ethanoate, such reactions are called acetylation reactions. So what is it called? Acetylation reactions are those in which you are adding acetyl group to alcohol where the rupture occurs at H bond. So acetylation, formation of ethyl ethanoate. So observe carefully, every time I am trying to cleave this bond here, this is H plus, this is Cl minus is replacing that. Simple as that. Now let me pick up next reaction. What is the next reaction here? I have a compound here. Let me write this first. C2H5OH. Okay, so I'm taking this alcohol. If you don't want, if you're getting confused with writing this, you're going to write CH3CH2OH. Not a problem. Yes. Now pick up this. Now what is this compound? CH3COCOOCH3. Now observe carefully. If I close this here, what is it called? CH3COOH, acetic acid, correct? Now observe, I'll write this compound here. This, how did I get this? I took CH3COOH, again I took one more mole of CH3COOH, okay? What did I take out? I took out water from this. If I take out water, what am I left with? CH3COO, CH3COO, CH3, now this is, okay, this is correct, CH3CO. Just see, this is also there here, this is also there, this. So that is why we are getting, what are we getting? We are getting a compound by dehydrating acetic acid. So that's why it is called acetic anhydride. Anhydride means without water. So this compound is called acetic anhydride. So I'm writing this as acetic anhydride. An means without. So acetic acid is the parent atom. So now what happens is, where is the rupture occurring? So here you have to cleave the bond here. Now exactly. Just see, you can just take, either you can break the bond here or you can break the bond here. Not a problem. Yes, because both the sides are similar. You can just break the bond here and here. Now basically this is plus, this is minus, which is what we have seen. Now just observe carefully. CH3CH2COO. Now I have to cleave this bond here. Now observe carefully. So this is your this will go with the first one. Yeah, what do I get? Now whole thing, CH3CH2 COO CH3, right? Okay, now what did I do? Instead of cleaving it here, I took it here, so that now already O I have cleaved it. So CH3CH2 COO CH3. What is left out now? We am left with acetic acid. This acetic acid and this one will combine. What do I get? I get this acetic acid. Now observe carefully. Let me write this. Alcohol plus acetic anhydride. Take this bond, both are similar. Basically, you will get an ester plus acid. How did I get this? Here I have to cleave H plus, that is the reaction rupture of H plus. Now you have this bond, take your pen and just cleave the bond here above oxygen. You can cleave it down also, but here because I've cleaved it already here, I've cleaved it above. Now pick up CH3CH2, CH3CH2, COO. Ester CH3 CO. This is also again called ethyl ethanoate and acetic acid. Acetic acid. So this reaction where there is a rupture of acetic anhydride, right? So you again get, just like acetylation, acetic anhydride also, you get an ethanoate structure. So those two are the reactions. So note it. Let me come back to one more reaction. Yes, so let us do one last reaction with RMGX. Now I'm picking up CH3, your alcohol, right? Now we very well know RMGX is a Grignard's reagent. So instead of RMGX, let me take one more, C2H5MGX, not a problem, right? Fine. Now Grignard's reagent always forms addition products. Now observe in this case, what is going to happen is, as I said, there is a rupture of bond here, OH. Now your C2H5 gets added to this. Observe carefully. You get an, okay, what is C2H6? 1 2 CH3 CH3. You get an ethane. Remember, conversion of alcohol to alkanes. This is one conversion. Now what else is left out? You have your MgX. Now there is a rupture here. This is your positive charge, this is your negative charge. Your Mg is broken up and it forms, the whole thing comes out, adds as C2H5 and your X. So observe carefully. Whenever you are adding Grignard's reagent, as I said, in aldehydes, ketones, you will be getting alcohols. But here, from alcohol, again, you will not get alcohol. Remember that. So in Grignard's reagent, very important. This can be used as conversion of ethanol to ethane. You can use this reaction as a conversion. So Grignard's reagent, basically it will break up into your positive and negative charges, and you will be getting, now when this is negative, it will pick up positive charge. When this is positive, it will pick up the negative charge, and finally you will get an alkane. Just note it. So we've already done reactions based on the rupture of oxygen and hydrogen, where we have seen the release of hydrogen gas. So we have seen reaction with metal, acetic anhydride, acetyl chloride, esterification reactions. So let us see now what happens when there is a cleavage between carbon and oxygen bond. Earlier there was a cleavage here. Now I'm going to show the reactions where the nucleophile OH minus is replaced every time with the incoming nucleophile. So let us see. Now Lucas test. I think you all remember in haloalkanes, haloarenes chapter, these were the same reactions which we did with alcohols. So I'm going to just repeat it once again so that it is a complete revision of that particular topic. So I'm going first with the Lucas test. So Lucas test basically is used to convert alcohols to haloalkanes. Correct? This is what we have done. So I'm going to pick up alcohol. So when is this converted? Under which condition? You require anhydrous zinc chloride. This is the basic requirement. You need to maintain the anhydrous conditions. Then only the water, you'll get water as a byproduct, and finally prepare your RX. So first one. So I'm going to take or test with primary alcohol, secondary alcohol and tertiary alcohol. So first I'm going to write the primary alcohol. Suppose, right, this is one H. So we very well know primary alcohol is an alcohol where carbon has 1, 2 hydrogens and 1 alkyl group. This is your primary. Secondary alcohol is something where carbon has 2 alkyl groups and 1 hydrogen. Tertiary alcohol is something where carbon has 3 alkyl groups. I am writing the same story again and again. Right. Now, when I am adding this anhydrous ZnCl2 to the reagent, when I am adding this particular thing, along with this, I am going to add HCl to every reaction. Now observe carefully. I said it is going to dehydrate. This is going to take out water from where? Now what are we learning? We are learning reactions of the cleavage of OH bond. Yes, exactly, there is a rupture of the bond here and water molecule comes out. And what am I going to get? I am going to get R, H, and your Cl and your water molecule. Have I not prepared haloalkane? Yes, I did. Now for this particular reaction, what do we get? You will get this, and you get R, your hydrogen with 2 alkyl groups and your Cl plus water. Fine, done. You again have a tertiary alcohol. Now remember, your tertiary alcohol are your 3 alkyl groups which we discussed, and your Cl and H2O. Observe carefully. The primary alcohol, the reaction of primary alcohol is very difficult at room temperature. It is because it is primary carbocation is unstable enough. It's very difficult at room temperature. So I require a catalyst like anhydrous ZnCl2. But for secondary and tertiary alcohols, we can easily perform the reaction at room temperature. That means I can just heat it for 2 or 3 minutes. You will find the turbidity. But for tertiary alcohol, within seconds only, as soon as you add your HCl, immediately it will form the turbidity, that is your haloalkane. So what am I trying to explain you all? In Lucas test, it is a test basically for converting alcohols to haloalkanes. Primary will respond least, tertiary will respond very fast. So how will I write the order? Primary is very less, secondary very less compared to tertiary. This is your order for your alcohols to react with Lucas reagent, that is anhydrous ZnCl2. Yes, fine. Now let me complete and do this reaction with the second one that we have already studied Lucas test. Now let me add hydrogen iodide and see what's going to happen. So whenever you find hydrogen iodide reactions in the exam, remember, now let me write this first, CH3 CH2OH plus HI. Okay, yes. Hydrogen iodide reactions always occur in the presence of red phosphorus. Without red phosphorus, the iodine gas, whatever is there, or the HI, whatever you add, is not released. Remember, so red phosphorus as a catalyst is going to release out the hydrogen gas to this. Now observe carefully this reaction. This is little bit different, but please don't get confused. Such reactions only are asked. Whenever you have hydrogen iodide in the reaction, try to put 2 moles. That's the easiest one. When you put 2 moles, I said HI, which gas is released? Iodine gas is released. So 2 I's will come out as iodine gas. Okay, iodine vapor rather, right? That is done. Now what am I left with? Water molecule H, because the molecule, the bond has to cleave here. Yes, H and OH. Done. So what do I get now? H2O. Water is done. Now what else is there? Yes, your CH3. Now how many HIs are there? 2, right? So let me write that 2 HI in this way. See whether you can understand or not. HI and HI. Okay, so what happened now? During this reaction, iodine has come out as iodine vapors. Water, H2O has come out as water. What is left now? CH3, CH2 and H. What is that now? C2H6. Now understand, very important reaction. Whenever, again I'm stressing it, whenever you find an alcohol and when you are adding HI to that, you require red phosphorus as a catalyst. What does it do? It helps us to release out the iodine gas. That's fine. But as soon as such reactions are given to you, try to put 2 moles. Why am I telling that? Because for you to get the byproducts is easy. Right? Iodine comes out as iodine vapor. If I take 1 mole, you will get a confusion. You will get into confusion. Okay, what should I do? No, just take 2 moles. You'll get iodine, and leftover water is already out, and you'll get alkane. Now, what sort of question is this? You can take this as a conversion of alcohols to alkenes. Remember this conversion. Alcohols to alkenes can be done with HI. I'll be doing conversions where I'll be using HI in the presence of red phosphorus. So use it or take it as an important reaction. Put a star in your book so that you will not skip out in your exam. Yes, fine. This is done. So I've done with this. I have done with this. Let me do PCl3, which we have already done in the first chapter. So PCl3 is PCl3 or PCl5. Both are phosphorus reactions with phosphorus trihalides, isn't it? Why did I say phosphorus trihalide? 3 chlorides, pentahalide means phosphorus halides. So reaction with phosphorus halides. Right. Now let us see how can I write this reaction. Suppose whenever you take PCl3, again repetition of first chapter, whenever you are taking PCl3, try to pick up 3 moles of PCl3. I already said this, PCl3, try to pick up 3 moles. Okay. When you are taking 3 moles, because why? I'll tell you. Here there is a cleavage of OH bond. When you are taking 3 moles of Cl, this is a nucleophile, this is a nucleophile. When 3 moles are coming and attacking this, OH also should be 3. Logic? Yes. Now, see, easy. These 3 Cls will come and replace this. So, you get C2H5Cl. How many? 3. What else is left now? You still have hydrogen. You still have oxygen. You still have phosphorus. How many should you write? H3PO3. H3PO3. Observe carefully. H3 PO3. Fine. Now, suppose if I am not taking 3 PCLs, right? I am only taking 1. Will that be done? Yes, it will be done. Why? Now see this reaction. This is balanced. This is also balanced. 3 Cls balanced. H3 PO3 balanced. That means whenever you are taking PCl3, try to use 3 moles of ethanol. I started from the other way showing you that PCl3 not required to use 3 moles. You should use 3 moles for ethanol. So that is this. So what is the name of this compound? Phosphoric acid. Now, I am starting with the next reaction, PCl5. So, let us start. So, again, alcohol, there should be a cleavage here, or the rupture of the bond should be at OH position. I am going to add PCl5. I told you in the first chapter, whenever I am taking PCl5 phosphorus pentahalide, you can divide this like this. P, write it like this, Cl, 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 Cl and Cl. Yes, not a problem. Yeah. Now, see. I have to prepare alkyl halide. The first ethyl group comes out with this. So what do I get? C2H5Cl. That's done. Fine. Now replacement is done perfectly. Now what else do I have? I have your phosphorus, I have chlorine and this. Now just see. Your H and Cl comes out as HCl. That is also done perfect. Now what else am I left with? I am left with phosphorus. I am left with oxygen, chlorine. POCl3. Phosphoxychloride. Phosphorus oxychloride. Not a problem. Phosphorus oxychloride. Yes, you can write that reaction. So here for PCl3 you will get phosphoric acid. For PCl5 you will get phosphorus oxychloride. Now I am doing with this last reaction as we have done earlier. This is called thionyl chloride. Remember, thio means sulfur. Thionyl chloride this is the most, I already said, this is the most economical reaction. That means whatever reactant or whatever haloalkane you are preparing, if the question asked us, why is thionyl chloride the preferred preparation for haloalkanes? I'll write the reaction, you will be able to answer, just see. Now, I have taken C2H5OH, ethanol. Now, I'm going to add thionyl chloride to this, SOCl2. Now, what happens is, when thionyl chloride is added, first important thing, where should we cleave the bond? Yes, this is the site of cleavage. Correct? Yeah. Sulfur oxide in this one and this one comes out of that as sulfur dioxide gas. First sulfur dioxide gas vaporizes out. It comes out. Once sulfur dioxide gas comes out, what else is left? Your hydrogen and chlorine. Your HCl. Now, that also comes out as vapor. HCl vapors. Now what else is left? You are left with C2H5Cl, because one Cl has gone with HCl and you're left with C2H5Cl, which is the purest form. So now my question, back to the question, why is thionyl chloride used as an economical product for preparation of haloalkane? Answer is, in this reaction, both are gaseous products. When both are gaseous products, the haloalkane which is obtained as the purest form. You don't have any impurities in that reaction. So I can directly use this haloalkane for further reactions. Yes. So in earlier case, do we have any gaseous products? No. So this is your reaction. So this is what? 3, 4, 5. So these are the reactions involving COOH bond. I'll meet you again with reactions involving the electrons of oxygen. So we've already started with the name reactions of phenols. We have done one Lieberman's test, where I said it is a confirmatory test for phenol. So let us come back and do the remaining name reactions. With this, your phenol chapter would be completed. Then we'll start with the ether chapter. So in phenols, as I said, the test which I discussed was Lieberman's test. So now I'll be discussing about an important reaction of phenols, that is your Reimer-Tiemann reaction. Very important. So let us write down, Reimer-Tiemann reaction. Right. So along with this Reimer-Tiemann reaction, I'll also give a clue about Gattermann reaction, just remember, or Kolb's also. Okay, so I'll just remember this clue in Kolb's reaction and Reimer-Tiemann reaction. In Reimer-Tiemann reaction, you will basically find phenol getting converted into salicylaldehyde. This is your first important thing which you have to remember. In Kolb's reaction, your phenol gets converted into salicylic acid. That is the only difference, but the mechanisms are that is only similarity, and mechanisms are completely different. So let us see. Remember, Reimer-Tiemann, you have to get the final product as salicylaldehyde, and your Kolb's, the final product should be salicylic acid. So let us start with the first reaction. Now, whenever Reimer-Tiemann reaction is given to you, the first most important, or the examiner is going to observe about three important things: whether you have taken the raw material as phenol or not, point number one; whether you have maintained or taken chloroform, because this is the most important thing; whether you have picked up sodium hydroxide or not, that's important. And apart from this, the whole reaction, whatever I'm going to do, what I'm going to show, please go through it step by step, so that not even a single charge is missed out. Fine. Under these conditions, your phenol is going to get converted into a compound called salicylaldehyde. So salicylaldehyde. Yes. So let us start with the mechanism. So first important thing, when you go with your Reimer-Tiemann reaction, when I speak about the step 1, first most important thing is your chloroform and your base. So reaction with your chloroform and your base. So remember, reaction, how does this look? First important thing, your chloroform CHCl3. So what is this now? Chloroform. This chloroform, when it's reacting with your base, so instead of this, I'm going to pick up your OH minus. Now observe carefully, your OH and your H comes out as water. What else is left now? You're left with CCl3. So CCl3. Yes, now remember. Now what is this? CCl3 from here gradually breaks up into, just see, C is still here, Cl2, yes, plus Cl minus, right? Now this is with a lone pair of electron. Now this is important for us. This is called dichlorocarbene. This is our electrophile now. So what did I do? I picked up chloroform. In the presence of a base, it's getting converted into CCl3. So further, when this decomposes, it decomposes into two elements. One, this is called dichlorocarbene, remember. So this dichlorocarbene, and this is chloride anion. So what is the difference now? This dichlorocarbene acts as an electrophile for us. This is going to perform the whole reaction. This is where it's going to join the ortho position and show. So this is your step 1. Please note it. I'll come back to step 2. Yes. Now I've already got CCl2. Let us go back to step 2 and see what's going to happen in this. Now in our step 2, what did I say? We have our dichlorocarbene, that's an electrophile. Now I'm going to pick up phenol, right? Fine. This phenol, as we know, the stable form is phenoxide, correct? Right. One, yes. This phenoxide, your dichlorocarbene, which is acting as electrophile, is going to come and attack this point. So you can either write in this way, or you can, not a problem, any direction resonance. First important thing, oxygen is going to drop in the charge. So how does this look now? You have double bond oxygen Yes, you still have this bond, you still have this bond, you still have this bond. This is CCl2. Double bond and double bond can't be together. Yes. So your double bond and double bond can't be together. So what happens? This particular bond is shared with this. How does this look now? This has become your double bond O. This bond is still existing here. This is also existing here. And this is opened up and shared with this. Fine. So now the hydrogen which was here also comes out, and we are going to show this H and your carbon, Cl and Cl. Done. There's still a lone pair of electron with carbon here, so this is minus. Observe carefully. Now from this particular reaction, the negative charge of this minus is donated to this hydrogen. So this bond shifts here, and we very well know double and double can't be together, so your oxygen, this double bond shifts here. So how does this look now? This looks like single bond O minus. Your bond has already reached, and you're left with CHCl2. Done. Now we are almost coming closer to the final product. Now this whole compound, right? Basically this is transition state, means a bit intermediate state for a few seconds. And from this compound, now I'm going to introduce sodium hydroxide. How many moles? 2. There's a cleavage or the formation of a cation and anion. This is your nucleophile. This is also a nucleophile. So there is exchange of this nucleophile with this chlorine. So what do we get now? We get O minus, all pi bonds, and your CHOH taken twice. How did I get twice? Because there are 2 chlorines, so I have replaced this with 2 OHs. This is, now we've got. Now we are going to dehydrate it here, taking out water. So what do we have here? CHO H2. So oxygen is also 2, hydrogen is also 2. So what am I doing now? I'm going to take 2H and 1 O. So what is left now? I'm subtracting minus H2O here. If I'm taking out 2H and 1 O, I'm be left with only 1 oxygen. So it is like this. Your oxygen minus 1 minus and your CHO. So what am I trying to explain here? Just see, it is CH, it is OH and OH, correct? Now what did I do? I dehydrated it, I took out water. So the leftover is CHO. Now you're introducing H plus. This H plus goes and attacks this. So finally we have made salicylaldehyde with, or salicylaldehyde from phenol using chloroform. So the main aim or the main role of chloroform is to supply or to form this compound. The main important thing which I have done in step 1, that is formation of the electrophile, that is dichlorocarbene, is initiated by chloroform. So if a reasoning question is asked, what is the role of chloroform in this Reimer-Tiemann reaction, you have to specifically say the release of electrophile or dichlorocarbene. Yes, that is going to initiate the whole reaction. So please note it, this is salicylate. This is your Reimer-Tiemann reaction. So we have done the name reactions. Let us come back to the next class of name reactions. We are almost end of the chapter. So oxidation and reduction of phenols. So basically whenever we speak about oxidation, right, it's addition of oxygen or removal of hydrogen. For that we need basic oxidizing agents. I already said phenol is highly, or it's a strong electron releasing group, but not more than that, more than oxide, phenoxide, but it is a strong electron releasing group. So for that to get oxidized, I require a stronger oxidizing agents like, let us see. So whenever you're finding oxidation of phenol, I'm going to use stronger oxidizing agents like sodium chromate. What is sodium chromate? Na2Cr2O7 in acidified medium. Yes, this is going to act as an oxidizing agent for us. This sodium chromate, whenever you find in the paper sodium chromate or potassium permanganate or potassium dichromates, you remember those are all oxidizing agents. You're supposed to add oxygen to the particular reactant given to you. So this is an oxidizing agent. Now what will it do? It's going to add oxygen and remove hydrogen. Yes, that is what is oxidizing agent work. So how does this look now? It forms a product called benzoquinone. Right, benzoquinone. What are benzoquinones? Benzoquinones are used as an oxidizing agents in chemistry. Wherever we have, it's the same like this. Whenever we require some oxidation process, I use it as an oxidizing agents. Yes. Now, mostly when I find quinones are used in most of the transfer reactions like photosynthesis. When you have photosynthesis reactions, quinones come into picture. These quinones are used as you find them in the transport chain, quinones, and you also find quinones in, you know, whenever you have a transport mechanism basically in living organisms. So you biology students will be using this quinones. So when I'm doing a reasoning question, I'll give you 3 reasoning questions on this, where I'll describe about how is it used in blood clotting. That question also will be covered in that. How are quinones used in the photosynthesis mechanisms? So let us come back. Now this benzoquinone, further, if I am adding excess of phenol to this, excess of phenol, how does this form? Now I am adding this phenol to this benzoquinone. I get a product called phenoquinone. How is that formed? Just see, phenoquinone. What is benzoquinone? Benzoquinone is the O double bond O and double bond O. Just see phenoquinone, easy. Just write your phenol ring. Yeah, this is OH, correct? Now write your benzoquinone in this way. Double bond O, double bond O. So you have 2 bonds, isn't it? Above and below. On the other side, why am I taking 2 phenol rings? Because I'm adding excess and I have to show that hydrogen bonding. Yes. Now observe, this is forming, this is linked. This is also forming. I'm just drawing this link. So there's no space here, so I'll make it a bit dot H. Yes, this compound is called phenoquinone. Phenyl rings, quinone. This is your oxidation. So in oxidation reactions, basically 2 requirements. One is oxidizing agents. Second, addition of oxygen. Third, further conversion, you finally get the product that is phenoquinone. Let us come back and see reduction. So what is reduction? Basically, it is addition of hydrogen or removal of oxygen, correct? So for that also I need reducing agents. Here I used oxidizing agents. So here I need reducing agents. So I'll pick up phenol. I'm going to use reducing agents, as I told you once. Nickel, you can use nickel, you can use platinum, you can use palladium. Yes, I'm going to use nickel catalyst here. Nickel is a catalyst. Yes. Now I said reduction means addition of hydrogen. I'm going to add hydrogen. Now according to this, we very well know there are alternate pi bonds. When this is added to this whole structure, yes, 6 bonds satisfied, you get cyclohexanol. Cyclo compounds, because you have already added hydrogens. These are 6. So cyclohexanol, this opens up and adds at each point, and finally we get cyclohexanol. So reduction reactions, they produce cyclohexanols. Oxidation reactions produce quinones and phenoquinones, or benzoquinones and phenoquinones. So this is the last reaction of the phenol chapter. There's one reaction called Gattermann reaction, where I'll be teaching along with the aldehyde chapter, because Gattermann-Koch reaction, I wanted to show you that difference while writing the reaction. So let us complete the phenol chapter with this reaction, that is coupling reaction. So So when I speak about coupling reaction, you'll be seeing the same coupling in aniline chapter also, so amines chapter. So coupling is basically you're going to couple two compounds. So what are they? I'm going to pick up one compound called BDC. This is what we did earlier. BDC stands for benzene. This is benzene. Nitrogen means azonium chloride. Benzene diazonium chloride. So benzene diazonium chloride, the other name given is BDC. Yes. To this BDC, I am going to couple phenol. Yes. Now observe, there is one hydrogen here. Here you can write X also, not a problem. So during coupling, your HCl is out. What do I get? I get HCl out. Now try to couple these two together. One ring here, this one. There's one more phenol ring here. There is OH, and these two are linked with azo group. This is called your coupling reaction, where you're coupled two rings. One is BDC and phenol, and this is name of this compound para-hydroxy azobenzene. Yes, this whole thing is performed in ice cold solution, ice cold alkaline solution. So this is your coupling reaction. I'll be showing you one more coupling in amines chapter, anilines chapter. So I'm done with the phenol chapter. I'll be doing ethers again in the next video with ethers. Then I'll start with the reasoning questions. Maybe that will be a bit mind twisting. So let us meet again with the ethers chapter. Preparation of phenol from, just look here, salicylic, okay, if I take salicylic acid, okay, fine. Now take, what is salicylic acid? Basically, your salicylic acid is used for, removal of dandruff, itchiness, or, dryness, psoriasis, all these skin related problems. So that salicylic acid formula is this. Just observe, benzene ring with COOH and OH. This is salicylic acid. So salicylic acid. To this salicylic acid, if I am introducing sodium hydroxide, observe carefully, this H and this OH just comes out. So I get minus water. So what do I get? Now I get OH and COONA. Now what happened? This particular thing here, this is a cleavage, so you get COONA. Now what is the COONA? Sodium salicylate. It is called sodium salicylate. Okay, done. Now to this sodium salicylate, if I am introducing soda lime, so what am I doing? I am going to add again sodium hydroxide in the presence of soda lime, NaOH and CO. I've already done a video what is regarding this soda lime, what is the role of calcium oxide in that, what is the role of NaOH in that. Please go to the video, reaction or decarboxylation reaction, that was decarboxylation haloalkanes, haloarenes. So when introduce this one into this, first Na2CO3 sodium carbonate is out, Na2CO3 is out. Yeah, so now what happened to Na2CO3? That's just out, fine. And now observe, this sodium, whatever is there, it goes and forms a sodium phenoxide ion. Sodium phenoxide. As usual, we very well know when sodium phenoxide is formed, I have to do the acidification reaction. Means I have to add HCl to this. When I add HCl, NaCl, this comes out and we get OH and NaCl. Now, this is how you're going to prepare. So, please check again. Now, this is your salicylic acid, right? Salicylic acid, you're introducing a base. Then it converts into sodium salt of salicylic acid or sodium salicylate, right? Now, this particular sodium salicylate, I'm introducing soda lime or sodium hydroxide with a mixture of calcium oxide, that is soda lime. Once you introduce your sodium carbonate is out, and the leftover forms sodium phenoxide. Yes, so this sodium phenoxide on acidification forms phenol and your NaCl. So please go through the reaction. And I'm done with the preparations of phenols. So yes, so now I'll be starting with the chemical properties of phenols, which will include reactions of the cleavage of OH bond as well as benzene rings. So let us meet again in the next class. So students, welcome back to one more session of the alcohols chapter. We've already completed the alcohols chapter. I've done the preparations, I have done the chemical properties, I have also done the name reactions. So gradually I'll be going into the phenols topic. So phenols, after phenols, we'll be doing the ethers chapter, like the ethers topic. Once I'm done with alcohols, phenols and ethers, I'll be doing a list of 20 to 25 reasoning questions. So please go through all the reasoning questions. So what I've observed in the videos are when I'm giving you a list or when I'm preparing a playlist of all the videos, you are just watching. Maybe I've seen students going through the videos where basic reactions. Please don't do that. Every topic or whatever video is uploaded to you, everything is important for your exam. We never know from which corner of the reaction is given to you. So please go through the videos. Mechanisms are important in organic chemistry. Reactions are important. Reasoning questions are important. Basically, my target is to hit that 70 out of 70. So please go through all the videos on regular basis. Fine. So let us start with the phenols chapter. So when I speak about phenols topic, right, we very well know phenols represented by the aromatic ring benzene with OH. Correct? Yes. Now, in this phenols, you have preparations, you have chemical properties also. Basically, when I look into the phenols chapter, phenols you will study under preparations of phenols. You will be studying reactions involving the cleavage of OH bond. Reactions involving cleavage of OH bond. And you will be studying reactions involving only benzene ring. Reactions involving benzene ring. Yes. So when I look into the topic, now let us start with the first preparations. So first, when I speak about preparations of phenols, so remember, what I did is you have different preparations of phenols. So what I did, I picked up the common things. So that means I have taken the starting raw material as benzene, and from benzene I am going to prepare phenols in different ways. So understand, this will be also useful for your conversions, right? So basic this is, I picked up benzene as the raw material. So when I pick up benzene, now we are doing preparations of phenols. Preparations of phenols. In this, so what did I do? I picked up benzene. Now from this benzene ring, I'm going to prepare phenols by 4 different ways. Just see what I'm going to do. I'm going to do a process called chlorination, right? I'll do chlorination by step by step, I'll prepare phenol. I'm also going to do a process called sulfonation. I'm also going to do sulfonation of benzene ring. With this sulfonation, by step, I'll be preparing phenols. After that, I'll be taking benzene and I'm going to perform a reaction called nitration. And again, by step by step, I'll be getting the phenol preparation. Finally, I'll be achieving or preparing phenol. And also I'll be taking your propene. Right, I'll be taking propene. To this propene, I'll be introducing a dehydrating agent like phosphoric acid, and I'll be preparing phenol also. And finally, last but not the least, we also have a reaction called decarboxylation of salicylic acid. Decarboxylation of salicylic or sodium salt of salicylic acid. Salicylic acid. Okay, salicylic acid. Yes, salicylic acid. Fine. So this decarboxylation salicylic acid. So I'll be going step by step. So let us come back and do one reaction of the other. But remember, the final product preparation is for phenol. So let us start with the preparations. So this is easy for you to remember during the exams. When you go for your exams, try to prepare this flowchart in your mind. So with that flowchart, when you go for your exam, you can just correlate. Okay, this is the step, then this is the step, then that is the step. So please go prepare the flowchart. I'm asking you to make the flowchart in your brain, not on the paper and just leave it. So make the flowchart in your brain and try to go to the exam, and as soon as any question given on phenol, you can directly do that. So let us start. So I'm going to start with the first one. So now I said what is a raw material which I picked up? I picked up benzene as a raw material, right? So now what am I going to do? I'm going to take benzene. Yeah, I'm going to first chlorinate it. Now observe. When I say chlorination reaction, what do I require? There should be some reagent which has to supply the electrophile chlorine to me. Yes, so for this I am going to take AlCl3, or you can also take FeCl3, not a problem, right? So thus the electrophile here provided is Cl+, correct? Yes, you've done in your grade 11, Cl+. Now this Cl+ will go and attack this benzene ring. So what do I get? I get chlorobenzene. So let us name this. This is chlorobenzene. Correct? Yes. Now this chlorobenzene further. Now remember, whenever you see chlorobenzene in the paper, that means you have to do a name reaction called Dawes process. I've done a video also on this Dawes process. Please go to the video. Chlorobenzene, register. Chlorobenzene means you have to do a name reaction called Dawes. Dawes. D-O-W-S. Dawes process. This is called Dawes process. For Dawes process, the temperature maintained should be 623 Kelvin. 623 Kelvin and 300 atmospheric pressure. So pressure maintained is 10. Under this condition only, you'll get a phenoxide ion. So, and I'm going to fuse with sodium hydroxide. Yes, now observe carefully. So what happens is, your Cl, yes, your Cl and your H will come out as HCl. Okay, done. Now what else is left now? This benzene and your phenoxide ion. So benzene and your sodium phenoxide. So what is this called? Sodium phenoxide ion. Sodium phenoxide. Done. Once the sodium phenoxide ion is prepared, I'm almost close to the reaction. Done. Simple. This is your sodium phenoxide. Now acidification reaction. Now it means you acidify this reaction with HCl. Acidification. When you acidify with HCl, what happens? Your Na and Cl will come out as a salt, and the leftover H plus. Now this is breaking here, this is cleaving here. Minus, plus, plus, minus. Cl and Na will come out as NaCl, and the leftover you get phenol. This is your phenol. So observe carefully. I just did chlorination. Basic. Every time whenever I do phenol preparation, I pick up benzene as a basic raw material. Chlorination, addition of chlorine. Yes, once chlorine is done, as soon as you see, perform the Dawes process. Once Dawes process, these are the conditions. Dawes process is used to convert chlorobenzene to sodium phenoxide. So once you get the sodium phenoxide in the reaction, now work is done. Almost you're close to preparation of phenol. Acidify this means you're neutralizing that reaction. You're not neutralizing, wrong. It is acidification, basically introducing the H plus ions into the reaction. So H plus in goes and salt is out of the reaction. So the Cl is not clear, maybe Cl, sodium chloride. This is how we are going to prepare that particular reaction. Please note it. Yeah, done. Now, after this chlorination, what did I say? And we are going to perform sulfonation reaction, correct? Now, I'm going to erase the whole thing. I'm going to leave that benzene there only because my raw material is benzene. I pick up that benzene and I'm going to perform sulfonation reaction. Yes, observe carefully. Now, what chlorination is done? So, let us write your chlorination of benzene is done. Now I'm going to do sulfonation reaction. Just observe sulfonation. For sulfonation reaction, we require an electrophile which is supplied by the fuming sulfuric acid. Okay, you can write fuming. Okay, fuming sulfuric acid. Instead, oleum. Oleum is H2S2O7. Okay, this is H2S2O7. Fine. But now this H2S2O7 fuming, this is also called fuming sulfuric acid, H2SO4. Okay, yes. Now this H2SO4, how does this break? Now just see, basically H2SO4, when you warm it, it will break up into H2O and SO3, sulfur trioxide. Now this sulfur trioxide is an electrophile. Remember, here this is a sulfur trioxide, this is an electrophile. So this electrophile goes and attacks this benzene ring. So how does this look now? This will open up this benzene and you get a H. So you, with that H, this SO3, you get SO3H. SO3 is electrophile, it will open up this particular H plus and you get SO3H. What is this called? This is called benzene sulfonic acid. Yes, done. Now benzene sulfonic acid is ready. Now what you do, you are going to introduce or fuse it with sodium hydroxide, because basically always remember we try to form a stable phenoxide ion and then finally come back to phenol. So when you fuse it with sodium phenoxide, observe carefully, your water comes out, yeah, and this will go and attack benzene sulfonic acid. So what do I get? I get SO3Na and water is out. Done? Yes. Now name this sodium salt of benzene sulfonic acid. So I'm writing it as sodium salt of benzene sulfonic acid. Okay, sulfonic acid. Done. Now I'm still almost closer. Yes. Now what do I do to take out that SO3 from the ring? I'm going to further introduce excess sodium hydroxide. Further, excess sodium hydroxide means, suppose if I take 2 moles of sodium hydroxide, what do I mean? I'm taking 2 moles. Suppose if this is 2 moles, can I write, so 2 moles means like just to show you all NaOH and NaOH? Yes, simple as that. 2 moles, I'm just trying to show you. Now observe carefully. This NaOH and NaOH, your Na2, now this is Na and your Na. What happened? Yeah, you get Na2SO3 is out. Na2SO3, sodium sulfite is out. Now this is done. Now what else is left? Your H2O is out. Your H2O is out. Now what is a benzene ring now? This benzene ring, you're left out with your sodium phenoxide. Now observe carefully. I'm adding that sodium phenoxide to this. Simple, just like your earlier reaction. Once you get sodium phenoxide, so name this is sodium phenoxide. Now once your sodium phenoxide is done, acidify this H plus HCl. This is breaking here, this is cleaving here, H plus and Cl minus. What do you get? NaCl is out. And what else do you get? You get your phenol. Phenol is done. I've prepared phenol from this. Yeah, so please see again, benzene, sulfonation, introducing your SO3 as an electrophile. This will attack benzene ring and open up the ring and forms benzene sulfonic acid. Now, gradually I have to come up to prepare sodium phenoxide, I have to prepare phenoxide ion. So I'm going to fuse it with sodium hydroxide. As you have seen, water is out and SO3Na is formed. Now we have formed a salt. Now this salt, further when I introduce excess sodium hydroxide, caustic soda, sodium sulfite, as I told you, Na2SO3 is out, water also is out, and finally you get sodium phenoxide. And acidify this with HCl. NaCl is out and phenol is prepared. This is your sulfonation reaction. Let us come back and do one more reaction. We did chlorination, we did sulfonation, now we will do nitration reaction. So I leave this here. I want this benzene ring as a raw material. So I'm going to take out this. Now I'm going to perform a reaction called a nitration. So what did I do now? I took benzene, I did chlorination, I did sulfonation. Now I'm going to do a reaction called nitration. Perform nitration mixture. Yes. When I take benzene, when I say nitration, right? Nitration is a process of performing or adding an electrophile called NO2 plus from nitrating mixture called HNO3 and H2SO4. This is called nitrating mixture. Now, this goes and adds to this benzene ring. When this adds to the benzene ring, then I call this as nitrobenzene. Nitrobenzene. Now, observe carefully. You have nitrogen, you have oxygen. Yes. If I add SnHCl, okay, what is this? SnHCl is a reducing agent. Okay, this is a reducing agent. What does it do? It's going to add H plus to the ring. Observe, oxygen is out, right? 2H. Oxygen is out and this hydrogen goes there and you get NH2. Aniline. Now, aniline is done. I'm almost close. Aniline, observe carefully. Whenever you see, I said whenever you see chlorobenzene, which reaction you should remember? You have to remember Dawes process. Whenever you see aniline, the reaction which you should remember is Sandmeyer's reaction. Very important, Sandmeyer's. So aniline is going to undergo a reaction called Sandmeyer's reaction. Meyer's reaction. So in Sandmeyer's reaction, basically aniline is treated with sodium nitrite and HCl. Okay, sodium nitrite and HCl is a resin at a temperature of 273 Kelvin to 278 Kelvin. Okay, now observe. When I rearrange this, basically this is forming HONO. HONO, we call it as HONO. Now observe. This nitrogen and this nitrogen and your HCl, okay, the reaction mechanism, when we follow a reaction mechanism, but this is not prescribed for your syllabus, but when we do the reaction mechanism, observe, this nitrogen and this Cl together forms a compound called BDC, that is N2Cl. This nitrogen and this Cl, okay, you get a compound called N2Cl. This is called BDC. BDC means benzene diazonium chloride. What is BDC? What is azonium? Okay, benzene means this ring. Di means 2. Azonium means N triple bond N. Right? Again linked with chlorine. So BDC, now once you get BDC, right? Now this is your Sandmeyer's. Starting from here and still not done, BDC reaction. So conversion of aniline to BDC in the presence of sodium nitrite and HCl at a temperature of 273 to 278 Kelvin is called Sandmeyer's reaction. Remember that, please. So BDC, once it's done, just warm the BDC. Okay, once you warm in the presence of water. Now observe carefully. When you're warming this BDC, immediately nitrogen gas escapes out. Okay, yes. Now observe carefully. Your H and Cl is out. What else is left? H and Cl has come out. Nitrogen has escaped because I've warmed it. The leftover AOH goes and attacks. OH goes and attacks. This is your phenol. Done? Yes. So please note it. Very important. Nitration. Electrophile is NO2. Once you see NO2, this is a procedure. You have to nitro to amino. Remember that. Nitration, after that, reducing agent, hydrogen. So oxygen is released and hydrogen is entered. Now once you perform the Sandmeyer's reaction where you get BDC, and once you get BDC, try to warm the reaction. So when you warm it, nitrogen gas escapes out, your HCl comes out and your OH is prepared, phenol is prepared. Yes, am I done with the reaction? Please note it. Yes. So now I'm done with this reaction. Now let us go to one more reaction. Again, I'll erase the whole thing after this. Now what am I going to do? I'm going to introduce, or I'm going to convert. I'm again taking the raw material benzene. Yes. Now observe. To this benzene, what am I going to do? I'm going to introduce an alkene, that is propene. CH3, C, H double bond CH2, propene. Here I am going to introduce H3PO4, which is acting as a dehydrating agent. Means it will remove water. Dehydrating agent. Dehydrating agent. Right. Now you will maintain a temperature of 200 degrees centigrade. Now what happens? At this particular point, this propene will go and add to this benzene ring. Yeah, how does it act? Observe carefully. The bond is broken here. So take that thing. This carbon should be at the center. Methyl on this side. This is single bond. This is CH3. This H is there. This is called cumene. Cumene. What is the other name? Isopropyl group, right? Isopropyl benzene. This is also called isopropyl benzene. Okay, done. Now observe. To this particular thing, I am going to introduce oxygen, almost at 130 degrees centigrade. Now what happens? This oxygen, this is nothing but O and O. This will go and break this and join here at this particular point, at the center carbon. Now how does this look? This looks like, see, now observe, see, the CH3 is still here. This CH3 is also still here. Now these O2 will join as OOH. Now this group where you have O and O linked is called peroxide group. So this is called cumene O group peroxide. Cumene peroxide. Peroxide, O and O both linked together. Now to this cumene peroxide, if I am introducing or if I am adding water, right? Because I need to prepare phenol, right? H plus, right? Now observe, your CH3 CO CH3. So this is your O, CH3 CO CH3. Your acetone is out. Yeah. What do I get? CH3 CO CH3 acetone, and the leftover is phenol. So this is how you're going to prepare. Take the benzene, introduce the propene ring into that with a dehydrating agent. So this is your dehydrating agent. So with this dehydrating agent, dehydrating is removal of water, you'll get cumene peroxide. To that cumene peroxide, if you're introducing 130 degrees oxygen, it will go and bond at this particular point. Yes. Once you are further introducing water in the presence of H plus ion, acidic medium, so what happens? The acetone is out and the leftover is phenol. This is how you're going to prepare. If they're directly asking you, prepare phenol from cumene or prepare phenol from benzene. Anything is the same. You can just go through this mechanism. Yes, done. Yes, so we've already prepared salicylic acid using Kolb's reaction. Now let us see how to convert salicylic acid into aspirin, right? So the other name given for aspirin is 2-acetoxy-benzoic acid. Yes, okay. Let us see how is this formed. It's simple. Now pick up your salicylic acid. Now what is salicylic acid? Your salicylic acid is your OH and your COH. This is your salicylic acid, correct? So to this salicylic acid, you're going to introduce a compound called acetic anhydride. I've been using the same acetic anhydride in previous classes also. So what is acetic anhydride? This is your CH3, CO, O, CO, CH3. Basically, you have taken 2 moles of acetic acid and you have dehydrated one water molecule. I've shown this already. And finally, you've got acetic anhydride. Now, observe. There's a cleavage of the bond as always. Yes. Now, there's a cleavage of the bond here also. Correct? Yes. Now, this whole thing comes and attacks here. So, what am I trying to say? This whole group comes and attaches to the electronegative oxygen atom. And your H plus comes out with this acetic acid. So how does this look now? Let us see. What did I say? Your COOH is still existing there. That is why you call benzoic acid. And now your oxygen is still existing there. What else is left? Now your carbon. Don't write O and O. Wrong. It is O, CO, CH3. Acetoxy. And what else has come out? Acetic acid is out. This is your aspirin tablet. So simple. Take salicylic acid, add acetic anhydride, cleave the bond above oxygen. One comes out as acetic acid and the other is your aspirin tablet. So aspirin, as I've written, 2-acetoxy-benzoic acid. This is a conversion of salicylic acid to aspirin. Yes, in the part B chapter of the alcohols, phenols and arenes, we are going to study about the chemical properties. That is, for alcohols, there are alcohols and phenols, you have common reactions. So for alcohols and phenols, you have two different types of reactions, that is reactions based on cleavage of O and H and reactions based on cleavage of R and O. So basically you will be studying about this combination as well as this combination, and after that for phenol you will be studying electrophilic substitution reactions, electrophilic aromatic substitution reactions because of the benzene ring of phenol. In electrophilic aromatic substitution reactions you will be studying about nitration, halogenation, reactions for Crafts alkylation, acylation too. Apart from this electrophilic aromatic substitution reactions, phenol also undergoes reduction, oxidation reactions, as well as a most famous Reimer-Tiemann reaction, as well as Kolb's electrolytic method. We'll be discussing gradually one after the other. Apart from the physical properties, preparations, chemical properties, I'll also be doing we should also do chemical properties for ethers. That is, ethers basically show electrophilic substitution reactions, so which includes nitration, nitrating mixture, free Crafts alkylation, acylation, as well as halogenation. So apart from all these, this chapter also has many reasoning questions which are based on acidity concept. Acidity, they'll ask you why is this less acidic, why is that other more acidic than that, how is the solubility when it is branched, why is this more stable. So we'll be doing all those. So acidity you can be studied under the topic phenol, acidity of phenol, acidity of alcohol, acidity of phenoxide and acidity of alkoxide. So I'll meet you in the next video with the concepts of alcohols, phenols and ethers. Yes, students. So we've already done with the introduction of alcohols, phenols and ethers. I have directly started, as I indicated in the introduction, we have nomenclature, classification. After that, we have physical properties. So between these two, there is a small topic called structure of functional group. Fine. So as I said, I'll be doing the nomenclature and classification at a stretch of for almost 40 to 45 minutes, combining all the organic chapters. But now directly I'm going to the topic structure of functional group. Let us see the questions asked in the boards. Yes. So basically when I speak about structure of functional groups, in grade 10 you have studied something called, you've learned in grade 10 regarding the structure, types of functional groups. Alcohol means all means OH. Al means aldehyde, one means ketone. So let us come back and use the same basics. So functional group, when we speak about structure, now in alcohols, when we speak about alcohols, as the name suggests, all, yes, all represents the functional group OH. Fine. When we speak about phenol, right, these are also alls, but here in phenols you have an aromatic ring linked to OH. This is aliphatic ring linked to OH and aromatic ring linked to OH, phenols OH. When we come to ethers, as in ethers you have two alkyl groups on both the sides, and this is your functional group. O is the functional group. If you have two alkyl groups, methyl, ethyl, not a problem, but in between if we have an electronegative oxygen atom here, then it is called ether, right? Yeah, let us come back. So there are two questions given based on this structure of a functional group. We'll be solving one after the other. Let us read the question first. Now what are we observing here? This is methyl group, alkyl group. Here all single bonds, sp3 hybridization. Here in phenols you have double bonds, sp2 hybridization. Again in ethers all single bonds, sp3 hybridization. So let us read this question. How should I remember this, ma'am? Basically try to practice this structures and try to remember, bond length. They will not ask you what is the bond length specifically. They'll ask you why is this more than that, why is that less than that. Let us read. Bond length of CO bond that is 136 picometer. So 136 picometer is basically pertaining to phenols, is shorter than in methanol, is shorter. Let us see. They're asking me basically here this question. Now in alcohol you have a bond length between C and O of 142 picometer. Here you have between phenol and oxygen 136 picometer. Yes, they're asking you why is this shorter. So let us write the reasons first. So when I see basically in both the things, what is different here H is same, not a problem. O and O is same. But what is differing? Here in alkyl group, OH is attached to alkyl, right? In alcohols, OH is attached to alkyl group. Yes, here OH is attached to the benzene ring. Most important. So in benzene ring, what is actually happening? There is always delocalization of pi bonds. So first, let me write in the first point in phenol. Because they've asked you about phenol, start writing with phenol. In phenol, OH is linked to benzene ring. That is done. So when OH is linked to benzene ring, what happens? Let us see. Here you have, first of all, oxygen is highly electronegative and it has lone pair of electrons. Just see 1, 2, 3, 4, 5, 6, 7, 8. So because of this lone pair of electron, oxygen shows conjugation with this benzene ring. Yes, you have studied. Yeah, when it shows conjugation with this benzene ring, immediately what happens? There's a partial double bond created. This is going to drop here and a double bond is created at this point. So what will I write? Oxygen due to presence of lone pair. LP stands for lone pair. What it does, it's going to undergoes conjugation. It undergoes conjugation because these are all the keywords. They're going to see this is linked to this is conjugation. So underline this conjugation. This is what the examiner wants you to write. Now, what happens when it is undergoing conjugation? What type of bond does it form? It forms double bonds. Correct? It's going to drop in the lone pair. It is going to form double bonds. So I'm going to underline this double bonds. Yes. Now, when it is undergoing or when it's forming double bonds here, now observe carefully. This particular double bond, yeah, when I compare with this single bond, now I have a doubt. Here also you have oxygen. Here also 1, 2, 3, 4, 5, 6, 7, 8. Here also it can drop in and go double bond. But here what is happening? This particular benzene ring shows plus R effect. It is all electron releasing group, right? It's going to show plus R effect, and this is going to show minus I effect. Fine. So what happens is when this drops into this, you have a partial double bond character, and we very well know double bonds are shorter than single bonds. This is what double bonds are shorter than single bonds. Correct? Yes. So now now I told you this is showing plus R effect, but is there any plus R effect group here? Not there. So oxygen, first important thing, conjugation. Second important thing, once it attains conjugation, it becomes double bond. Once it becomes double bond, we very well know double bonds are shorter than single bonds. That is why it is 136 picometer. Here it is 142 picometer. I am observing one more thing in this. What am I observing? Here this carbon is sp2 hybridized. Here this carbon is sp3 hybridized. Yes. In sp3 hybridized, what is the percentage of S? 25%. So in ROH, S percentage is how much? 25%. Yes, in AROH, if it is sp2, so in AROH we have sp2. S percentage is 33%. Correct? Now I'll answer. So now I've explained in terms of double bond. Now I'll explain in terms of hybridization. If S percentage is 25%, here S percentage is 33%. More the S character, stronger is the bond. Remember that. Higher is the S character, stronger is the bond. So henceforth, you have lesser bond length compared to ROH. So you can write here more S percentage, stronger is the bond. That is how you are going to reason your answer. It is a bit congested, but please note it carefully. This is how we are going to write and finish it off. So conjugation 1 point, yes. Double bond character 2nd point. Third, sp2 hybridization 3rd point. Let us come back to next question. Why phenol has smaller dipole than methanol? First of all, what is dipole? Due to the difference in electronegativity, one gets a partial positive charge, the other gets partial negative charge. Now they are asking you, compared to methanol and phenol, why is phenol having smaller dipole than methanol? That means why is it not breaking up into two different charges? Why is this not getting partial negative and why is this not getting partial positive? Let me see how to write. Okay, right. Now, basically when I speak about phenol, this clearly shows there are two important things in this. One is the alkyl group and one is the oxygen group. Now, we very well know oxygen shows electron withdrawing inductive effect, right? Remember that. Highly electronegative element, yes. So what it does, it shows always it tries to drag the electron density towards itself. So here in phenol, what is important? Oxygen shows electron withdrawing inductive effect. So what is electron withdrawing inductive effect called? Minus I effect. Minus I effect. Now, fine. When I speak about benzene ring always has all double bonds, right? We already know it keeps delocalizing, it shows resonance continuously, the shift of double bond from here till here, here till here, here till here. So always it has a pair of electrons which it can easily donate. So when something is donating, what type of effect we got? We call it as electron releasing R effect, that is plus R effect. So what should I write here? Benzene shows electron releasing effect, that is plus R effect. Plus R effect. So now here this is releasing, this is dragging, releasing, dragging. Finally, a lot of electron cloud forms around this particular point. Yes, when a lot of electron clouds forms between, is there any requirement or is there any difference in charges? No. So that is the reason, because of this electron releasing, because of this electron withdrawing, there is no requirement or there is no formation of dipoles. There are no polarity formed. So because of these two effect, so minus I and plus R, these two act as opposing, means both are acting on this. Because of this character or because of this property, there is no dipole created. That is what you are going to say. Because of this, no dipole observed. Yes, this is how you're going to write. But when I come and see this alcohol, not a problem. Here there is no plus R effect shown. This is clearly, there is no aromatization, there is no pi bond formation, there is no delocalization. So it can easily form this. There's one more question asked related to this. See how should you write. If the question asked is like this, why phenol has small, now they've asked you why phenol has smaller dipole. If they ask you, is phenol more polar than alcohol? Yes, tell me, is it easy? No. Why? Because here always you have two forces acting. It is not easy for me to break the bond and form new bonds. So phenol is less polar than alcohols. Remember that question. Please note it. Welcome back to one more session of chemical reactions of phenols. So we've already done the preparations and I gradually came into a topic called chemical reactions involving your OH bond, right? So this is what I said. I showed the cleavage of O and H and I've shown you a list of reactions for phenol. Now the topic which I'm going to discuss today is chemical reactions involving your benzene ring, right? Your benzene ring. Ma'am, what is the specialty here? Let me explain. Basically, we have in our chemistry electron donating groups, electron withdrawing groups, isn't it? We have studied electron releasing groups or electron withdrawing group. Under electron releasing group, you also have a category called strongly electron donating, moderately electron donating and weak electron donating. They are electron donating, but the variation, or as soon as an electrophile enters into the benzene ring or enters into the reaction, it immediately releases electrons and it opens up the sites at ortho and para position. So our phenol, whatever we are trying to explain, it comes under the strongly electron donating group. Remember that phenol, your OH group, it comes under strongly donating. They're very strong electron releasing groups. ERG stands for electron releasing groups, right? Fine. They keep on releasing electrons as soon as an electrophile comes into the ring. Now, oxide, O minus, means your phenol, phenoxide ion, also a strongly releasing group. You also have primary amines. Your primary amines, what are primary amines? NH2. nitrogen with two hydrogens. NH2 is a strongly electron releasing group. After that, secondary amines, that is NHR. Again, strongly the electron releasing. Tertiary amine, that is your NR3. Again, electron releasing. Your ethers. What are ethers? Represented by OR, right? ROR. Correct. So OR is a group. Alkyl group is the other alkyl group which you have taken. So whenever you find such functional groups in the surface or present in the particular reaction or particular in the benzene ring, on the surface of the benzene ring, one thing you have to remember, these are going to, suppose if I pick up one example of this, suppose if I pick up one example, whichever electrophile comes in attacks this is going to release electrons to this, and it shows resonance of the ortho and para positions. Ortho, para, ortho, meta positions. So it's going to allow the incoming electrophile either to your ortho position or to your, it also allows at para position. I'll be showing that also. It will also allow at the para position. Remember, not at meta positions. So remember, so because of this concept, we always get two types of products: ortho product as well as para product. So I'll be showing a list of reactions. Please let us note the concept of. Only thing I have to remember, if phenol is there or phenoxide ion is there, only I'll get two products. One is ortho, one is para. Most of the times para is major, but in nitration, ortho will be major. I'll be showing that. Please note it. Yes, so now I know the concept. If these are there, I'll be getting ortho and para. So let us start. Now when I start or when I write the heading of electron or reaction shown by benzene ring, basically reactions shown by benzene ring of phenol. Okay, now I'm not only benzene ring of phenol. Let me list out. Here, most of the chemical reactions or most of the name reactions which are very important are found in this phenol chapter. Please, I'll be giving out one reaction and reaction mechanism also. Please don't neglect while practicing. I've seen students, when there's a video like mechanism, you're just not even watching the video. Be very careful. Mechanisms are very important. Name reactions are very important. I've been telling the same since many videos. See, for us, let us not leave that 1 mark or let us not leave that 70 out of 70. Let us achieve that 70 out of 70 and see the amount of happiness you and your family members will have. You will be in the CBSE website when you get 70 out of 70 for the whole year. Remember that. So let us come back. So reaction shown by benzene, it basically shows reactions like electrophilic substitution reactions. Under electrophilic substitution reactions, it will be showing us bromination reactions. It's going to show us alkylation reaction. It will show us nitration reaction. It will also show sulfonation reaction. So in all the cases, remember, all these electrophilic, it will show both the products, ortho product as well as para product. I'll be giving questions in between where which one is important, which is major, which is minor. Please note it properly. If I come to the name reactions of phenol, very important, the most famous name reaction, yes, or even this is used in your lab. You will be asked in the lab, in your practical exam as a viva. When you're given a test for functional groups where you're given phenol, your examiner, the practical examiner may ask you this question from the theory part. So I'll list out that also. The first important reaction is Lieberman's reaction. Very, very important reaction. Lieberman's reaction. When I've gone as an examiner to one of the school, I asked them this test to show, or I asked them to explain this test along with the reaction. Please remember Lieberman's reaction for phenol. After that, you will be learning the famous Kolb's reaction. You'll also be, okay, I'll make a line here. Okay, you'll also be learning Gattermann reaction. You'll be learning oxidation of phenol. You'll also be learning reduction of phenol. And again famous, Reimer-Tiemann reaction. Reimer-Tiemann reaction, important reaction. And what else do we have? Yes, coupling reaction. Coupling reaction with BDC, coupling with BDC, benzene diazonium chloride. I'll be showing all the reactions. I'll also show you the mechanisms wherever it is required for you all. So please note this, and I'll be starting first with this and come back to this. So let us come back. We have already done the bromination reaction of phenol. So now let us come back and see one reasoning question of alkylation and acylation of phenol. So in the exam, if this is given to you, Friedel-Crafts reaction, we very well know Friedel-Crafts reaction is of two types, correct? One is alkylation and one is acylation. So basically, phenol, if it is Friedel-Crafts alkylation reaction, Friedel-Crafts alkylation reaction, I'm just writing it as alkylation here. And when I speak about Friedel-Crafts acylation reaction, just remember phenol, so that means in alkylation you're going to add CH3Cl, in acylation you're going to add CH3COCl, correct? RCOCl. Remember, phenol does not show Friedel-Crafts alkylation reaction, right? Remember, so in the exam if this is given, just write no reaction. When I'm doing my reasoning questions, I'll explain why it is not showing, why aniline also doesn't show Friedel-Crafts alkylation reaction. But when it is acylation reaction, basically you're going to find two types of products. Let me show you that. So in acylation of phenol, what is the nature of phenol? This OH, whatever is there, it is a bidentate nucleophile. That means bidentate nucleophile. What does that mean? Bidentate means two sides. It can attack from both the sides. It can use this side as attacking in this also, this side also. So this whole phenol, basically, if I speak, it is a bidentate nucleophile. It can attack, means this particular AR can attack from this side, this ROCl, and from the other side. I'll show you that. So because of this bidentate nucleophile nature, what happens is when phenol is, or when it is made to attack with your RCOCl, instead of CH3 I'm going to take as RCOCl. So what happens is this phenol will show me, or it will give me two different products. How does it attack? Just see, this is your phenol ring, correct? Yeah. Now your OH is here, and this particular thing is going to cleave here. This is your electrophile, this is your nucleophile. It's going to show me C double bond O and R. This is one product. Yes, this is one product. And the other product is phenol is going to show me one more product where, just both, you'll get an ester. Just see, you get an ester. So yeah, this is the ester. You're not finding an ester formation, you will find an ester formation. So what happens is, basically in alkylation there is no reaction for phenol, but in acylation it's going to show me two products. This is one product and this is one product. Finally, when I observe the structure, it's going to give me ester when it is reacting with acylation group. So we call it as C acylation, A acylation basically. C acylation is something called, this is called C acylation. We don't have in your syllabus, but I'm just mentioning it. This is called C acylation. This is called A acylation. What is that? C acylation, A acylation. C acylation is basically electrophilic aromatic substitution reactions, and C acylation is nucleophilic acyl substitution. This is called electrophilic aromatic substitution, and this is called nucleophilic acyl substitution. Just remember, this will not undergo alkylation, but if it undergoes acylation, these are the two products. One is this electrophile attacking, the other thing is nucleophilic acyl substitution reactions, where we get an ester reaction. Yes, so remember this. So please note it. Yes, and now after this, let us go back and do one more reaction of phenol, that is your nitration reaction. Remember, phenol, as I said, it's an OH group. OH is strongly electron donating, and it is going to give me ortho product and para product, correct? Now let us see. Now I'm going to take phenol, so let us write this heading, nitration of phenol, right? So when I'm going to take this phenol, yeah, and in the paper, if you find dilute HNO3, yes, at 20% or 20 degrees centigrade, and if you find concentrated HNO3, right, both, correct, concentrated HNO3 along with sulfuric acid is a nitrating mixture. This concentrated HNO3 or dilute HNO3, what is electrophile it is going to give us, or what is electrophile which is attacking NO2 plus, right? NO2 plus is an electrophile, correct? Here also it is NO2 plus is an electrophile. Now what happens is, at dilute HNO3 at 20 degrees centigrade, yeah, it's very dilute, isn't it? So the attack of this electrophile attacks at two positions. But remember, dilute, the electrophile is this, it's going to attack at two positions. Now one is at ortho position, one is at para position. Okay, one is at ortho, one is at para position. Yes, now this is your ortho nitrophenol and this is your para nitrophenol, correct? Now, when it is your concentrated nitric acid along with the nitrating mixture, rather nitric acid and sulfuric acid, at a stretch you get all the three occupied. What that is? 2, 4, 6. All the three are occupied. That is 2, 4, 6. Tribromophenol. Tribromophenol, or it is also called as picric acid. Picric acid. Yes. Right. Now observe carefully. What is the reason? Let us see the reason. Now here, if I speak, here it is a dilute condition, here it is the concentrated condition. So immediately the site is opened up and all the three sites which are ortho, para and ortho positions opened up, and the incoming electrophile has come and attacked. Fine. But now in the exam, if they ask you compared to ortho and para, which is a major product, because in the earlier reaction bromination, what did I say? Para is more stable. But here, if I compare ortho and para nitrophenol, this is a major product and this is a minor product. Remember that. I'll explain the reason. Please note it. For dilute, you get ortho and para. For concentrated, you get 2, 4, 6 tribromophenol at a stretch. Remember that. Earlier in bromination, aqueous bromine will give you 2, 4, 6. Bromine and carbon disulfide will give you ortho and para product. Okay. Let us come back and reason this. So this is the question. Yes. So now what question may be asked from this? They may ask you in nitration of phenol, which is the major product? Which is the major product? So what did I answer just now? I said ortho is the major product, correct? We have to reason that. So you will write like this, just write. Right, I am writing now ortho nitrophenol. Here I will be writing para nitrophenol. Okay, I just wrote that NO2 plus. Here I have written. Yes. Now observe carefully. Here what happens in orthonitrophenol, when I said this is a major product, isn't it? This is major, this is minor. Correct? And now what is the reason? Simple. As you've seen, what are you observing? In orthonitrophenol, there is a formation of hydrogen bond in between oxygen and hydrogen. Yes. So what is happening? There is a formation of hydrogen bond. What type of hydrogen bond is this? This is intra. Intra means within the molecule. There is intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Here what happened? Yes, here what happened? You have this para nitrophenol. So this is one molecule, this becomes reverse. Just see, this bonds with one more nitro group forming. Now here what happened here? You have this nitro, on the other side you have your H and OH. So what did I show you? Let us understand again. Here in this case you are finding hydrogen bonding within the molecule, so I call it as intramolecular. But here I am finding hydrogen bonding, but it is found in between two molecules. That's why this is called intermolecular hydrogen bond. Inter means between. Intermolecular hydrogen bonding. So because of this reason, yes, so what happened, which is stronger? Yeah, this is stronger, isn't it? This is very strong and this is more preferred, more stable. So this is a bit, compared to this is a bit less stable. So we always say this is more strong and this is highly preferred product. Let me reason again. Compared to orthonitrophenol and paranitrophenol, which is the most preferred product, this is a major product. So I wrote MJ. So let me write major product. Why is this major product? Because of intramolecular hydrogen bonding, which makes it more stable. Hence it is highly preferred. And this shows intermolecular hydrogen bonding, hence it is less preferred because less stable than compared to this. This is how you're going to reason the question. So let us see one more reaction. As I said, your phenol is ortho and para-directing. Let us do the first reaction of electrophilic aromatic substitution reactions, that is bromination. So here I'll explain you, I'll give you a reasoning question regarding this. Let us see. Suppose in the exam, remember two things. Either bromine is given with polar solvent or bromine is given with non-polar or less polar solvent. Remember that condition. Suppose in your paper, if you're seeing phenol and if you see this condition like this, okay, fine. If you're seeing aqueous bromine and if you're seeing bromine in carbon disulfide, remember, it can be carbon disulfide or it can be chloroform, it can be carbon tetrachloride, right, or less polar solvent. Fine. Let us see. What is the difference between this one and this one? Bromine, bromine are same, not a problem. But here, this is a polar solvent and this is, I should say, less polar solvent. Less polar solvent, right? Ma'am, basically you would have got a doubt. Ma'am, whenever we do alkylation, acylation, we try to pick up your AlCl3 free graphs. Suppose if I am doing bromination, I would have picked up FeBr3, right? Normally what we do, whenever we are doing bromination reactions, we try to pick up FeBr3, which acts as a Lewis catalyst or Lewis acid. FeBr3 and then we brominate it. But here, what happened? Instead of FeBr3 as a Lewis acid, I'm going to pick up a different solvent like a polar solvent and a non-polar solvent. Let us see what products we get and then we'll do a reasoning question. Whenever you're seeing aqueous polar solvent, remember the product which you get is your phenol. You get 2, 4, 6 tribromophenol. Remember what product do you get? 2, 4, 6 tribromophenol. Why did I write this? What this is 1, 2, 3, 4, 5, 6, 2, 4, 6 tribromophenol. But as soon as you see, when you see such less polar solvents like carbon disulfide, if I say most non-polar like solvents, or your, as I said, you can also see chloroform, yeah, chloroform in that. If you see carbon tetrachloride, any of these solvents, the product which you get is either two different products. Your phenol ring, you may get either ortho product and you also get para product, right? Two different products you get, ortho bromophenol and this is para bromophenol. Yes. Now what is the difference? Let's observe carefully. What happens is, hope you have understood this. I'm not using this thing. Why? I have to reason this also. FeBr3 is not used as a Lewis catalyst here because we very well know OH is a strongly electron releasing group. Correct? When it is strongly electron releasing group, it is going to direct the incoming electrophile to the ortho position and para position. Then when OH is already present in the ring, I don't require any Lewis catalyst for allowing the electrophile to enter to ortho para. So we don't use FeBr3 here. You can also use these solvents. That is your first reasoning question. Now I'm going to erase this and start. Now here, you should get it out, ma'am. Why are we getting 2,4,6 tribromo in aqueous bromine solvent or aqueous solvent? The reason is, just see, whenever you're dissolving phenol in aqueous, that means a polar solvent, immediately your phenol when you're dissolving in an aqueous solvent, it will get dissociated or it will break up. The bond here breaks up and it forms a phenoxide ion. Remember this. What happens? It immediately forms a phenoxide ion. Now this is phenol, this is your phenoxide ion. So this phenoxide ion we very well know is highly or strongly electron donating group compared to phenol. Phenoxide is strongly electron donating. This strongly electron donating group immediately, now because it is polar solvent, it is dissociated, and from a strongly electron donating, now this, because of this strongly electron donating group, it will try to donate its electron here. This becomes a partial double bond. Yes, it will become a partial double bond, and finally what happens? Double bond and double bond can't stay together. This goes like that, this shifts, then this shifts, and finally you get a site where ortho position, para position, and your the one more ortho position, all these are opened up due to resonance structure, right? So what happens? Because of this, finally you get an ortho, para and resin, and all the three are opened up. That is the reason your incoming electrophile immediately goes and attacks at OP and P. Ortho, para and ortho positions. Once again, whenever you find, if the question is asked, whenever you find aqueous bromine, why is it showing 2, 4, 6 products? Answer should be, when phenol is dissolved in aqueous bromine, it will immediately dissociate into phenoxide ion. Phenoxide ion, we very well know, is a strong electron releasing group, and due to resonance it immediately shifts its bond and attains a partial double bond character. And now we very well know double bond and double bond can't stay together, so it shows delocalization of pi electrons, and thus we have ortho, para and ortho sites opened up. That is the reason in aqueous bromine you get 2, 4, 6 products. Now let us see non-aqueous or less polar solvents. Here what happens? We very well know, as the name suggests, these are less polar solvents. So when phenol is taken under this condition, your phenol dissociation into phenoxide not possible, point number 1. So phenol will not dissociate. So what is left now? Only phenol is left. Yeah, we very well know phenol also is electron releasing group, but compared to phenoxide, phenol is less electron, means it will not immediately allow the ortho, para and ortho positions to open up. But what it does, this phenol in the presence of non-polar, less polar solvents, it will give us both the products, right? It slowly releases, then again at ortho position, and then after that para positions. Remember, ortho and para both are obtained. So what should you write? In the presence of less polar solvents, phenol, ionization of phenol into phenoxide, ionization of phenol into phenoxide is not possible. So because of this, what happens? It will slowly allow the incoming electrophile to ortho and para positions. Ortho positions and para positions. Remember that. So what is a major product here? Para is a major product. So I am writing para is a major product and your ortho is a minor product. Again, one more question. Why ortho is a minor product, ma'am? You can always see the steric hindrance here is more compared to this. This is symmetrical. This is steric hindrance. So para is more preferred than ortho. Para bromophenol is more preferred than ortho bromophenol. So note this. This may be one question with FEBRT. There may be one question with this. Why? There may be one question with this. Yes, so let us come back and do one more electrophilic aromatic substitution reactions, that is sulfonation reaction. Yes, so we've already discussed bromination. We have done nitration. So please remember, whenever you are doing electrophilic substitution, 2 conditions: aqueous bromine as well as bromine in carbon disulfide. In nitration, you should always remember dilute nitric acid and concentrated nitric acid. And Friedel-Crafts alkylation, I also gave you the reason. Friedel-Crafts acylation, formation of ester also, I've shown you this. So let us come back and do sulfonation now. So when I take your phenol, right, sulfonation basically occurs in the presence of concentrated sulfuric acid. concentrated sulfuric acid. This also concentrated. Why have I taken two different reactions? One, if the concentrated sulfuric acid is made or added at 25 degrees centigrade, in the exam they'll give you the temperature. If this concentrated sulfuric acid is added at 100 degrees centigrade, we very well know sulfuric acid, when this is added, the electrophile which is going to add is SO3H. Yes, this is your grade 11 syllabus where you have seen dissociation forming SO3H as the electrophile. So H2SO4, SO3, SO3H and OH is the leftover thing. Right. So this SO3H, here also SO3H is an electrophile. Just as I said, this is an electron releasing group which will allow the incoming electrophile to ortho and para. Simple as that. So you get phenol with one ortho product and you'll get phenol one with para product. There's nothing, no logic and simple, like ortho and para, when they open up due to resonance you get two different products. Here when I say, basically first we get the ortho product, that means further when the temperature is increased to 100 degrees it forms a para product. Simple as that. So let us name this compound. This is what? This is ortho, because ortho position, correct? I can also write like this, phenol sulfonic acid. This is also right. Right? Say the same way. Right? Para phenol sulfonic acid. Sulfonic acid, where para is a major product. Yes, this is your sulfonation reaction. Only thing you have to remember in this is temperature. 25 degree would be, but both, remember, don't write dilute sulfuric acid. It is concentrated sulfuric acid, but at different temperatures. Lower temperatures you will get ortho product. Higher temperatures you will get para product. Done? Yes. So now I've done all the electrophilic addition reactions. Now what am I left with? I have to do all the name reactions now. In the name reactions, let us list out the name reactions which we have for phenol as I did earlier. You have Lieberman's test, Lieberman's test or Lieberman's test, nitroso test. You have Kolb's reaction. You have Reimer-Tiemann reaction, Reimer-Tiemann reaction. You have Gattermann's reaction. You have coupling reaction. You have oxidation reaction. You have reduction reaction. Yes. Yeah. So when I start with the Lieberman's test first, basically Lieberman's test This test is also called as Lieberman's nitroso test. This is also called as Lieberman's nitroso test. Where will this reaction be useful? Basically, this reaction you'll be using it in your practical experiment. You have your 30 marks practicals. There the examiner may ask you, when you're doing your experiment, your content-based experiment, where you have alcohol testing, you have phenol testing, you have amines testing, ester testing, in that acid testing, in that if you're given phenol as one of the functional group, if you are asked to identify that functional group, Lieberman's test is a confirmatory test for phenol. Okay, there's one more test like phthalic anhydride. I'll be doing that also. So Lieberman test is basically a confirmatory test for phenols. So it is a confirmatory test for phenol. Remember this. If your examiner is asking you, tell me the confirmatory test for phenol, you can use this test as an example. Basically, in Lieberman's test, what do? We pick up or we take the functional group phenol. To that, you will be adding concentrated sulfuric acid. When you are adding this, once done, you are going to add to this test tube two important things. One is sodium nitrite and a second important thing is excess water. When you are adding these two, you will be getting a red coloration formed in the test tube. So the first indication after adding NaNO2 is red coloration. Once this red coloration is obtained, to this red coloration, if you are adding a base, sodium hydroxide, immediately this will turn into a blue colored solution. Blue colored solution. Let us see what is this red and blue colored solution with the reactions. Now, I'm going to take out all these and let me start with the reaction. Yes, so in this particular reaction, first important thing, what am I taking? I'm going to take, right, I said NaNO2, right? Step 1, sodium nitrate. You're adding excess water to this. Okay, when you're adding excess water to NaNO2, what is this now? Sodium nitrite. Done. This breaks up into nitrous acid plus your base. Okay, that NaOH base. This is nitrous acid. This nitrous acid, I can write it as HONO, correct? Yes, now let us start. Now I am going to take my phenol. I am going to add this phenol in the presence of HONO. There is a cleavage of the bond here. Where does this go? This goes and attacks at nitro. Yes, fine. This compound, both OH and NO, is called nitrosophenol. Right? Right, nitrosophenol. This is in equilibrium with, now this H will shift here. How does this look now? This compound, double bond O, this is shifted, double bond NOH. This is called the quinoxime. Quinoxime, got it from quinone, that is quinoxime. When I show the oxidation reaction, I'll show you quinones, also quinones and phenoquinones. So this is quinoxime, remember this. Now that quinoxime, when it is reacting with phenol, just observe, this is your phenol. Okay, now phenol, what do? I'll write OH on this side. I'll write OH on this side. This is your phenol, correct? Yes. This quinoxime is going to come and, or it's going to react with phenol. Just write exactly, please don't get confused, write it exactly. Double bond O on the other side, double bond NOH, correct? Yes. Now this phenol has an hydrogen here. This is what is going to happen. There is elimination of water molecule, first point. So water is eliminated. So what do you get? Write exactly the same product there. There are two rings, 1 and 2. The first benzene ring. There is one more ring. At the end you have OH. This is eliminated, correct? So single bond N. This is linked with double bond to this ring and double bond O. This is your red colored product that is called indophenol. This is called indophenol, which is red in color. Right, what is the last step now? To this indophenol, I said indophenol, further when I add a base, it will turn to blue color, I said. Let us see that. Now I am going to add sodium hydroxide to this. When I add sodium hydroxide, observe carefully, this H and this OH comes out. What do you get? Write exactly the same product. Write this product here. Done. This is minus, this is plus. This is going to come and attack here, Na. Done. Now this is your single bond, your double nitrogen, your double bond. Just observe carefully. You have your ring, benzene ring with sodium, and everything is same. So what is the difference now? It is only the sodium which is different. So what should I write now? Sodium salt of indophenol. Simple. This is indophenol and this is sodium salt of indophenol. Why? We have just replaced the H plus from here and I got sodium salt of indophenol. So let us redo the reaction once again. Basically, Lieberman's test is for it's a confirmation test for phenol, where we are going to take, this is a basic reaction, right? So for this basic reaction, as I said, phenol should be added or with concentrated sulfuric acid. Once this is added, you in the presence of sodium nitrite and excess water, correct? You'll get a red coloration precipitate. To this you'll add sodium hydroxide and you'll get a blue colored precipitate. So once you're done with this, first do this basic reaction please. If you're not doing this, you will not get to know from where you're getting nitrous acid. And just observe, exactly cleave the point here, bond here, and you'll be getting to product that's called nitrosophenol. Nitrosophenol, which is in equilibrium with, just shift this H here. This is called quinoxime. Actually, this is O double bond O, that is oxide. So NOH, quinoxime. Now this quinoxime is going to react with phenol. This is your phenol and this is your quinoxime. What did I do? I just eliminated water molecule. Most of the students, they do mistake here. They don't open up this H plus here and they get subtracted from here. That's a mistake. So quinoxime, eliminate water and the leftover product. This is called indophenol. Yeah, red colored dye. That indophenol, further when you introduce a base, your H plus comes out along with the OH minus of sodium hydroxide and you get sodium salt of indophenol, which is blue in color. This is your blue product. Please note it. Phenols. Now we're going to start with the topic ethers, right? Please students, remember we have very less time. Yeah, I'm observing students are not taking things seriously until now. If you're not studying on the daily basis, it will be a big load for you all in the month of February. We have all the other subjects for preparing. If you're completing chemistry by the month of January, you'll be really relaxed in the month of March. So please go through the videos on regular basis, keep preparing notes so that let us finally reach that target of 70 out of 70. So let us start the topic today, ethers. Yes, so when I speak about ethers, the general formula for ethers is CnH2n plus 2O. Yes, and yeah, I'll show you the formula, then we can relate that. Basically, ethers are called as dialkyl derivatives of water. Dialkyl derivatives of water means basically your water is HOH, correct? If I am taking out or replacing this hydrogen with alkyl group, then it is called a dialkyl derivative. Yes, so both the hydrogens replaced by alkyl, so dialkyl derivative of water. Yes, fine. So this particular ether basically is going to show, or it's a very small topic given for your or prescribed for your CBSE syllabus. So this particular ether we are going to study or we are going to learn under two headings. First, we'll be studying about the preparations of ethers and we'll be studying the chemical reactions or chemical properties of ethers. Yes, so under preparations of ethers, we have hardly two prescribed for your NCERT, only for NCERT, that is dehydration of alcohol. Dehydration of alcohol, first one. Second is very important reaction, that is Williamson's ether synthesis. I'll be showing you different variations with primary alkoxide, tertiary alkoxide, primary alkyl halide, tertiary. So we'll be doing examples also. And apart from this preparations, you have chemical properties. What is this? Now in this ether, you have the cleavage of the bond of C and O. So reactions involving cleavage of CO bond. Right, done. Second, this particular oxygen 1, 2, 3, 4, 5, 6, 7, 8. It also has lone pair of electrons. It should also show certain reactions. So reactions involving involving ethereal oxygen. So what did I write now? I've written a word called ethereal oxygen. This particular oxygen, because it is present or it's forming the ether group, we call it as ethereal oxygen. So what do we name? Ethereal oxygen, which is linked to two alkyl groups on both the sides. Yes, so this is your basic introduction. So let us come back and see the types of ethers. Fine. Yes. So now when I am starting with this ether chapter, now I basically know what are the subtopics which I have in the NCERT textbook. So let us briefly start with the introduction or the types of ethers. So let us put the heading types of ethers. So when I write these types of ethers, basically you have an ether. Now I said what is the formula? ROR, correct? So ether, the first type of ether is called symmetrical ether. Symmetrical ether, where you have both the alkyl groups same. Both alkyl groups are same, symmetrical. When I divide this equal, I get CH3 on this side, CH3. This also is a symmetrical ether. Correct. Now the second category of ethers is called mixed or unsymmetrical ethers. Unsymmetrical ethers. What that means? Here you have two similar alkyl groups. Here you may have one alkyl group in this way and the other alkyl group is in this way. Yes, so both are mixed. It can be anything, prop, but, anything. So I am showing you the basic example, mixed and unsymmetrical ethers. Suppose if I have just like this, if I have CH3OCH3, both are alkyl groups. So such ethers are called aliphatic ethers. Aliphatic ethers. Aliphatic chain. Suppose if I have one end as this, the other also this. Okay, fine. Now, here we said it is aliphatic. So, this will become now aromatic ether. Aromatic ether. Correct? Yes. There's one more class of ethers where if one is C6H5O and CH3, yes, then we call it as phenyl ethers. Phenyl ethers. Simple classification, nothing much to remember. So symmetrical, similar, mixed, two different combinations, aliphatic, two alkyl groups, aromatic, two aryl groups. If I take one alkyl and one aryl, I call it as phenyl ethers. Yes, so please note it. I'll meet you again in the next video with the preparations of ethers. Discuss the types of ethers. Now let us start with the preparations of ethers. Yes, so in the preparations of ethers, as I said, we are going to prepare ethers by dehydration of alcohols. So preparation of ethers. Yeah, let us write the heading dehydration of alcohols. Correct. Now, whenever we say dehydration of alcohols, basically we need a dehydrating agent. Yes, if it is oxidation, oxidizing agent. In the same way, dehydrating agent. We already discussed in the previous videos, sulfuric acid is a dehydrating agent. Phosphoric acid is a dehydrating agent. Correct? Yes, it's going to take out or remove water from that particular reaction. In the same way, I can also use aluminium trioxide as a dehydrating agent. So let us write. So what do? We are going to take alcohol. So I'm going to take the basic alcohol here. Yeah. Now let us see what happens when I'm going to introduce dehydrating agent like concentrated sulfuric acid. Now I'm going to introduce again concentrated sulfuric acid here. Here I'm going to introduce aluminium trioxide. Yeah. Now if the concentrated sulfuric acid or phosphoric acid, so let us write the dehydrating agent H2SO4, H3PO4. Yeah. Now what are these called? These are called as polar protic solvents. What are these called? Polar protic solvents. So what are actually polar protic solvents? Nothing. When you dissolve these in water, if they are going to release a form or like furnish H plus ions, then they are called polar protic solvents, right? So we've already studied SN2 mechanism, polar protic solvents, polar aprotic solvents. So let us come back. Polar protic solvents are those, when I dissolve this, it will become H plus and HSO4 minus. So if it releases H plus, then it is called polar protic solvent. Fine. So I said I'm going to take this particular one, concentrated sulfuric acid, L2O3. If concentrated sulfuric acid is picked up at 413 Kelvin, what happens? If you are taking concentrated sulfuric acid, you are increasing the temperature of to 443 Kelvin, what happens? And when you are introducing aluminum trioxide, let us see. In the exam, they will not ask you directly what is dehydration of alcohol, nothing. They will give you the reactant, they will give you the temperature, you have to show the product. They may be the other way, they may give you the product, you need to write the temperature and write the reactant. Anything may happen. Please remember, anyways you have to be clear with the concept. Now I am going to take this here. When it is concentrated sulfuric acid, let me pick up 2 moles of this. So how does this reaction look? C2H5OH plus OH C2H5. Right, I'm writing I've already written the reaction conditions here. There's an elimination of water. Why is elimination of water? Because I said sulfuric acid is a dehydrating agent. So this is going to take out water. And what am I going to get? I'm going to get C2H5O, C2H5, a symmetrical ether. Diethyl ether. This is called diethyl ether. Done. I just got water, I got diethyl ether. Now if it is in the same condition, suppose, let me take some place here. If it is in the same condition, if it is again concentrated sulfuric acid at 443 Kelvin, remember higher temperatures, more than dehydration, elimination or formation of alkene is more preferred. Yeah, elimination more than dehydration, we get an alkene formation at higher temperatures. How is this possible? Just see, I am going to take this CH3 CH2OH. Now what conditions I'm using concentrated sulfuric acid 443. Basically now elimination of water molecule. This is dehydration of water molecule, but here after dehydrating you're getting an ether, but here eliminating water molecule. So one hydrogen from here, H, one OH from here, OH. Remember, one from this carbon and one from this carbon, and the bond in between these two shifts here. This is here like this shifts here. So what do I get? Basically, what am I doing? There are 2 carbons, one hydrogen from here, one OH from here, and the bond here is shifting. So what do I get? This becomes CH3 CH2, correct? This bond has shifted here. Now this also becomes CH2, ethene. So I get ethene. So when you increase the temperature, elimination is more preferred than the normal dehydration. So again, once again, this is also dehydration, but what is happening? You're finding an eliminated product, that is alkene. So remember this temperature, 413, casually normally you can take out water with seeing this, but 443, don't try to make it 2 moles. Remember, at higher temperatures alkenes are formed, correct? Yeah. Now let us come back and see the third reaction, that is with Al2O3. This is also a dehydrating agent, just like the first one, nothing big, it's the same. It acts as a catalyst here. Al2O3 acts as a catalyst, where again I am going to take same C2H5OH plus OH C2H5. I am going to eliminate water from here and I am going to get an symmetrical ether. It's the same thing, diethyl ether. So this is how you are going to prepare ethers. Remember the temperature conditions are very important. Lower temperature ethers, higher temperatures alkenes. Yes, so note this. Yes, so let us come back and do one more mechanism. We've already prepared ether, that is diethyl ether, but from concentrated sulfuric acid, using that is 413 Kelvin, correct? Yes, 443 we have made an alkene. So what your CBSE wants you to learn the mechanism for the dehydration of alcohol in the presence of concentrated sulfuric acid to form ethers, right? So the heading would be in your exam, if this question is given to you, they would be given or you will be given write the mechanism for acid catalyzed dehydration of alcohols, right? So that is what we did earlier. So in acid catalyzed dehydration of alcohols, what did we do? We took alcohol, ethanol. How many moles? We have taken 2 moles. Then I have introduced a polar protic solvent, H2SO4. I said polar protic means they are going to donate H plus ions. Correct? Yes. This polar protic solvent in the presence of this dehydrating. What is this agent now? It is a dehydrating agent. It is going to remove water. So H from here, OH from here is removed and you have got diethyl ether. Correct? Now they want us to show this mechanism. Simple. So when I have to write the mechanism, basically acid catalyzed dehydration. There are 2 ways of giving this. If they directly ask you the mechanisms, write the reaction, start with the mechanism. But in some cases, like last year CBSE paper, what they've done is they've given this reaction. Yes, they've not mentioned anything above. They've given this reaction, state the mechanism of the above reaction to form ethers. So it is like that basically. So there are 2 ways. Either given directly mechanism, you can write it. Given the reaction, you have to write the mechanism. Either way it is the same, but what should you remember? This is important. If you see this is the product which is formed at 413 Kelvin. Correct? Yes. Now let us start with the mechanism. So in acid catalyzed dehydration of alcohols, basically this follows 3 important steps. First step is protonation. Second step is SN2, means it's going to follow SN2 mechanism. So SN2 mechanism. Third step is deprotonation. So what does that mean? Protonation is adding of proton from H2SO4. SN2 mechanism means the nucleophile is going to attack from the back, as we have seen in SN2 mechanism. Here alcohol is going to form the nucleophile. Third is removal of that H plus and finally forming ethers. So let us see. So protonation, step 1. In protonation, what is important? We need a polar protic solvent. So I am going to take C2H5OH and I am going to add proton to this. From where did I get this proton? As I said, I got this proton from polar protic solvent, that is sulfuric acid. Yes, to this polar protic solvent, yeah, observe oxygen. When I take oxygen, how does this oxygen look like? It is like this, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 octet, correct? Now, this is shared with this H plus. Now, how does this look? C2H5O, yeah. This H is still existing. 1, 2, 3, 4 plus and here water. Means there is a bond formation by sharing. Yes, done. Now I have protonation done. Yes, from sulfuric acid. Now what is the second step? SN2 attack. What is SN2 attack? As we have seen in SN2 mechanism, if nucleophile attacks from the back, yeah, because of the smaller atoms and finally forms a transition state and we get the product. So in SN2 attack here, one alcohol is done. In the SN2 attack, I am going to pick up one more alcohol. So instead of writing C2H for anything, CH3CH2OH. Now this alcohol is your second alcohol. We have taken 2 alcohols, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now this will behave as a nucleophile. This is going to attack from the back of this. So how does this look? If I take CH3, CH2O, hydrogen plus. Now observe carefully. This has lone pair of electron. This has formed a bond. Correct? Now what happened to satisfy this? Because this has already shared a bond here. To satisfy this bond is going to shift here. When this bond is shifting here, this becomes plus carbocation. Yes. To satisfy that, this is going to attack this carbon. Don't write here. This is where your carbocation forms. Once again, this is plus. Fine. To satisfy that or for removal of water, this bond shifts to this position. This becomes positive now. to satisfy that carbocation, your lone pair is shared with this carbocation. So what do I get now? I get two products. First thing, elimination of water, because dehydration should be done, right? So what do I get now? I have this whole group here, CH3, CH2. There is one oxygen in the center. Okay, now there is a hydrogen also here, and this group CH2, CH3. Now what happened? Oxygen has shared this pair of electron with this, so this attains positive charge. Yes, now let us come back. In the third step, deprotonation happens. Deprotonation means I am going to remove water. Sorry, I am going to remove H plus ion. This H plus is removed because then only I'll get the ether, correct? So pick that up. CH3, your CH2, your plus, and your H is here. I have to take out this CH2, CH3. Now observe carefully. This is going to come out, and this bond shifts because it's plus, right? So what do we get now? Finally, CH3, CH2O, CH2, CH3 ether. Fine. So finally I've got diethyl ether. Once again, remember, in acid catalyzed dehydration, 3 steps are important. Protonation, step 1. SN2 attack, step 2. Deprotonation, step 3. Why did I say SN2 attack? Because it's going to attack from the back towards this carbocation, and finally I get that molecule, and here your second alcohol is acting as a nucleophile, and your proton is supplied or provided by the polar protic solvent, that is your sulfuric acid. Please note it. Yes, so what did we learn now? We have learned the reactions involving the cleavage of CO bond in your ethers, correct? So I've shown you 3 reactions. One was with H2SO4, where H2SO4 broke up into H plus and HSO4 minus. Now then I showed you reaction with hydroiodic acid, HI. Remember, please, I've shown you, go through the video again so that it's easy for you to relate to the mechanism. There I've shown you under cold conditions and under warm conditions. If you're increasing the temperature, what happens? So now I'll be showing the mechanism for the cold condition, and then I'll go back to the warm condition, which is prescribed for you in your CBSE syllabus. Now I said reaction with HI, correct? Yes. Now I'm going to pick up cold condition and I'm going to show you the reaction. So under cold condition, what did we write? ROR with HI is going to break up. Just cleave it here, anywhere either side. You get ROH plus and RI. Correct? This is what we have done under cold. Let us see the mechanism for this. Suppose instead of R, I am going to pick up a CH3O, CH3. Fine? Done? Now. 1, 2, 3, 4, 5, 6, 7, 8. Correct? Now in step 1, your HI is going to come and attack. So what happens? HI will first, there is a cleavage of the bond. This becomes plus, this becomes minus. So now this pair of electron is donated to this. How does this look? CH3O, yes, 3H, this has become plus because this has lost a pair of electron. Now done. Now in the second step, observe, now CH3, can I write it as H and H? Correct? Yeah. Now this iodine, whatever is there, will come and attack this group. So which attack is this? SN2 mechanism. When this is attacking this cation, why is this attacking? Basically, this has become positive. When this bond shifts here, this attains positive charge. right? So then this iodine nucleophile comes and attacks this carbocation. So now what happens? What do you get? This particular bond, you get CH3OH. Now already this bond has broken up. What do I get? CH3I. Look here, ROH, CH3OH, RI, R, CH3. So what has actually happened? What has formed and what bonds are broken? Let us see. Bonds broken, bonds formed. Let us see what are broken, what are formed. What is the use of writing that? When you write that in the exam, it's easy. Okay, this is a bond, these bonds. You remember this bonds broken, bonds formed. Now you can directly do the mechanism. Just see. First of all, under bonds broken, HI. So HI bond is broken. Correct? Done. After that, come back here. Which bond is broken? COH bond. CO bond is broken. Which bond has formed? O and H bond has formed, isn't it? Bonds formed, O and H. Correct? Now, further what bond has formed here? New bond. This is broken. This is formed, C and I. So this is how you're going to remember the mechanism. Please note it. Under cold conditions, it's going to give me an alcohol and alkyl halide with this mechanism. So if you still want to practice it, just write the steps. Cleavage of bond of HI, protonation of this compound, then SN2 mechanism, then formation of alcohol halide. If you wish to write in steps, please note it. So we've already started with the chemical properties of ethers, where we have seen the addition of HI. What did we do? First reaction was with sulfuric acid, where I've shown you H plus addition and HSO4 minus addition. Now the next reaction would be reaction with HI, hydroiodic acid. So I've shown you a mechanism where I picked up symmetrical ether, isn't it? I picked up both the methyl groups in my previous video, and I've shown the formation of methanol and methyl iodide. That's not a problem, but problem starts when you have an unsymmetrical ether and addition of HI to unsymmetrical ether. So let us see. Now suppose if I have an unsymmetrical ether. What is unsymmetrical ether? As I said, if you have a methyl group on one side, yeah, and you have a different group. Suppose if it is C2H5, right? C2H5, if you wish to write like this, not a problem. If you wish to write like this, CH2, CH3, also not a problem. So if you have an unsymmetrical ether, C2H5, if you are adding HI to this, what are the products? Suppose instead of this, here you have a tertiary group, right? A tertiary alkyl group and an ether and a smaller group. What will happen if I add HI? Right? Basically in your NCERT book, you have a mechanism for this. For both the things, you have mechanisms. You're supposed to learn mechanism for both. How is the question asked in the exam? Write the reaction mechanism when HI is added to an unsymmetrical ether, right? Right. Now, let us remember one logic. Whenever you find a smaller group and a bulky group, means compared to this, this is a bit larger, right? Yeah. Just see, whenever you have a smaller group and a larger group here, your nucleophile, now this is your nucleophile, yeah, the nucleophile attacks to, or it'll go and attach to a carbon having less bulkier atoms, means it'll attach to a carbon having smaller atoms. So compared to this and this, this is 3 hydrogen atoms, this is 5 hydrogen atoms. So where will it go and attach? So the nucleophile will go and attach to this. Correct? So what will happen? Where will the bond cleave? Here. And what product do I get? I get CH3I plus C2H5OH. Done. So let me take out this arrow. So this is the product which you get at this particular point. Correct? Yes. Now let me see this reaction. When you have a tertiary ether or tertiary alkyl halide with this normal methyl, your nucleophile will attack the bulkier group. Because why? because the tertiary carbocation is more stable than primary, remember that. So what product do I get? I have to cleave the bond here and I get CH3, 3 and iodine, tertiary alkyl halide, plus the leftover is CH3OH. So once again, let us recollect. What do we do? When you have a smaller carbon, means a group with lesser number of hydrogen atoms, that means less steric hindrance, the nucleophile will attack that group if it is primary. So second combination, if you have a larger alkyl group and a smaller alkyl group, the nucleophile will prefer the tertiary group, means larger group means tertiary. Tertiary is more preferred there because of tertiary carbocation formation. So now we'll see the mechanism for both of them. So let us write here. Step 1 of this, yes, observe. First you are going to take this ether, right? CH3O C2H5, correct? 1 2 3 4 5 6 7 8. Now observe, HI is going to add to this. As I said, there is a cleavage of bond. Fine. So this becomes H plus, this becomes I minus. So now what happens? This is donated to this H plus. How does this look? Your CH3O, C2H5 and your I minus is out and your H plus is attacked oxygen. Because this has shared a pair of electron here, right? This becomes plus. Now this particular, if you're not writing plus, try to make a bond, not a problem like this. Now this is called oxonium ion. What is this? Oxonium ion. What is oxonium ion? Oxonium ion or oxonium is something where it is attached to 3 bonds. Remember, so oxygen is attached to 3 bonds on this side, just like your hydronium ion, like H3O plus. What is H3O plus? H, oxygen, 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 right? This is hydronium ion. 3 bonds on all the sides, so it is called oxonium ion, right? Yes, now come back. So this is done. Now your hydrogen is done. Now let us come back to step 2. Now in your step 2, what happens? This nucleophile iodine is going to it will go and attack to the less steric hindrance group. Compared to this one, this is less steric hindrance, hydrogen atoms are too small enough, equally spaced, right? So iodine is going to attack this molecule from this side. So which type of mechanism is this when it's attacking from this side? Smaller group, primary. So this is called SN1 mechanism. Remember, we have studied earlier SN1 mechanism. This is going to follow SN1, that's going to follow SN2. So in SN1 mechanism, iodine is going and attacking this group, primary, less bulkier group. Now what do I get at this particular stage? I get a transition state. Just observe, CH3OH, C2H5, right? And your iodine is here. This is your transition state which is going to stay for few seconds. Now we very well know once this group is formed, there is a cleavage of the bond. What do I get? I get 2 products here. One is your methyl iodide. As I said, the lower group is preferred, that means primary alkyl halide is formed and the leftover group is C2H5OH. Done. That is the mechanism. So remember, primary is more preferred by the alkyl halide. Let us come back to this tertiary. When I speak about tertiary, when I am writing the mechanism of this, let us write step 1. First pick up this ether, CH3. Yeah, this is going to break up into 2. One is CH3 taken thrice. Your carbon also is here. Tertiary carbocation. First important thing, it's going to break up into tertiary carbocation and the leftover CH3O minus. Now once the tertiary carbocation is formed, this is the most stable state, carbocation, most stable form. To this tertiary carbocation, now let us go with step 2. Step 2, when we see this tertiary carbocation So we did a mistake here. This is not SN1, this is your SN2. I'm sorry, this is your SN2 mechanism, right? Wrong. So it's both the incoming group and the outgoing group are present in the same transition state. So this is SN2. Yeah. So your tertiary carbocation, whatever is here, is attacked by your nucleophile now. Your HI is there, isn't it? HI. So what do I get? Then I get my tertiary alkyl halide. And when I say the leftover CH3 CO minus CH3 CO minus and your H plus of H attacks to form CH3OH. Simple. So please try to understand once again. Here I've written, so what type of mechanism is this? This is SN1 mechanism. Tertiary SN1 mechanism. Let us understand. When I have two conditions, what are the two conditions? If I have a combination of a smaller group and a bulkier group, yeah, then your nucleophile, whatever is there, it is going or it will prefer a smaller alkyl group so that to reduce the steric hindrance. So smaller alkyl group and I get this. And the leftover is alcohol. Suppose if I have a tertiary alkyl group in an ether with a primary, your nucleophile will attack tertiary only because of stable carbocation formation. So tertiary, you'll get tertiary halide. You have to see. Tertiary is given, a primary is given to me. So tertiary alkyl halide and methanol. In the step 1, as we know, as I've told earlier, this particular step, first there's a cleavage of the bond. This bond finally it forms an oxonium ion. Oxonium means oxygen with 3 bonds. Once oxonium ion is formed, your iodine is going to see which is less bulkier in both. Compared to this and this is less bulkier, only 3 hydrogen atoms. This goes and attacks from the back and forms a transition state. Now this is a transition state where you are finding both the incoming group and the leaving group. Once this is done, there is a cleavage of the bond. And the leftover alcohol. This is what you get. But when it is a tertiary ether, remember first you have to form out, it is going to break up into a tertiary carbocation, stable form. To that tertiary carbocation, using your SN1 mechanism, your iodine is going to attack and come out as tertiary alkyl halide and the leftover as methanol. These are your mechanisms for unsymmetrical ethers with HI. Yes, so students, we've already learned the acid catalyzed dehydration of alcohols and we have prepared ethers. Now next important name reaction in ethers is Williamson ether synthesis. So let us write the heading. Williamson ether synthesis. Right. Now observe carefully. It's very easy but little tricky. Let us see that. In Williamson ether synthesis, basically you require an alkyl halide. Yes. Along with this, you require, so we'll write this as alkyl halide. Along with this, you require an alkoxide. Okay. So Na instead of this, okay, this is better. This is alk oxide. So which alkoxide is this? I picked up sodium alkoxide. So sodium alkoxide. Done. Then there is an elimination of NaX. The leftover you get ether. Okay, basic thing. So for Williamson ether synthesis, when you are writing in the reaction, Williamson ether synthesis is the reaction between an alkyl halide and an alkoxide. So if you are picking up sodium alkoxide to form ethers. Here Williamson ether synthesis I can use for preparing both symmetrical and unsymmetrical ethers. Both can be prepared with using Williamson ether synthesis. Yeah, so remember this. Now next important thing is Just see whether this clue will be helpful for you. Now this is your alkyl halide, correct? This is your alkoxide. Now if the alkyl halide is primary, okay, if the alkyl halide is primary, then if it is combining with your tertiary alkoxides, okay, if the alkyl halide is primary and it is combining with tertiary alkoxide, the product which you get is ether, correct? Done. Now reverse it. Now this is primary alkyl halide, this is tertiary. Now take this tertiary here. If tertiary alkyl halide is reacting with primary alkoxide, you will get alkenes. Why? Here in this particular case, elimination is preferred, or it dominates over substitution. Rather than substitution, it prefers elimination. So because when we say elimination, there is a formation of alkene. If you remember this, the whole concept is easy for us. This is very important. Remember, please note it carefully. Very, very important. So this should be primary. Then if the tertiary alkoxide is there, you will get ether. If you are picking up tertiary alkyl halide and if you are picking primary alkoxide, I get alkene. So with this, let me start with the reaction. So done? Yeah. So now what did I say? I said primary alkyl halide, correct? So what is now this primary alkyl halide? Your X, correct? Now carbon. Then your primary is with 2 hydrogens and 1 alkyl group. So this is your primary alkyl halide. Now I'm going to take tertiary alkoxide. What is tertiary alkoxide? Your oxygen is there, your sodium is there, and your carbon or the alkyl group whichever is there is again attached to 3 alkyl groups, correct? So 4 around. This is tertiary alkoxide. In such particular cases, you're going to take out NaX, and the leftover you're going to write R. This is your CH2, your O, and your carbon with T3. It's not a problem. Comfortably I took out and I got this. This is done. Now if you are picking up this case, tertiary alkyl halide. This is the first step. Now let me take the second step. Tertiary alkyl halide means what? Carbon with X. So tertiary alkyl. All the 3 are alkyl halides. Sorry, alkyl groups. Now this is also done. Now I have to add primary alkoxide. So O is still there. Na is there. Correct. Now primary. Suppose if I take C2H5. Not a problem. This is primary alkyl halide because carbon attached to hydrogens. Yes. So if you're getting confused, if you're writing CH to C2H5, write CH2 CH3. Now see, carbon attached to 2 hydrogens, primary alkoxide. Yeah. Now what happens in this case? As I said, so in tertiary, if there is a tertiary alkyl halide, elimination is preferred than your substitution. That is what I say for forming alkene. Elimination is more preferred. Now observe carefully. What happens is basically your NaX is out. Not a problem, comfortably. Yeah. Now observe. There is this particular carbon. You can pick up anything. Now this hydrogen, this is like H3 is H2 and H. This whole thing. Yeah. Now I said I will get alkene. This whole thing comes out with this hydrogen. What do I get? C2H5OH. Now the bond which is here is going to shift here. What do I get now? CH3, C, your carbon, your double bond, CH2, your CH3. Alkene. So this is the logic. So once again, if you are taking primary alkyl halide and tertiary alkoxide, you will get ethers. The reverse. If you are taking tertiary alkyl halide and primary alkoxide, you will get alkenes. Because elimination is versus substitution. So elimination is more preferred here. So what is the order when I write order of alkyl halides? for Williamson ether synthesis. Alkyl halides for Williamson ether synthesis. So what is the order? So whenever you are speaking about Williamson ether synthesis, the order for alkyl halides is which will for ether means if I have to prepare ethers, I have to pick up primary is more preferred than secondary, is more preferred than tertiary. If you are picking up secondary and tertiary, you will get alkenes. If you are preferring primary, you will get ethers. Remember this. Please note it, and I'll come back with one more example. Yes, so we've already discussed Williamson ether synthesis. So what clue should I remember? For Williamson ether synthesis, if you have to prepare ether in Williamson synthesis, primary is alkyl halide is more preferred than tertiary. If you're finding primary alkyl halide, try to prepare ether. If you're finding secondary or tertiary alkyl halide, try to prepare alkenes, right? So let us see these examples. Suppose if this question is given to you like this. So first, as soon as this is given, now what is this alkyl halide? Carbon with 3 hydrogens, yeah. So this is primary alkyl halide. So as soon as you see primary alkyl halide, what should you do? Automatically we said, okay, tertiary alkoxide, correct? So what did I say? If you find primary alkyl halide, just close your eyes and just finish off, take out NaBr and prepare ether. So primary alkyl halide always gives ethers. Simple. Done. Now let us come back. Now again you're finding your whole concentration should be on the alkyl halides. Here, as soon as you see this alkyl halide, which type of alkyl halide is this? This is tertiary alkyl halide. Correct? Yeah. So tertiary alkyl halide automatically with your, this is your bulkier group and this is less hindrance, steric hindrance group. So this is your primary alkoxide. So as soon as you see your primary tertiary alkyl halide, blindly you have to say or find or write the product of an alkene, correct? So what did we say? First Na and Br comes out, NaBr, right? This is H and H, as I've shown. The CH3OH comes out, methanol. This bond is going to shift here. So what do I get? CH3, C, double bond, CH2 and CH3. So this is your plus. Alkene. This has come out with this. This H has come out with methanol and this bond has shifted here, so you get alkene. So where should your concentration be? Alkyl halide. That's it. Remember, Williamson ether synthesis means alkyl halide. Primary ether, tertiary alkene. Let us come back and see this. They've reversed this question. Nothing. It's the same. So where should my concentration go? My concentration should go here. Don't get confused. If this is given, where is the alkyl? Don't do. This is your primary alkyl halide. So this is primary alkyl halide. So what product should you get? Ethers. Pick up NaCl, write NaCl. So join the whole thing. Tertiary, so 3CO and C2H5. Ether. This is how we are going to solve your questions. So please remember, Williamson ether synthesis means alkyl halide primary. Williamson ether synthesis secondary and tertiary alkyl halides will give us alkenes. Yes, so we've already seen the preparations of ethers with your dehydration of alcohols. Then we also did Williamson ether synthesis. I've also given you the variations of Williamson ether synthesis. Now let us do the last preparation of ethers. That is preparation of ethers with dry silver oxide. Okay, what is dry silver oxide? Let us see. Basically, dry silver oxide is a mild oxidizing agent, right? What does it do? It's going to add oxygen. So it is a mild oxidizing agent. Whenever you see dry silver oxide, remember this concept. It is a mild oxidizing agent. It will just add oxygen to the given compound. Here, what am I going to do? I'm going to take an alkyl halide. So this is your alkyl halide. So when dry silver oxide is added, so it's going to add oxygen to this. Suppose I have to prepare ether, I'll pick up 2 moles of this. So what does this reaction come back to? R and R are 2 R's. So R, this oxygen is added, or this is going to add, I should not say that oxygen, it's going to add oxygen to that, and left over is what? AgX, correct? What, how many moles? 2 AgX. This is your ether. So this is how, so when it's basically not given in your NCERT, but remember, if Ag2O is given to you, it's just addition of ether, addition of oxygen to your alkyl halide to form the particular ether. So we are done with the preparation. So I'll meet you again in the chemical reactions of ethers in my next video. Yes, let us come back to the last topic of the chapter of alcohols, phenols and ethers. Till now we have been studying symmetrical ethers, unsymmetrical ethers. Now we'll be doing aryl ethers. So basically in aryl ethers, as I said, you have one benzene ring and one an alkyl group. Suppose if we are taking this alkyl group as a CH3, right, OCH3, then this is called anisole. I've seen most of the students, when anisole is given to them, they get confused. There's nothing to get confused. Aryl ring with O and R. This is here. This R can be methyl. Fine. So if you're taking out this oxygen, if you're just having CH3, then it is called toluene. If you have O, then it is called anisole. Right? Now let us start with the first reaction. Here, when you see anisole, basically 1, 2, 3, 4, 5, 6, 7, 8. It has a lone pair of electron, because of which this is highly activating. It's going to push the electron donating group, and further when methyl group is donating electrons to this, these electrons are also sent, or they are donated to the benzene ring. Because of this, anisole is going to attain a partial double bond character. Yes. Now, double bond and double bond can't be together, so this starts showing resonance, and finally we get a site where ortho and para positions are opened up. You have an ortho position, you have a para position, and again an ortho position where your electrophile can come and attack. So that means whenever you are finding anisole in the paper, you have to just add the electrophile at the ortho and the para position. Nothing to do, simply add it at ortho and para. Suppose these are all your electrophilic substitution reaction. This is called bromination, where the electrophile is Br. This is called Friedel-Crafts alkylation, where the electrophile is methyl group. Friedel-Crafts acylation, where the electrophile is acyl group. Nitration, where your electrophile is NO2+. Simple. Once you find anisole, first thing you have to remember is methyl is electron donating group, alkyl group. Second important thing, lone pair of electrons, those are also donated. Once they are donated, due to resonance, ortho and para sites are opened up for the electrophile to come and attack. Means there are excess electrons observed here, so electrophile can go and attack at that particular point. So now, pick up anisole, write anisole in the top, 1+ para. So how to name this? Ortho bromo anisole. This is para bromo anisole. Done? Yes, first one. Let us come back and see. Now here in Friedel-Crafts alkylation, we are going to add alkyl group, right? This is your chloride and this is your alkyl group which acts as electrophile. Now pick up anisole, OCH3, ortho plus OCH3, para. Done. Let us name this. So you can start from here. So this is 2-methoxy toluene. I said, oh, if it is only CH3 toluene, now this becomes 4-methoxy toluene. Yeah, right. Now in this particular case, I have to add the acyl group to anisole. You are going to pick up the anisole group anisole, and add, what should you add? You have to start from COCH3. Don't add CH3CO. Now again you're going to add it at the para position. This is OCH3 and para. That is COCH3. How to name this? Just observe. This is CO group, this is O group. Don't get confused. Simple. This is acetyl chloride, right? So you can just write ortho acetoxy anisole or 2-acetoxy anisole or 4-acetoxy anisole or acetophenone. That's also no problem, not a problem. Acetophenone, that also 2-acetophenone, 4-acetophenone, not a problem. If I come back to this particular nitration, you can write CH3 ortho plus your OCH3 para. Now observe carefully how to write this. Ortho nitroanisole, para nitroanisole. Yes, so let us come back and see. Anisole basically shows only two products. Ortho para, ortho para, ortho para and ortho para. Everywhere para is a major product. Always para is a major product because of its symmetrical nature. Remember, para. One thing you have to remember, as soon as you write the products, please try to name them. Yes, please note it. So we are done with the preparations of ethers. Now let us come back to the next topic, that is chemical properties of ethers. So basically whenever you are learning chemical properties of ethers, just remember ether, it reacts with phosphorus halides, right? It reacts with acids, it reacts with oxidizing agents, it's going to react with your reducing agents because it has oxygen, has a lone pair of electron present on that. So it shows a series of reactions which we'll be doing. So when I said acids, reaction of acid, earlier when I've given my introduction video, I said ethers are going to show two types of reactions, correct? So let us write the heading, chemical properties of ethers. So I said ethers are going to show two types of reactions. One is in your ROR, it's going to show reaction based on cleavage of carbon and oxygen. So the first type of reaction is cleavage of CO bond, right? When I go with the second classification, a reaction shown due to lone pair of electrons on oxygen or ethereal oxygen. So reactions due to ethereal oxygen, correct? This is what we have learned. So first I'll start with this topic. We'll be doing two mechanisms in this, and then we'll come back to that also, and we'll see the reaction with phosphorus halides and how is it going to react with different oxidizing agents. So let us come back. So when I speak about reactions involving cleavage of RX, first, so reactions involving RO bond. Yes, now just see. Now I'm going to pick up first reaction, just see. Now I'm going to take an ether. I said it's going to react with acids, so let me pick up sulfuric acid. Right? Fine. So either you can cleave it here or you can cleave the bond here. Either way it's the same. Yeah. Now you have to add this to this. Suppose if you're cleaving the bond here, I said RO bond, right? So sulfuric acid, can sulfuric acid be written like H plus and HSO4 minus? Correct? Yes. Now what happens when this is cleaving? RO becomes minus and this becomes R plus, isn't it? Now observe, your H plus comes and attacks here, so you get alcohol. Now this is minus, so what do you get? R HSO4. Simple, yeah. Now let us do with an example. So what did I say? I have to take an alcohol. So let me take CH3O C2H5. Okay, not a problem. Fine. So if you're getting confused with this one, you can write similar as this one also, not a problem, because learn from with symmetrical and then come back to unsymmetrical. So symmetrical, then I have to add sulfuric acid to this H and HSO4 minus. H plus HSO4 minus. So I'm going to cleave the bond. What did I do? I cleaved it here. So cleave it here. What do you get? This attains a positive charge, this attains a negative charge. So what do you get? Positive and negative. CH3HSO4 plus CH3OH. Methanol. This is how it's going to react with sulfuric acid. Now let us come back and see one more reaction which is involving the cleavage of RO bond. Yeah. Yes, so let us see one more. In this particular reaction, you have to remember one important thing. Reaction with acids. So earlier also I did with sulfuric acid. Now I'm going to do with a strong acid, that is HI. Very famous reaction this is. HI. HI is hydroiodic acid. Hydroiodic acid. Now let us see. Suppose if you are taking ether and you are adding HI. Now here HI I am going to add under cold conditions. I am not heating it. I am just going to add HI under cold conditions. Correct? Yes. Now just observe, there's nothing. Just cleave. I said it's cleavage of RO bond. Cleave it here. This becomes plus, this becomes minus, this becomes plus, this becomes minus. So what do you get? Positive and negative. Correct? Ri. And the leftover negative and positive ROH. Same thing which I did earlier. Now, if the same hydroiodic acid is added, now what are these conditions? These are cold conditions. If I am maintaining hot conditions, means I am going to warm that particular listen. I am going to maintain some temperature. That means I am going to take an ether. I am going to add HI. And this is but excess, and I am going to heat it. Yes, see, I'll show you the mechanism also. You have mechanism for this. Remember, both the mechanisms you're going to learn. So the product which you get is, observe, yeah. If you take 2 HI, I said excess, right? So here I didn't take excess. I took a normal one with cold temperature. If I take 2 excess, first important, observe, H2O, you will get water out. Fine, yeah. So now what else is left here? 2 alkyl groups, correct? And your iodine. That means what is this actually? How does this look? If I take an example, I'll take C2H5O C2H5 plus HI 2HI excess. Whenever you see excess and warm conditions, you should just get an alkyl. 1, 2 and 3. 2 moles of C2H5I. So plus H2O. Done. Ethyl iodide. When it is cold conditions, you are getting your alcohol and your iodides, or means whichever halogen you get, alkyl halide. When it is warm conditions, you are going to get 2 moles, means C2H5 linked of iodine and C2H5 and water molecule. When I show the mechanism, you will clearly understand what is. Please note it.